Very good morning, everybody, and welcome to day 3 of Science at the Shine Dome. Another beautiful sunny day here in Canberra. My name's Anna Maria Rabier. I'm the Chief Executive here at the Academy. I'd like to begin by paying respects to the traditional owners of the land on which we meet, the Ngunnawal people, and pay my respects to elders past, present and emerging on all of the lands on which the Academy operates and its fellows live and work. We're here today to enjoy the scientific presentations from fellows elected in 2024. I'm very much looking forward to them. Before we get started, I'd like to take this opportunity to introduce an Academy Fellow and Chief Defence Scientist, Professor Tanya Munro, who joins us on behalf of joins us as one of our platinum partners. The Department of Defence has very generously sponsored Science at the Shine Dome, and we are very, very grateful for that sponsorship. Professor Munro is known to many of you. She's a physicist, well known for her work in photonics. She has been Australia's Chief Defence Scientist since 2019, and prior to that was Deputy Vice-Chancellor Research and Innovation at the University of South Australia. She was elected to the Academy in 2012 at the age of 39. She's an accomplished celloist and a serial glass ceiling breaker. Please welcome to the stage, Tanya Munro.
Thank you, Anna Maria, for that lovely introduction. I too acknowledge that we meet here on the lands of the Ngunnawal people. Our Indigenous brothers and sisters, ancestors, were this nation's first scientists, technologists, innovators, and we still have so much to learn about the way they generate and apply knowledge. Firstly, to all of the new fellows, warmest congratulations. It's an extraordinary honour to be recognised as a fellow of this very esteemed Academy. And when you walk across the stage and sign that book, you realise you're part of Australia's science history. Warm congratulations. I still remember the buzz that I got doing the same 12 years ago. I'm very proud to be a fellow of this Academy. Defence is proud to be a platinum sponsor of Science at the Shine Dome this year and have done in previous years because science is critically important to our nation. Science is important to our nation in every sphere of endeavour, from health to agriculture to basic understanding of the world in which we live to, of course, the defence of our nation. We're living in very challenging times at the moment, and you really don't have to look very hard into today's media to see that the terrible toll that conflict is playing across our world. Even today in Melbourne, as the Land Forces Conference happens, you can see that we have many citizens enjoying that privilege that we fight so hard for in our democracy, which is the right to protest. You could argue that we've gone over the last 10 years from being a nation protected by our geography, able to feel safe in the separation from conflict, to being a nation now that through the advances in technology is experiencing conflict right now in the cyber domain, right to knowing that we no longer have a 10-year warning period of more immediate conflict in our region. And I really just wanted to briefly share with you the sense of what role science plays in this. In July this year, Defence Science and Technology Group celebrated 50 years since its antecedent organisation, DSTO, was formed. And the group, which I'm very proud to lead, has done all sorts of wonderful things to deter conflict. And that's where I think science can make the biggest difference to the defence of our nation and our security as Australians. When we do our job well, you don't know that we've done it. Some of the extraordinary things that our defence science has done for our nation include the world's best over-the-horizon radar systems, or the black box in every aeroplane developed by David Warren from Defence Science. I call on each and every one of you to reflect about how your science could potentially make our world safer. Our nation has now signed up to a strategy of deterrence. And what deterrence means is that every day a potential adversary wakes up and says, today is not the day because the risk of them following actions relevant to their national interests outweighs the reward they see they would get by applying that force. Through science, we can make sure that our smaller nation with vast territories to protect can keep this region peaceful and keep our men and women out of conflict. Thank you very much for the science you do, for the difference you make to our nation. Together now, you join this community of fellows that I'm very proud to be part of, and I look forward to working with you over coming years to see how Australia can continue to be a free and democratic country. Just before I get off the stage, I wanted to state that you see behind me a banner for a summit we're having here in Canberra next week. If you're interested, please sign up. We're bringing together Australian academia, industry and our international partners from around the globe to see how we can better harness the excellence in Australian science to protect Australia. Thank you, and again, warmest congratulations on becoming Fellows of the Academy. Thank you.
Thank you, Tanya. And in addition to thanking you for your generous sponsorship of Science at the Shine Dome, thank you too for your collaboration as we worked through the amendments to the Defence Trade Control Act earlier this year and last year. I think it's fair to say that the relationship between Defence and the Academy is a lot stronger, and the outcomes of those negotiations have placed research in a better place. So thank you for that. We will have people at the conference next week, so that's excellent. And may I also thank you for forging many, many collaborations between the Department of Defence and the university sector. I think that's really being felt across the sector, and it's a terrific way to work. Thank you. To introduce our fellows who will be presenting this morning, the presentations will be facilitated by two council members, Professor Margaret Shiel and Professor Ian Wright. Margaret Shiel is a distinguished chemist and has made a significant contribution to mass spectrometry, I even know how to say that, in Australia. She was made a professor in chemistry in 2000, being the first woman to be a professor in chemistry in Australia. Margaret's also an influential leader in the scientific and university sector, playing a pivotal role in national science policy development and an avid supporter of early and mid-career researchers and women and girls in science. Many of you will have seen Margaret's outstanding work in chairing the review of the Australian Research Council, which has led to absolutely terrific recommendations being implemented. Thank you, Margaret, for that. Ian Wright is a plant ecologist and applied principles of economics to the study of plant evolution. If you're a student, you will have seen Ian's work on a worldwide leaf economic spectrum, which is now a standard in scientific textbooks. To introduce our first speaker, I'll hand over to Margaret. Thank you.
Thank you very much, Anna Maria, and I too am pleased to have the opportunity to be here and to introduce this outstanding group of presenters and new fellows. So our first presenter is Professor Nerilie Abram. Nerilie Abram is a leading paleo and climate scientist who's made outstanding contributions to our understanding of how Earth's climate system behaved over the last millennium. Her multidisciplinary approaches have also brought critical perspectives to modern-day human-induced climate change, including bushfire, drought, and the onset of anthropogenic warming. Please welcome Professor Abram.
Good morning. It is such a great honour to be elected as a Fellow of the Academy and to be here today to be able to tell you about the work that my teams and I do in bringing perspectives to understanding climate change. Maybe if I can progress. There we go. So this is where I want to start the story today. Looking at this record of global temperature change over the last 170 years. And what we can say from this now is that the human influence on our climate is now unequivocal. That's now a statement of scientific fact that's agreed by every country in the world through the most recent reports of the Intergovernmental Panel on Climate Change. As a paleoclimate scientist, when I look at a record like this, I want to know what happened before. Is this the full picture of our climate? Oh, we're going the wrong way. Okay, great. So the way that we do this is to find ways that we can use the natural archives that are preserved in the Earth system, like the layers of ancient snowfall over Antarctica, or the growth of the skeletons of corals in our tropical oceans. So my team and I go to different places to collect these records and build these natural perspectives on past climate. And we also build the open access databases that bring together all of this information from around the world. And what that does, through bringing all of this information together, is enables this really unique perspective on the recent human-caused climate warming. And that we can see that the speed at which the climate is warming and the level at which it has warmed to is far outside anything that we expect from natural variability over the last 2,000 years. But we can go further than that global perspective, because climate warming isn't developing in the same way everywhere around the world. And when we do that, what we find is that the earliest signs of this human-caused climate warming actually developed as early as the 1830s over the Northern Hemisphere continents and the tropical oceans. And so that observational record that we have doesn't give us the full picture of human-caused climate warming. But that's also important because it tells us that the climate system is incredibly sensitive to even small increases in carbon dioxide levels in the atmosphere. So the green curve here is showing the changing levels of carbon dioxide in our atmosphere, and what we see is that as soon as we saw carbon dioxide levels rising outside of their level of natural variability of the last 2,000 years, we saw that detectable sign of warming being caused in our climate. So that perspective is also very important when we think about the challenge ahead of us in terms of limiting climate warming and stabilising our climate system. Unfortunately, we have missed the opportunity to limit warming to 1.5 degrees. It is now physically impossible to reduce emissions at the rate that would be required to limit warming to that level. And so that tells us that we have an enormous challenge ahead of us in terms of the climate risks that we're going to face. Now, those climate risks are a combination of that warming of the climate, but also the natural variability that leads to the extreme events that cause the most harm to people and the environment. As an example, 2019 was a positive Indian Ocean dipole event, and this was part of our natural variability that contributed to 2019 being Australia's hottest and driest year on record. And when we look to the observational record and we look at the ocean temperatures off the coast of Java and Sumatra, which are the core of activity for the Indian Ocean dipole, we see that 2019 was the strongest event that we've ever recorded in our observational record. But our observational records are short, and we can use corals that we collect from the tropical oceans in this area off the coast of Java and Sumatra to be able to push that observational record back by more than 100 years. And we can also use fossil corals like this that we see thrown up around coastlines to be able to reconstruct windows even further back in time. And when we do that, we find these same sorts of events in the past, but what we can see is that it is possible, even in a climate system without human-caused climate change, to have positive Indian Ocean dipole events that are far stronger than what we observed in 2019. And so events like this and the information that we get from past climate records allow us to glimpse climate events that are unimaginable if we're only looking at our observational record. Australia's tinderbox drought was an intense 3-year dry spell in southeast Australia. 2019 was the last year of that drought. And when we first started looking at this drought event, before the term tinderbox drought had been coined, One of the questions that we were asking was, is this just a bad luck drought to have 3 years in a row where rainfall was so far below what we would normally expect? And what we can do is to take everything that we know from the observational record of Australian rainfall, everything that we know about ocean temperature variability around Australia, and through linear inverse models, be able to look at what's the likelihood that we would have 3 years in a row of conditions like this. And what we find is that the tinderbox drought was unforeseeable based on what we knew from our observational record. And so that really sort of tells us that we need to be thinking beyond what we can see just in our observations, and this wasn't just a bad luck drought. Our observational record is particularly challenging when we're talking about something like drought, where our observations since 1900 only give us a few examples to actually base our understanding on. And so we can use climate model simulations of the last millennium to go a lot further back in time and to have multiple realizations of climate variability. And when we do that, what we find is that, again, even without human-caused climate change, it is very possible in Australia to have droughts that don't break for more than 20 years. So that's something that is quite unimaginable compared to the droughts that we've lived through since the 1900s, and adds an added sense of urgency about how do we prepare Australia for extremes like this, particularly in a changing climate. So the climate change that we see now and the climate variability is not the same as what it was 100 years ago. So human-caused climate change is not just warming the climate, it's also changing the way that our climate variability works. So if we go back to the Indian Ocean dipole as an example of this, and we use our coral records to look at how frequently those positive events happened in the past, how frequently they happen in our observational record, and how frequently they happen in future climate simulations, and we bring all of those different lines of evidence together, we start to build a coherent picture about our climate and how the Indian Ocean dipole is changing. And what we can see is that because of human-caused climate change, we're actually making it more likely that we have these positive Indian Ocean dipole events. And we would expect that in the future, these will become an increasing component of our year-to-year climate variability. And it's not just in the Indian Ocean where we see this phenomenon. If we go and we look at what's happening in the Pacific Ocean to the El Nino Southern Oscillation, we also see this same example when we go back, again using coral records from the past, where we can see that the frequency of Central Pacific type El Nino events is becoming more frequent. Those are the type of events that are most significant for Australia's rainfall. And then if we go to the Southern Ocean and we look at how the storm-bearing winds around the Southern Ocean are changing through a process known as the Southern Annular Mode, we can also see these these recent changes that are pushing that system outside of the natural variability that it's operated in over the last 1,000 years. Now, all of those changes in different ways adding to the risk of drought and fire that we'll face in Australia. That was a very quick tour of paleoclimate information and the perspectives that it brings to human-caused climate change. But the takeaway here is that we're going to need to prepare for future climate extremes that are far beyond anything that we've experienced in recent history. And paleoclimate evidence is one of the tools that we can use to be able to imagine what those climate extremes will look like and to be able to prepare for them in the future. And just to wrap up, I'd like to acknowledge the wonderful people that I've worked with through my career. I've been very lucky that my career has taken me to amazing places, but it's always the people that I work with who are the really memorable parts of those experiences. I'd also like to thank my family, and particularly my husband, who has made it possible for me to be able to follow this career, including being away from home for long periods of time. And a thank you to my nominator, Matt England, for his endless support over the years. Thank you.
Thank you very much, Nerilie. That was a really enlightening presentation. We have time for some questions, if I've got questions from the audience. And there's also questions online if people want to feed them to us. But I see Frances has her hand up. Thank you.
Thank you. That was enlightening. I know that we're also a country of flooding rains, so drought is kind of the opposite of that, but did you also look at the frequency of flooding?
Yes, so we have been looking at that, and particularly even in terms of drought, one of the changes in how we think about drought is not just that it's a period without rain, but it's a period without that drought-breaking heavy rain, and that's what we really need to keep Australia out of drought. And so we do look at that, and we're looking at that both in terms of the large-scale processes, so how frequent are La Nina events going to be in the future, but also looking down to the synoptic scale. What are the weather patterns that we need to set up those drought-breaking rain events? Because in Australia, when we have even, if we look at last year's El Nino as an example, we didn't have particularly dry conditions, and that was just because of one or two extreme rainfall events that fell in November, and were able to mean that we didn't actually shift into drought. So yes, that drought-breaking rainfall and heavy rainfall is a really important part of the picture as well.
And Nerilie, that's related also to the ocean temperature, right?
Yes.
Yeah. So, question. I had one. You know the curve you showed with the CO2 going up in 80, so that coincided with the Industrial Revolution. How much of it is from burning what would have been coal then, and how much is it sort of the land clearing? Do we know that?
We do know that. And roundabout at the moment, it's about 90% of our emissions are from fossil fuel use. And so when we're thinking about what we're going to need to do in terms of decarbonising, it really places emphasis on needing to reduce fossil fuels. We can't solve this problem without tackling that sort of largest part of the problem.
Great. Thank you, Nerilie, and please join with me in congratulating. Thank you. And our next speaker is Andrew Blakers, who has an impossibly short intro here for a very long list of accomplishments that I'm aware of. He's made major contributions to the advancement of solar energy as a key to decarbonising the global economy, and I think we're all beneficiaries of that. And he's been incredibly important and prominent in the analysis of renewable energy systems and the development of the global atlas of pumped hydro energy storage. So please welcome Andrew.
I'm going to talk about the fastest energy change in history. So I could give you a very nitty-gritty, lots of scientific diagrams of solar cells, but I'm going to try and make it quite visual. Solar energy won the global energy race. Hands down, game over, solar energy won. So Nerilie's talk is very apt. We've got a major problem. We also have a fantastic forever solution. So solar deployment around the world is doubling every 3 years. Wind is doubling every 6 years. And everything else together is basically static and will start to fall quite soon. Nuclear reactors have been talked about a lot. We need about 400 gigawatts of solar and wind to completely decarbonise Australia. And we could do it also with 120 full-size, gigawatt-size nuclear reactors. Plus a lot of storage for load following for both nuclear and solar and wind, because nuclear runs 24/7 dead flat. Demand goes up and down. So I know what I would prefer. I like my own private nuclear reactor, 150 million kilometres away in the sky. So complete decarbonisation of the world requires about 100 billion solar panels. This is after we electrify everything, transport, heating and industry. And that translates to about 40 square metres of solar panel per person, which is a very small fraction of the area of land required to feed you. So the area of land required for solar panels is absolutely tiny in terms of land alienation. It can go in arid areas, it can go on rooftops. Anyone who doesn't have a solar rooftop, if they've got a sunny roof, is simply wasting money, because this is the cheapest energy you will ever get, 5 cents per kilowatt hour, is the cost of harvesting solar energy from your own rooftop. And as our rooftop solar goes up and up, the grid is remaining stable. Agri-solar is obviously very important, combining sheep in particular with solar panels. The sheep benefit both from shade and shelter from the wind, and the output of the land actually goes up, not down, and the farmer gets a double cash crop, one from hosting the solar farm, the second from hosting the sheep. For our tropical neighbours, in particular Nigeria and Indonesia, there is a mind-bogglingly large opportunity for placement of offshore floating solar panels. It just so happens that tropical storms, which are the black lines, do not go to the equator. They are either side of the equator. And Nigeria will be number 3 for population in 2050. Indonesia will be number 5. Together, they could harvest 35 times current global generation of electricity from calm tropical areas that never see large waves nor strong winds. So Indonesia does not need to chop down any trees to get unlimited energy from floating solar panels. Australia is sitting in number 1 spot for per capita solar generation. The graph you see here is all leading countries. Green is wind, yellow is solar. We're number 4 for combined solar and wind generation. And we need to increase our deployment rate of solar and wind, but it's very clear that Australia is the global pathfinder. All the other leading countries are in Europe and share electricity across national boundaries, which makes it much easier to balance variable solar and wind. We have to go it alone, and the upshot is we're finding it remarkably straightforward to go rapidly to high levels of solar and wind. This is our trajectory. Black is fossil fuels, blue is hydro, which is not changing at all, and green is rapidly growing solar plus wind. And you can see from 2017 down to 23, fossil fuels have been shrinking as a proportion of generation, and they'll go down to 18% under the government policy, and solar and wind will rise to 75% by 2030, plus the 7% hydro makes 82% target. And provided there's not a change of policy after the next election, this is extremely likely to be realised because of the government's policies of various kinds. Balancing solar and wind is straightforward. Spread the solar panels and wind turbines out over large areas to avoid local weather fluctuations, and storage. Batteries and pumped hydro. So Snow 2.0 is the flagship storage opportunity in Australia. It's equivalent to about 5 million electric vehicle batteries. It's bigger than all the utility batteries in the whole world put together. And the cost at $34 per kilowatt hour, the capital cost, is 12 times cheaper than batteries for overnight storage. So batteries and pumped hydro together solve energy storage. So switching gears, I was going to be an astronomer when I was growing up, but then I took up bushwalking and went to a lot of very nice places, and realised that the physics and maths I had done at ANU was better employed in doing something about climate change, because it was quite obvious as a physicist back in the 70s that climate change was going to be a major problem. Now, nothing mysterious about the physics of CO2. And the PERC solar cell, which is something that I was involved with, is one of the major accomplishments of my career, and I think the other is pumped hydro energy storage. There's also some others, but I'll talk about the PERC solar cell and the pumped hydro energy storage components. So PERC solar cells, an Australian invention at the University of New South Wales in the 1980s and 90s, $0.25 trillion in global PERC solar panel sales to date. It's mitigating about 3% of global emissions by displacing coal generation, and I had the very great privilege of going off to meet the King in 2023, and that was a huge amount of fun with my 3 colleagues, Martin Green, Zhenhua Zhao and Wang, as recipient of the Queen Elizabeth Prize for Engineering. Storage for large amounts of pumped hydro, for large amounts of solar and wind is a solved problem. The global atlas that my team at ANU has developed contains 0.8 million sites with 86 million gigawatt hours of potential storage. That's equivalent to about 1 trillion EV batteries. So we're absolutely spoiled for choice. And if you go to any one of the 800,000 sites in our global atlas, Australia's got 5,000 of them, you'll see something that looks like this. This is a schematic of one of the sites, an upper reservoir at the top, a lower reservoir at the bottom. This is a 1,500 gigawatt hour site near Lithgow. Australia would need just one of these to completely decarbonise itself. And not one of the 800,000 sites involves a new dam on a river. So Australia's got about 300,000 times more sites than it would ever need. Tiny areas of land per person, about 4 square metres to completely decarbonise Australia. That's 1/10 of the area of solar panel and a very small fraction of the area required for agriculture. And tiny volumes of water, 4 litres per person per day to replace evaporation and to provide the initial fill. And that's about half a minute of your morning shower. So there's a lot of nonsense talked about renewables. Wind turbines and solar panels are filth that's all over the countryside, according to a certain politician called Mr. Joyce. Obviously, he likes coal mines better, apparently. And waste, all the solar panel waste is going to drown us in solar panel glass, etc. Well, when you work it out, when we're fully decarbonised, the waste will be about 18 kilograms of glass per person. And that will be saving 18,000 kilograms per person per year of carbon dioxide. And there's a similar 1,000 to 1 ratio for wind turbines in terms of waste versus CO2 avoided. There's lots of unreliable, non-peer-reviewed research out there, such as the Institute of Public Affairs, claiming that 1/3 of Australia's prime agricultural farmland will be destroyed by moving to solar and wind. The correct number is 1,200 square kilometres. That's about 45 square metres per person, including the solar, the wind, the transmission and the storage, compared with 4.2 million square kilometres devoted to agriculture. We don't need to choose between eating and getting lots of energy. Remarkably, some people object to their neighbours in putting solar panels on their farms. You can't hear it, see it, smell it, touch it or taste it, but it just ain't right. My view is it's none of anybody else's business except the farmer involved. One of the nice things about solar is I can go to lots of nice places and pretend that I'm working, like Kutachita or Lake Talbingo, which is the lower reservoir for Snowy 2.0, or a place up in the Snowy Mountains called Snowy Vale, or go out to Montague Island, Lighthouse, or go and look at solar sheep, where agriculture and solar works well together, or go to Lord Howe Island and look at the solar panels there. And that's it. And if you take a picture of that QR code, you'll be able to go to our Global Pumped Hydro Atlas. Thank you.
Thank you, Andrew. That was equally enlightening and encouraging, actually. Have we got questions for Andrew? Yeah, one in the front and then Tanya. So I'll go here first and then Tanya. We hear the waste argument a lot in Queensland about the number of...
Thank you very much, Andrew. It was a fantastic lecture. I have to ask the $64 million question then, after all of this. Why does the Australian Coalition persist with promoting fossil fuels?
It's totally mad. All of the solar farms, all of the wind farms, all of the pumped hydro, all of the transmission will be in rural areas, and it involves hundreds of billions of dollars of expenditure. It is mind-boggling to me why they don't seize this. I mean, when a developer of a solar farm or a wind farm goes to see their local member and says, "Do you mind if I spend $1 billion in your electorate?" Normally, the local member is all over the consortium, but apparently they don't want $1 billion in their electorates. It's just very strange. I don't understand politics. Technology's easy.
Tanya, I think.
Thank you, Andrew, for a great talk and for your work. A science question. Why do tropical storms not sit near the equator?
I think the previous speaker can probably answer that better than me.
Matthew, yeah, that was news to me too, actually. Nerilie? Oh, Matthew.
Again, there's probably other people in the room better placed to answer that, but I believe it's to do with the rotation of the Earth and you have a low Coriolis effect close to the equator.
Okay, I'm only supposed to take 2 questions, but given, I'll take one more at the back, just in front of Matthew. Yeah, sorry.
So I'm curious. I mean, you very convincingly demonstrated that nuclear makes no sense in Australia. Are there places in the world where there is a case for nuclear, or is there no case for it anywhere in the world?
There's no case anywhere. 3/4 of the population lives in the Sun Belt, which is within 35 degrees of latitude of the equator. There's 1 billion wealthy people who live north of 40 degrees in Europe, North America, and Japan, northern China. And for them, they've got mind-bogglingly good wind. So the Baltic Sea, the North Sea, Northeast USA, and the Sea of Japan have vast offshore wind reserves, excellent wind. So everyone's got either solar or wind or both. Why would you go to something that costs 2, 3, 4 times as expensive?
I'm going to get into trouble, Bob, I think. But you probably trump me if you want to ask a question.
Just a real dumb question. How does pumped hydro work?
During a sunny, windy day, you pump water from the lower to the upper reservoir, and then in the middle of the night, the water comes back down through the turbine. The water goes up, same water in an off-river pumped hydro system, the same water goes up and down for 100 years, just up, down, every day.
I'm going to call it quits there. I can see, Andrew, that you're going to have lots of questions at morning tea, and I'm going to pass over to Ian for our next speaker.
Thanks, Margaret. So, good morning. I'm pleased to introduce our next speaker, Rachelle Buchbinder. Rachelle is a rheumatologist and clinical epidemiologist, internationally recognised for her work on musculoskeletal health, including evaluation of a mass media campaign that successfully shifted misconceptions about back pain. She's led over 20 musculoskeletal trials that have challenged the value of accepted treatments, changed paradigms about placebo surgical trials, and implemented strategies to improve care. Please welcome Professor Rachelle Buchbinder.
Thank you very much. I feel greatly honoured to be in this room and to be part of the Academy. I want to, before I forget, thank NH and MRC, who have been my prime funder over the years. I'd like to thank Adele Green, who suggested me to Paul Hodges, who nominated me, and my mentor, Claire Bombardier from University of Toronto, where after my disastrous start to my science career, as you saw yesterday, I did a Masters of Clinical Epidemiology, which basically changed my career trajectory. So I'm going to talk about a few things that I've done over my career, the public health messaging, trials to establish the true benefits of treatment, optimising care, and in particular reducing low-value care, and more recently trying to reduce high-carbon low-value care. Raising public awareness about the problem of too much medicine, and then my collaborations and partnerships. So those of you from Victoria hopefully remember the Back Pain Don't Take It Lying Down campaign at the end of the 1990s, which was instituted because costs for back pain had tripled over a decade in workers' compensation. It was done without any science. The Director of Public Affairs thought it would be a good idea because she'd seen ads for Sun Smart and seatbelts, so she just decided she'd do this campaign, and we were lucky enough to convince her that it needed to be evaluated. It's focused on very simple messages: staying active, not resting for prolonged periods, remaining at work, and X-rays are unnecessary. It was primarily television ads, which was fortunate at that time, and they were aired during Victorian things like football grand finals. So a lot of the population saw the ads, and it had actors such as Conor Friderer. It had famous people like Merv Hughes, and there was even other cricketers that you could see in the pictures, and it had experts. And other things like the compensable guidelines that doctors all received, probably thrown in the bin, and the back book, which was what the campaign was based on, was translated into 16 languages. We found that it dramatically improved population beliefs in Victoria. We did a quasi-experimental control before-after study with New South Wales as a control state, not eliminating, but excluding people from the border. And this slide shows that the back beliefs questionnaire dramatically improved beliefs in Victoria over the duration of the campaign, indicated by the red oblongs at the bottom. And after the end of 3 years, the government changed in Victoria, and so there have been no further ads, even though originally we were hoping to have top-up ads every year. The campaign, even 5 years after the end of the campaign, we evaluated the beliefs again, and there was still a significant difference, but you can see there's been some decay in Victoria over time. I wanted to show this slide because it shows quantile plots that show that mass media campaigns are very effective. At baseline, you can see here, this is back beliefs, and the other graph is fear avoidance. At baseline, Victorian beliefs and New South Wales beliefs are exactly the same, irrespective of whether you had poor beliefs or better beliefs. And over the time of the surveys, you can see that on average, we moved the middle people first in their beliefs. And then by the fourth survey, the harder people, the people with poorer beliefs, they eventually move as well. So mass media is a very effective way of moving the whole population of beliefs, irrespective of where you start from. And it can, if you can do it well, you can reach people that don't see the ads, people that are hard to reach, people that don't even see the ads. They'll all move over time. And similarly here, they reduce their fear avoidance of moving. It also improved doctors' knowledge, attitudes and stated management of back pain. So compared to New South Wales, doctors after the campaign were much more likely to know that you didn't need to prescribe bed rest, you didn't need to do imaging, patients could remain at work. And it also, we found in their stated management that they would manage people better than in New South Wales. There was only one group that didn't change as a result of the campaign, and I usually ask the audience to nominate who they might be. And they're doctors with a special interest in back pain. And they did not change as a result of the campaign. There was no change over time and no change between states. Interestingly, they also found that guidelines would not be helpful in their practice. So this started me on a journey of looking at low-value care and what are the reasons that people that are supposed to be experts actually manage people much poorer. And my take-home from this slide is if you've got back pain, don't go and see someone who professes to be an expert. It also reduced back pain claims. It reduced the duration of the claims, and it significantly reduced both the medical costs and the overall costs. It's been replicated now in 9 countries around the world, most recently France, with similar results in improving population beliefs, but no one in Australia's trying to do this again, and probably it wouldn't work now because we watch television in a different way. The second thing is trials. So I did this trial of vertebroplasty, which is a bone cement that you inject into fractures in the spine. It had been used for over a decade. Not even a single trial had been done. They're all observational studies. And much to our surprise at the time, we found absolutely no benefit. And there are significant harms, and the harms that are still being published, you can die. The piece of cement can break off and go into your heart and perforate your heart. It can cause pulmonary emboli, it can cause paralysis. And this treatment is still being used in some parts of the world. So it went from something that was called the Lazarus effect that was mentioned yesterday by Georgina Long, a treatment that enables the bedbound to walk again, to something that's the poster child for systemic failure of performing appropriate evaluation before we give these procedures to our patients. And in fact, during the trial, we saw the Lazarus effect in people who had placebo. So a patient who flew down on the air ambulance, couldn't move, drove himself home, and he had placebo. So these are some of the things that I've done. What I want to show you is the bigger list of things that we should stop doing. There's only a small number of trials that have actually shown a benefit. And these are some of the treatments that we're still investigating. So things like arthroscopy for knee arthritis, platelet-rich plasma injections that are very lucrative for the person doing the procedure but provides no benefit. Medical cannabis for pain. 61% of Australians are being prescribed cannabis for chronic pain. It doesn't work. So to be more optimistic, we've also been working with the government and others to try and improve care. And this was a trial that we did in collaboration with the federal government, trying to reduce low-value musculoskeletal imaging among high requesters in general practice across Australia. It was a cluster factorial 2x2 design. We had over 3,000 GPs who fitted into this category. A fifth of them got no intervention, and then they got either a standard letter where they had their use compared to their peers and an enhanced display, and it was either delivered once or twice. Unfortunately, it was done during COVID, but what we were able to demonstrate was even after 6 months, there were 47,000 fewer scans done. And this equates to about $7 million, but we're not allowed to talk about the money because this was a quality improvement exercise. We've just done another trial looking at funny pathology tests that GPs do, and I can't show you the results, but it's even bigger improvement. So finally, we've developed collaborations. So we developed the Australia-New Zealand Musculoskeletal Clinical Trial Network, established in 2015. We now have over 440 members, and we've been lucky enough to have 2 CREs. We've now included basic science into our group. We're building a lot of early career capacity, and we're also doing living guidelines for rheumatology, currently inflammatory arthritis in both adults and children, and we're also doing e-learning courses. Finally, we've developed the Wiser Healthcare Collaboration. This was formed from a program grant, and we're trying to reduce overdiagnosis and overtreatment or too much medicine, and more recently, trying to also make healthcare carbon neutral. The healthcare is responsible for 7% of the carbon footprint in Australia. And this is our book that I wrote with Ian Harris, which outlines the problems of too much medicine around the Hippocratic Oath, which, if you look at the Hippocratic Oath, most of those issues are still a big problem today, things like lack of science literacy in particular. And we were lucky enough to write the book in Bellagio, and all of you in this room would be able to apply to the Bellagio Foundation to get a writing residency.
I'd also like to encourage early career researchers, mid-career researchers also, that you're very welcome to ask questions. It's not just for the learned academics down the front. So anyway, we have a question up the back here.
Beautiful talk. Thank you very much. I noticed you listed the Cochrane collaboration on the first slide, but you didn't mention it. How do you fit in with Cochrane?
So I'm the coordinating editor of Cochrane Musculoskeletal, which now includes back and neck, since 2015. And I can actually announce since yesterday that we've now got an international thematic group that also includes pain. I've done probably 150 systematic reviews over my lifetime and trained numerous students. We run a systematic review course at Monash, but also workshops all over the world. And I think clinicians all need to do something like that, one systematic review, and they will understand how to read a paper and understand how much bad research is being published as well.
Thanks for a very interesting talk. I'm curious to know, for your first controversial treatment you mentioned, whose name I can't recall now, vertebro something or other.
Vertebroplasty.
The injection one, yeah. How effective was the placebo compared to no treatment at all? And how do you even pretend you're giving an injection in that context?
So the placebo, so we we know when you give vertebroplasty, so we sedate people, and so they're asleep. But the two things that they remember are the cement, which is a really noxious smell, and they can remember tapping on their back. So what we did was we have a high fidelity placebo, is that we did everything except inject the cement. So we actually did a small cut in the back, we inserted the needle, we took out the sharp needle at the bone edge, but we tapped on the bone so they could remember the tapping, and then we opened up this expensive cement in the theatre so they could smell it. And the placebo effect was immense. There have now been 4 other placebo-controlled trials that have shown the same thing. But I'm not kidding. The placebo effect was, I mean, what you've got to remember is vertebral fractures actually get better quickly no matter what you do. And sometimes patients said they'd go in the trial, but by the time we organised it, they were actually better. So we already got a hint that in fact it's just the natural history that we're seeing, because many people get better very quickly. And placebo did just as well. If you go on CBS News, you'll see a lovely nun. There was a trial at the Mayo Clinic, and the nun was in the placebo group, and she just describes her experience beautifully about, I was so shocked, I had the placebo, but I was so much better. It was amazing. So that was really cool.
Wonderful. Thank you, Rachelle. Over to you, Margaret.
Thank you, Rachelle, and thank you, Ian. Our next presenter is Kylie Catchpole. She is a leader in research in the field of solar energy, and her pioneering work on the mechanisms of nanoscale interaction between light and semiconductors established new approaches to improve light absorption in solar cells and to therefore lead to the development of more efficient solar cells and high efficiency hydrogen generation. So, Kylie.
Thanks very much. It's a great honour to be here. I'm going to be talking about energy and climate, reasons for optimism. And you've heard from Andrew earlier a bunch of reasons for optimism. I want to add a few more to those. And this, I think, is the biggest reason for optimism, is that renewable energy can turn emissions around. So this is a graph from the International Energy Agency World Energy Outlook from last year, and it shows you that by 2030, they're expecting, under the stated policy scenario, this is the STEPS scenario, they're expecting emissions to be turning around by 2030, and this is mostly due to solar energy and wind energy. So they've produced a bunch of different scenarios. The stated policies scenario I've shown before, that's the most conservative scenario. The other scenarios that they've looked at are the announced pledges scenario and a net zero emissions scenario. And in all of those scenarios, solar is the dominant future electricity technology from about the 2030s. And the second contributor is wind. So renewable energy will be the dominant future electricity technology from about the 2030s under any of these scenarios. So we're at the beginning of a major technological transformation, the biggest change in the way we use energy since the Industrial Revolution. So it's interesting to look back and have a look at a few lessons from history of previous technological transformations of motor cars and telecommunications and electricity, and see what we can learn from what happened. The first thing that you learn is that radical change is indeed possible. So it shows you New York in 1900. At the Easter parade, there was one motor vehicle and the rest were horse-drawn carriages. You can see by 1913, there was one horse and the rest were motor vehicles. So radical change is indeed possible. It does happen. The other thing that you learn is that infrastructure change does take time, and we can see this from the history of the internet over the past 20 years or so. In 1995, we had dial-up internet, and it would take you a few seconds for a web page to load. And the reason that we now have fast streaming video is that we had infrastructure change. We had all these broadband cables that were laid, but that required digging up trenches, and that just does take time. And so with electrification, we will require more transmission, and so that's a lot of putting up poles and wires. So all of that will take some time, but it can happen. Another thing that you can learn is that new capacity actually creates new possibilities. And this is one of the first ever electrical appliances. When they first installed electricity in people's homes, you had lights and wires. You didn't have the idea that you could actually plug something in. So this was a new concept, that you could actually have electrical plugs and plug something in. And this is the first electrical toaster. So similarly, we will have lots of cheap electricity in the daytime. So this is a new capacity and new possibility, and we'll think of interesting things to do with it. Another lesson is that we're likely to want a lot more capacity than we think. And there's a real important lesson from the NBN here, because when we first had internet, we were excited if we could load a web page, and nobody was thinking that they would be wanting to stream movies. At that time, it just wasn't something that was imagined. And so we thought, oh, well, maybe a slow internet will be fine. No, but we're glad that we want more and more, and we all always want more and more. Now, similarly, for energy, at the moment we're planning to electrify the things that we currently use, but we're likely to want a lot more capacity than we think. And we can see this in all the opportunities to decarbonise our emissions. So this is the sources of emissions globally. You can see that 73% of emissions globally are coming from energy. So decarbonising energy is the main game. That's the main thing that we need to do. Using solar, at the moment, it's cheaper to decarbonise energy use in buildings through electricity and heat, and also in road transport through electric vehicles. So those parts we will already decarbonise quickly just because it's cheaper to do so. But there's a lot of other opportunities you can see for energy use in industry, for energy use for producing chemicals, for producing aviation fuel, for producing shipping fuel. All of these, there's lots of more opportunities, and so we're going to want more capacity than we think at the moment, very likely. So my work has been in reducing the cost of solar further for all these wide range of applications that we're going to want lots of cheap solar energy for. In particular, recently I've been working on perovskite solar cells, which is a new material. You can put them on top of a standard solar cell. They have a higher semiconductor band gap, so they're better at absorbing the blue photons. They will give you a higher voltage for those blue photons, and then the red photons can pass through and can be used in your standard silicon solar cell. So doing that, we've made some of the most efficient perovskite solar cells, overcoming previously unrecognised losses in those cells, and we've also made some of the most efficient perovskite silicon tandem cells with those two cells stacked on top of each other, and these have the potential to reduce the cost of electricity from solar further. I'd like to finish by talking about one more reason for optimism. I've said that optimism is justified, but optimism is also generative. This is Christiana Figueres, who was lead negotiator for the 2015 Paris Climate Agreement. And when she took on the job in about 2011, she was asked if she thought if it was possible to reach a global climate agreement. And she said, "Not in my lifetime." And she realised once she'd said that if she didn't believe it was possible, then in fact it was not possible. So she recognised that her first task was to actually convince other people that it was possible. And so optimism is generative. It allows things to happen that would not be able to happen otherwise. So we can teach this, and I think we ought to teach this to young people. I teach a course at ANU called Optimism in Agency and in Times of Change, where I teach students about the different ways that they can contribute to global challenges, how they can combine their strengths and their interests to actually make a positive difference in the world. So, we've seen that projections from the International Energy Agency show that renewable energy will turn emissions around. Solar will be the dominant source of electricity under any reasonable scenario. It does require infrastructure change, and there is an important lesson from broadband here, and optimism is both justified and generative. Thank you.
Thank you, Kylie, and it's wonderful to have that optimism. Questions? There's one at the back.
Thanks for a really interesting talk. This might be a pipe dream, but I'm just wondering, you mentioned the poles and wires for transmission. Is there anyone working on ideas of wireless transmission?
I guess for short distances and small amounts of electricity, yes, you can do that. I mean, people have sometimes thought of, beaming power down from space. So there's lots of possibilities, but the cheapest thing is to use the poles and wires, and that'll be the quickest thing as well.
I've got a question up the back, and then Francis.
Hello. Hi, Kylie. Beautiful talk. I'm curious about the optimism course. How were the students transformed, and did you see students who were highly skeptical and would never change? I would like to hear, some of the stories from the course.
Okay, thanks, Anita. So just sort of examples of some of the things that students have done. Some of them have made mobile apps that show you the emissions from the different mode of transport that you choose. So you might look at Google Maps and say, oh, there's this much emissions if I go this way, or this much another way. Some of them have made card decks of endangered plants, and by playing this card game, you suddenly learn the names of endangered plants. I know, for example, that the chocolate lily is an endangered Australian plant as a result of playing that card game. The students have said that it's changed what they thought was possible. They didn't. They had spent a lot of their degree often learning about all these problems, and as a result of learning about all these problems, they felt really disempowered, and it was actually impacting their mental health. So just by providing a space for them to say, look, you can do something now, you don't have to wait till later in your career, they found that really empowering, and they've said, I've had students say that they wish everyone could do the course.
I was finding myself wishing my students were doing the course, so the same reaction. Kylie. Francis, sorry.
I think you'll give me an optimistic answer, but the cost of perovskite cells compared to silica must be higher and also involves metals. So do you think the cost will come down as we produce them more, or do you think it'd be just certain uses?
So it's hard to say. Silicon is already cheap, and we're already installing at large scale, and we should continue to do so. As the world's dominant electricity technology, we should also keep trying everything to make it even better and even cheaper. So perovskite is one way to do that. Certainly there is the potential to make it cheaper, and especially by stacking on top so you get the higher efficiency. The main point there is that if you have higher efficiency, you need less land, you need less installation. A lot of the cost is actually the installation. So for example, if you have your panel in your hand, that's only a quarter of the whole cost of the panel on the roof of your house. A lot of it, the 3/4 is actually putting it up there and getting it installed. So if it's more efficient, then you need less of those, so it can be cheaper.
Great. Well, thank you very much, Kylie. That was really a wonderful presentation. And it gives me great pleasure to introduce our next presenter, Professor Mary Garson. I feel like I've followed Mary around the country. She left Wollongong just as I was arriving, and I arrived in Queensland where she went from there. And we heard yesterday some of the history of that. She's a globally recognised expert in the chemistry, biosynthesis and bioactivity of secondary metabolites from marine and terrestrial environments, and best known for her pioneering work of using stable radioactive isotopes to define unusual biosynthetic pathways. So please welcome Mary Garson.
Thank you very much, Margaret. And a link that I have with Margaret is I was the inaugural recipient of the Margaret Shield Leadership Award of RACI several years ago. Thank you very much for the incredible honour of being elected to the Academy. And I'd particularly like to thank President Jagadish, because I remember so clearly the conversation that we had on April the 10th and how generous you were with your time. I was a bit wobbly at my knees when I realised what the conversation was going to be about. In between, during April and May, I felt very much that I must have joined a secret society because we weren't allowed to talk about this to other people. But this week, what has been wonderful is actually discovering that I've joined a scientific family. So thank you very much. Now I'm going to tell you about my research work. So I'm a classically trained organic chemist, and I dived into marine science. I literally came as a neophyte from England to do a 2-year project. I wrote an application for a QE2 fellowship. These days, that fellowship application would be thrown in the bin because I had zero background. I couldn't even scuba dive. I didn't know what a marine sponge looked like. And so the people assessing that grant in 2024 would say she couldn't possibly do this project. I'm extraordinarily grateful to colleagues from Townsville, marine researchers, Australian Institute of Marine Science, who guided me through the early phases of my research. Richard Payne has very kindly actually done an introduction of my presentation because he showed a slide yesterday in which the left-hand side was small natural products. And on the right-hand side, and that was the focus of his research, he was talking about peptides and proteins. So please transfer your attention back to that left-hand side of the screen and where the molecules are elegantly small and exquisite. And in terms of what I do, of course, having once I'd learnt to master scuba diving, and the research is, of course, always done under permits, mostly Queensland, New South Wales. I guess I know more than anybody else about the chemistry of marine animals from the eastern coastline of Australia. And the focus is going to be very much on marine sponges. When I first arrived, I didn't even know what a marine sponge was, let alone how to recognise them underwater. And we're also going to be talking about nudibranchs, which are carnivorous mollusks that eat sponges. And so there is a strong chemical link. And as I described yesterday, the science is really about doing a molecular jigsaw puzzle. Richard described it as Lego. I did jigsaws during COVID, and so for me, this is a jigsaw puzzle, identifying fragments by nuclear magnetic resonance, and then joining them together. The training that I had in England in terms of biosynthesis, thinking about, in that case, it was actually working out the biochemical pathways by which fungi manufacture antibiotics. And so thinking about the small molecular weight precursors and how they're converted chemically into useful products. And the incorporation studies that we've done over many years have often used C14 and C13 materials that are synthesized in my laboratory. So just a couple of signature slides here, and I apologize to the non-chemists. The chemical chicken wire is not relevant here. That's to show that the chemists that there is some serious biosynthetic thinking going on behind the chemistry. If you take a look at the little brown sponge in the top right-hand corner of this picture, which is growing on acroporid corals at Heron Island, it's actually a very dangerous animal. Not only is the surface clean, so it's producing bioactive chemicals that interfere with the settlement and metamorphosis of larvae of other species that might otherwise use it as a substrate. It also kills the coral tissue on which it's growing. And we were able to establish that the source of that biological activity was a group of so-called 3-alkyl piperidine alkaloids. Now, an alkaloid contains nitrogen, but technically speaking, these molecules are actually put together by a so-called polyketide pathway using acetate building blocks, and the chain starter unit is nicotinic acid. So it's an exquisite little example, a simple molecule, but quite a complex biosynthetic story. Underneath, just a single project for one PhD student, The whole PhD was the material that's shown on the slide, and about 4 papers, 30 different compounds, this time polyacetate, polypropionate compounds, and the key motif is the cyclic peroxy motif. And if you think about Richard's talk from yesterday, he mentioned artemisinin, which is a world-famous cyclic peroxide, which is a potent antimalarial. And likewise, our compounds were antimalarials. The biggest change in terms of doing structures in the 40 years that I've been working in the field have been that in addition to thinking about how the compounds are made, we now use computational modelling in our work. And these are 2 of the recent projects in my group where we have used modelling, DFT calculations, thinking about conformer populations to help inform us about the chemical structures. If we look at the single mollusk shown at the top right hand, that was the entire project. One single animal, which is about the size of my little finger joint. The chemical extract was small, but a talented student was able to isolate 21 different compounds from that, and a couple of the structures are shown at the top. If you look at the structure on the right, epoxyagoniolide, the med-chem people in the audience will be saying it had to be biologically active. There's an enal, mycoacceptor, and there's also a reactive epoxy carbonyl. These are motifs that you would expect to confer biological activity. But those 2 functional units are hidden in the middle of the molecule. They're not biologically exposed, and we've not yet been able to identify any biological activity associated with this compound. Plus, of course, we had vanishingly small amounts of it in order to undertake testing. Now I'm going to move very rapidly on to my signature research. The terpene shown at the bottom in the middle, isocyanoclovine, it's the NC functional group picked out in purple, which was the reason why I came to Australia. This particular set of compounds came from a mollusk, Phylidia ocellata, which is one of the most beautiful animals in which I've worked. But let me tell you now about that isocyano research, diisocyanoidosine, which featured in the video that was shown on me yesterday. So back in England, in the middle of winter, there I was reading the marine natural products literature, and I saw this structure, and I went, whoa, where does that come from? This is a really interesting rearranged diterpene, but where does that NC unit come from? And so I came here, and the actual experiments were done on the Great Barrier Reef. If you look at the picture on the left, I'm actually camping out on a pontoon in the middle of the Great Barrier Reef overnight and doing incorporation experiments and proving that inorganic cyanide is the actual source of that isonitrile group. And we still don't know what the biochemical source of the cyanide is. There is, of course, no cyanide naturally in seawater. So I continued on from this early signature research to look at a swag of other functional groups that are shown in the box on the right. But probably the more interesting question was whether these are compounds actually produced by the sponge host or by associated microorganisms. I did some experiments, this is in pre-genomic times, and was able to establish that the terpenes are associated with the sponge host, but we couldn't definitely prove that they were produced by the sponge host rather than microbes. So it was a great pleasure a couple of years ago to read of some research by an American group who took my early studies and have now managed to identify the presence of terpene synthases in the sponge host. So my ideas all those years ago have been shown to be correct. Right, just one final story I want to tell you about. I've been suggesting that marine animals make bioactive compounds for a reason. Life underwater, of course, is a competition for food and space, and also for presenting disease. So many of the compounds are antibacterial. They need to prevent infection from all of those zillions of microbes in the marine environment. And so here's a typical project at the top right, a bright orange and a bright purple sponge, both fleshy, looking like they would be perfect food for fish and crabs, getting really close to each other, but not actually, neither is, I'll just keep slightly away from that evil-looking orange sponge next to me. So these are clearly substrates for experiments, and it highlights the need to actually go and do these observations in the field. Rather than talking about one of our sponge projects, I thought I would finish with a study on some nudibranchs. Nudibranchs eat sponges, and I'm going to show you that here we have a group of 5 different nudibranch species, all chromadorid species, all beautifully coloured, quite distinctive. And the signature chemistry that they get from their preferred sponge diets are the set of molecules shown on the outside of this wheel. If instead you dissect out the rim tissue rather than the gut tissue of the mollusk, so for example, if we look at the Elizabethina, the beautifully blue and yellow mollusk at the top of the slide, if you dissect out the rim tissue, you find a single compound. It's called latrunculin. It's not a terpene. It's a macrolide. It's highly potent. It's a well-known cytotoxin. It's used in cell biological studies. And that chemical is present in the rim tissue of each of these different species, although their gut chemistry is different. Now, because Margaret is here, I guessed correctly that I should show some mass spec imaging. So here's an optical image showing that there are specialized glands inside the rim tissue and that is where the latrunculin is localized. The assays are done, we've done a lot of anti-predator deterrent assays using fish, and also I want to just highlight, as we will be coming up to lunch later on, what I call our red spaghetti assay. If you look at the top left picture, where we incorporate our compound of interest into a spaghetti pellet, which is squid-flavoured, yum, so that the predator, in this case, it's a little common shrimp from the rock pools of Caloundra, and because it has a clear body, you can determine whether the pellet has been digested or not. So what's going on here in terms of the ecology story? We have a similar, highly conspicuous colour pattern, and we have a very strong bioactive chemical signal. And to the ecology people in the audience, they will recognise that this supports what's called a Mullerian mimicry group. It's kind of cooperative mimicry in as much as contact by a predator with any one of this group of 5 different species of mollusks is going to reinforce avoidance behaviour in all of the predators. I have to finish by, again, just telling you about Maritigrella marigarsoni, which means little female sea tiger. And I like to think that these mollusks are all dancing in celebration underwater this week, seeing that they are now actually also cover girls, as well as being incorporated into the literature. And if you don't mind me taking 30 seconds, Margaret, I must share with you our work over many years. I work on behalf of the International Union of Pure and Applied Chemistry, and the Global Women's Breakfast that I created about 15 years ago, we reinvented it in 2019, and now every year about 30,000 participants join in. We're actually operating in over 100 countries. The last event had 77 countries joining in, over 420 events. It's simply about joining young people together in a meaningful conversation to support their professional aspirations. Of course, it started with women chemists, but we welcome men to join in. And because next year is the International Year of Quantum Science and Technology, we would very much like other science groups to join with us. And the theme, because of next year being the quantum year, is accelerating equity in science. So as a result of that, I just simply at this stage would like to express my gratitude to the Academy. I congratulate my fellow class members, the 2024 class members, and thank you very much for your attention.
Thank you very much, Mary. Because you ran a little over time, I'm going to stop the questions and see if we can get back those few minutes. So I'll hand over to Ian for our next presenter. Thank you.
Thanks, Margaret. So our next presenter is Professor Arthur Georges. Arthur is here, some. And Arthur Georges is an ecologist and herpetologist. and an internationally recognised expert on the evolution and ecology of reptile sex determination. His work has revolutionised understanding of how the complex thermal environment of nests dictates sex in reptiles, how reptiles survived past climate changes, and how human activities constrain their ability to respond to future challenges. Thank you, Arthur.
Okay, well, it's an absolute honour and privilege to be admitted to the Academy, and I'm also really grateful for being able to be involved in these 4 days, which have been fantastic. I'd just like to thank Jenny Graves for nominating me, and also the wonderful students and postdoctoral fellows and collaborators who've worked with me in the work that I'm going to present today. And of course, I'm very grateful to my wife and family who have put up with my idiosyncrasies over the years. So basically, I'm going to run through a journey of discovery and try and tantalise you with some of the elements of my research over the years. You would probably all be well aware that there's not a one-to-one correspondence between genotype and phenotype. So basically, the blueprint of life, which is your genotype, is modified during development by environment to amend the ultimate phenotype that arises from that genotype. And even identical twins diverge in their physique, and particularly in their response to or propensity to develop common diseases over time. So the genotype and phenotype is modified by environment. So evolutionary biologists and ecologists call this phenotypic plasticity, and there's some really good examples, classical examples of Daphnia that gets a helmet in the presence of predators, and also leaves change their shape depending on how much light filters down through the canopy. And we're really interested in it as ecologists and environmental biologists because the ecological interactions and natural selection act on the phenotype, not the genotype. And so it's really important for an evolutionary biologist to realise that the phenotype is what natural selection is acting on, the genotype is what inherits the benefits forward. In the medical arena though, or in human health, they tend to call this developmental programming. And the reason they're interested in developmental programming is because insults to the developing embryo can lead to deleterious outcomes later in life. And so it's a really interesting area in medicine. And I think you'd understand that the fundamental underpinning mechanisms are going to be common between these two sort of fairly disparate perspectives on the same issue. I'm interested in a special case of phenotypic plasticity where you have the same genotype but discrete phenotypes, and intermediate states are either unviable or severely fitness compromised. And a good example is honeybees. A honeybee becomes a queen because of what the larva is fed. Another example, wings in the green aphid. So they can be wingless, but they'll develop wings when the population density is increased to the point where food becomes limiting. And of course you've got sex in dragons, where incubation temperature determines the sex of the offspring. I started my work up on the Daly River, working on the pig-nosed turtle, which has temperature-dependent sex determination, and I was working on the eggs of this species and the nesting biology. And the context for this was that the year before, Graham Webb and Peter Whitehead had discovered that this species has temperature-dependent sex determination. And in fact, at above 32 degrees, you get 100% females. Below 32 degrees, you get 100% males when they're incubated at constant temperatures. And so I was keen to look in the field to see what was happening in the natural nests, and I found that the actual boundary between males and females wasn't 32 degrees, it was 1.2 degrees lower at 30.8 degrees. And just sort of harking back to my vignette and connection with Asimov, this is the first Asimov moment. That's funny. You know, why would that be? And this sort of dogged me for months. I know you have to be fairly sort of anal to to have this sort of thing dog you for months, but it dogged me for months. And finally, then you have the second Asimov moment, which is the realisation as to why it might be so. And I had that realisation, and then I translated that into a very precise mathematical model, which I published in Ecologia in 1989. And then you have your next Asimov moment, which is the proof. You have the idea, you have the hypotheses, you get competing hypotheses, and then you move to the stage of doing the experimentation to eliminate those possibilities from consideration and to focus on what is likely to be the explanation. So I moved to the marine turtle to do the experimentation and collected the eggs from en repos. This species of loggerhead turtle has temperature-dependent sex determination as well. So at low temperatures, 100% males, at high temperatures, 100% females. But what I was able to show is that even if you held the temperatures constant at 26 degrees at a male determining temperature, and you increase the variability, the daily variability, which is what happens in natural nests, you increase that variability, you can switch the sex ratio from 100% male to 100% females. And the mathematical model that I published in 1989, I applied it to these data, and the fit was astonishingly good. And this is a good moment for a scientist when your theoretical expectation is borne out by experiment. So what this means is that it greatly expands our knowledge of how organisms can respond to climate change. And in particular, it means that it's not just about warm and cool, hot and cold. It's about more variable or less variable. And so they can seek out more variable sites to place their nests in order to respond to environmental change, such as climate change. And this doesn't just apply to sex in reptiles, it applies to any phenotypic trait that's thermosensitive. So it applies to the spots on the wings of butterflies, for example, which are thermosensitive, and so this modelling will apply equally well to predicting the size of spots on the wings of butterflies, which is really important in terms of predation. So that was really exciting early work. The next step was to ask the question, well, what about species with chromosomal sex? What about species that have sex chromosomes? How do they manage under complex thermal regimes? So the temperatures are going up and down each day, moving through the season. In the pig-nosed turtle, you could have temperatures as low as 18 degrees and as high as 45 degrees, and they're going be male, be male, be male, be male, the regulatory system, or be female, be female, be female. How do they do that? There must be some form of regulatory chaperoning, some mechanism that chaperones those regulatory processes in the face of that high variability in temperature. And so what happens when you push it? And so we moved to the dragon lizard because they've got a low generation time, lots of eggs, and we pushed the system to see whether that chaperoning mechanism would break down. And so, lo and behold, it does. And basically you have a 50-50 sex ratio, as you'd expect for animals that have chromosomal sex determination. 50-50 sex ratio, but when you push the temperatures up, it breaks down and you get ZZ sex reversal. So basically we've got developmental reprogramming of the sexual trajectories by temperature, which is really exciting. And it's very important for us because most people have been working on species that don't have an underlying predisposition to be one sex or the other. Most of them are working on TSD species. We have now a species where there's an underlying genetic predisposition and we can look at how temperature comes in to interfere with it. So the discoveries flowed thick and fast. We've got sex-reversed females are fertile, W chromosomes not needed for female development, sex reversal occurs in the wild, dads make better mums, the sex-reversed animals are bigger, lay more eggs. The transition from GSD to TSD can be very rapid, and populations in the wild are on the verge of shedding their W chromosome. But the big result was that ancient and ubiquitous mechanisms of chromatin modification are involved. And so basically what we found, to our surprise, was that there's thermosensitive intron retention in chromatin modified genes that are the genes that are responsible for the activation and deactivation of other genes, such as the sex-determining genes. And this thermosensitive activation, inactivation using these ancient and ubiquitous mechanisms was a surprise and opened up a number of channels for us to explore. These two students, PhD students, developed this working model and published it in biological reviews, and we're able to see whether we can now switch thermosensitivity off by poking into these various processes using the sort of inhibitors that are applied in human cancer studies, because these same mechanisms are the mechanisms that go awry in human cancer. So there's an array of mechanisms that we can use to interfere with this process and see whether we can actually switch thermosensitivity off. We found that it does manifest in the field in the sense that in some areas they have lost their thermosensitivity. What elements of this process have been modified by natural selection to turn off the thermosensitivity in the hotter areas of the species range? We're working with QMIR Berghoff on these inhibitors. And then I'll finish by saying that it's been a long and windy road. There's a lot of little side branches that delivered some interesting results, some didn't. But we developed unparalleled genomic resources, and this has put Pagona viticeps, the bearded dragon, on the map for a wide range of studies. We've provided the lizards to the Max Planck Institute for Brain Research, so they can use it as a reptilian model. Basically, Andrew Pask is looking at cranial development in the dragon. Patrick Weston and Sarah Whiteley and myself have put in an ARC grant, it's just still under consideration, to look at some of the regulatory pathways in mouse and dragon, where there's commonality. And so we've basically put this species on the map as a species of choice for studies requiring a reptilian model. And I'll leave it there, and thank you very much.
Thank you, Arthur, for a wonderful talk. I'm going to take the privilege of asking the first question. So in your talk yesterday, you spoke about the possibility that climate change will push the sex ratios kind of out of whack. I wonder, I suppose my undergrad understanding of sex ratios is that there's a natural oscillation around, say, a 50% ratio. So is the problem that climate change is pushing it too far, too fast? Or what would be the result?
Well, so these animals have sustained their populations through climate change in the past, and so the difficulty for them is that a 1:1 sex ratio is typically optimal. In marine turtles, if that ratio is pushed up to 90% in favour of females, 10% in males, and so it's demographically putting those populations at risk. And in the past, they would just contract their range and shift their ranges in order to accommodate that. And they can do that now as well. But there's a complication in the sense that when the actual factor that is determining the sex ratio is also involved in differential mortality, that the optimal sex ratio is no longer 1:1. It can be quite substantially different from 1:1. And so some of these species that have a 60-40 sex ratio, that could be the optimum for them because of that interplay between temperature determining mortality and temperature determining the sex ratio. So it's not as dire as it might first seem. Yeah.
Time for one more question.
Thank you for a marvellous presentation of brilliant work. As I'm sure you know, the flat-backed turtle in Western Australia, north of Broome, breeds in the winter, whereas those south of that line are summer breeders. Do some species adjust the time of year at which they breed to try and get optimal temperatures? How might this be controlled, and is this going to be an important mechanism in the future as climate changes?
Yes, it's, they can change where they nest, they can change how they nest, they can change when they nest. The studies that have been done on freshwater turtles in North America have shown that there are limits to their capacity to deal with climate change by those mechanisms. So, like, climate change is occurring so rapidly and it's so substantial that those species do not have the capacity to change when they breed sufficiently to accommodate climate change. There are limits to their ability to do that. So they do have a problem, but there are other dimensions to how they can respond to climate change, which I think my work's bringing out in terms of the complexity of how the thermal environment works and how they can manipulate where and when they lay their nests and how they construct their nests in order to respond to climate change. So they've got a lot more in their arsenal to be able to respond to climate change than we previously thought. But the rapidity of climate change is still likely to be a problem. And the other thing that our work has shown is that it's GSD species with chromosomal sex determination, can also have a problem with climate change because of sex reversal.
Thank you, Arthur. So on to, back to plants. So it gives me great pleasure to welcome Professor Ros Gleadow to the stage. So particular pleasure for me because I've known Ros for many years and she was an inspiration to me to get into research myself. So thank you, Ros. So Roslyn is a world leader in the field of cyanogenesis, the process of cyanide release from stable bioactive compounds in plants in response to herbivory. She has integrated opposing theories of plant defense to demonstrate that these bioactive compounds are intricately involved in nitrogen management, which is the evolutionary driver for the cyanogenesis, not just herbivore resistance. Her work explains why so many crop plants are cyanogenic and helps predict changes in nutritional value of plants in response to environmental challenges. She actively translates her work to impact food security, human and environmental health, and crop adaptation.
Yeah, well, thanks, Ian. I do remember you in second year. And I do remember even convincing you to test your eucalypts in honours for cyanogenesis, and they were positive. It was actually very interesting. So, wow, I never thought I would stand here. So I first saw this building, the Margin Embassy, as we used to call it, in 1961 on a family holiday when it was sitting in a paddock. And of course, I've visited many times with my husband, Andy, who's been a fellow for some time. And I've always enjoyed this conference, but I never really thought that I would be here. So I want to thank the Academy for this honour, and particularly want to thank my nominator, David Day, and all those who supported this. I work on plants that poison you, and there's a lot of plants that make cyanide. We call them cyanogenic. You may be familiar with them. They're apple seeds, that taste of marzipan, apricot kernels, really just whatever they say, don't eat them. They're actually very toxic. And these produce cyanide. There's about 30 species of eucalypts. If you go out into a forest and just select all the species, about 5% of them will be cyanogenic. If you go to crop plants, it's more like 30%. Some people have even put it at 50% are cyanogenic. That can't be accidental. That is a really big difference. And so my interest has been working out why plants make these compounds and how they may have evolved and why there are more in them in crop plants than others. So cyanide is released from stable non-toxic cyanogenic glucosides, and the glucose is broken off by an enzyme. This is, the nitrile is unstable, breaks down to release cyanide, which binds to cytochrome oxidase and will kill whatever aerobic organism it is, and the other side products. And so this is toxic. Within the plant, so the plant doesn't kill itself, of course, they're separated, spatially separated. And it had always been thought that the cyanogenic glucosides were vacuolar, but some work we've been able to do with live Raman spectroscopy would suggest that, in fact, they may be held in non-membrane bound organelles and not in the vacuole obviously quite tricky to get this published back then because no one had really heard of these types of organelles at that time. What happens if humans eat cyanide or animals? Well, on the left you see the picture from the recent drought in Italy, and these cattle are dead from eating forage sorghum. Now, in Australia, forage sorghum is used a lot for feeding cattle. You don't actually have a lot of deaths because in Australia they understand you shouldn't feed them on plants that are young or during drought stress. So this would be avoided, and there is some education going on in Italy about that. In humans, if you eat, for example, cassava or manioc, manioca, wherever you are in the part of the world, it can cause death, of course, but it can cause a disease called konzo, which is a paralysis, or it's a more like a spastic paralysis from eating poorly processed cassava and a monotonous cassava diet. In cassava, about 1 billion people eat this every day, so it's not an insignificant problem. The linamarin, which is the cyanogenic glucoside here, is made in the tips. It is, the leaves are very high as well. The leaves are quite toxic, made into a salad in Indonesia, so watch out for that. Transported into the tuberous roots, and that's where most people have it because it's very high in starch. And this woman here, she's pounding the cassava, and what she's doing, in fact, is bringing the, sorry, this is the reverse of where I should think it would be. She's bringing the cyanogenic glucoside in connection with the beta-glucosidase, add water, some of the cyanide will go into the air. If you can add a step in there and wait for a few hours between doing that grinding and adding the water and cooking the food, you can eliminate the cyanide, essentially. 97% will be removed. People don't always do this. Well, mostly they don't do this, and therefore you can get these diseases. Now, this came to the attention of an Australian working in Mozambique, Julie Cliff, and this was a photo from the very first konzo epidemic where they made the link between the coincidence of drought and this disease and cassava. And so these children have konzo. It can onset very quickly, within 24 hours, and it's permanent. And Howard Bradbury, who was a chemist at the ANU here, he has spent his retirement studying this, and one of the things he found was, that for example, on the left, if you go and sample flour in a Maputo market in Mozambique, it's about 15 to 20 parts per million cyanide. That's about double the WHO recommendation, but it's okay if you're eating a bunch of other things. But in a drought year, it's well over 200 parts per million and therefore very toxic. At a similar sort of time, I'd started doing some experiments on cassava because I started with eucalypts, but I ended up working on these crop plants and found that when we grew them, the well-watered cassava tubers had well over 100 parts per million cyanide, so that in itself was high. But the droughted ones, subject to drought in pot experiments, were much, much more toxic. So as a result of this, I made connections with these others, and we have, in the last year, launched the International Safe Cassava Working Group, which has members from over 50 countries in the world. We are seeking to work with dietitians, plant breeders, neurologists, ways to develop safe cassava, educate about that, and get the message out that there are ways to reduce disease associated with it. Now, konzo is not found everywhere in the world. What is actually more common is neurological effects, such as reduction in IQ, which is quite well documented in different parts of the world. As a eco-plant physiologist, what I've done is really been interested in how climate change affects resources and how they're allocated. So the traditional plant defence theories is that you have a certain amount of resources available to the plant. They'll allocate those resources to the production, to photosynthesis and growth, or to defence, such as compounds and like cyanogenic glucosides or other toxic compounds. So if anything reduces photosynthesis, the plant may still have access to nitrogen and so on, and these will be stored in the toxic compounds. And that sort of makes sense. Likewise, if you have a plant that's either genetically or for some other reason produces less of these secondary metabolites, as they're called, or specialised metabolites, the resources perhaps may be diverted into photosynthesis that will promote growth. So this is really the basic trade-off theory of plant defence. Bit of a spoiler alert here, it's really much more complicated than that, and there's a lot more interactions between these. And this is really what I've been focusing my work on, and I think it's best summarised in this paper I published with John Mullett from Texas A&M a couple of years ago, using molecular methods. So droughted sorghum, as we saw, can be a problem, and a farmer might look out and the only green thing they see is sorghum, but they don't know whether it's going to be toxic or not. Do I put my cattle on it or not? It takes a while to get the tests back. The tests aren't particularly accurate. In Queensland, it is known to use the sacrificial calf method to decide whether it's safe to put the rest of your herd on the crop. But there's got to be a better way. So again, we did similar pot experiments where if the plants are watered, they keep under the 600 parts per million limit for cyanide for cattle, it's safe. But if you drought them, then they can become extremely toxic. And so this would support the plant defence theories. The plants can't grow because they don't have enough water, therefore they're putting it into defence. And we've done quite a bit of work on this. If you drought them very severely, this doesn't happen. And it's like the plant has a mechanism for not storing nitrogen, not making these complex compounds. So it's not just a concentration effect, they actually upregulate biosynthesis of these compounds under drought. And so there is some nuance in this that if a plant is very droughted and therefore unable to recover those tissues or unable to recover from the drought, they don't make these compounds. So it's a bit more complex. So, just to summarise 25 years' work or so, I'm not going to go through this slide. All is to say is that they're very complex interactions. So if you want to predict, is your cassava safe to eat? Is your sorghum safe for your cattle? There's a lot of different things, and it's very, very hard to predict knowing what the environmental variables are. So working with a forage seed company in Queensland, Pack Seeds, we decided what we would do is to knock out the actual production of the cyanogenic glucoside. And at that time, it wasn't possible to transform sorghum, and so we went the mutagenesis route. So the biosynthetic pathway had been worked out by my colleague Budiman, who's a corresponding fellow of the Academy here previously. So there's two cytochrome P450s and a glucosyl transferase that make Durin, which is the cyanogenic glucoside in sorghum. And so we mutagenised 50,000 seed, grew them in the field. If you do this with Arabidopsis, it's a whole different thing doing it with a giant plant. And we tested these with a phenotypic screen, did EMS tilling, and knocked out that enzyme. So and looked for mutants that didn't make cyanogenic glucosides, and then by doing the tilling, the genetic screen, we could work out which ones had a mutagenised enzyme. So we found the total cyanide deficient molecule has a non-functional P450. The adult cyanide deficient molecule has a methylation mutant, it's a regulatory mutant, and many, many others. And so really, if the plants are allocating nitrogen and carbon to Durin, the plants that we've knocked this out on, we now have a nice model. We can have plants that are isogenic because we've done back crosses. And, but what we noticed that is when we knocked out the Durin, instead of the plants being smaller, in fact, in the early stages, very early on, we noticed that they are in fact, instead of being bigger, they're smaller. So in fact, not making these compounds, they actually have reduced growth and reduced vigour. The same thing so what we actually think that is, in fact, the Durin metabolism is entangled with growth. Again, another summary of 25 years worth of work. You can get cyanide itself can be assimilated. We know nitrate is involved directly in growth, but you can also get ammonia released from the remobilisation of nitrogen. At the same time, the turnover of these compounds and the synthesis of these compounds reduce oxidative stress and reduce reactive oxygen species and peroxide in the plant. So we now hypothesise and have good evidence that plants evolve these compounds to manage their nitrogen and to mitigate stress. And part of this has seen this love affair that humans have with toxic plants, that plants have actually, unlike many other toxins, have become more cyanogenic with domestication. Both we've seen this in sorghum and also very likely in cassava. And particularly like to point out my collaborators here, Robert Henry, Bill Moller, and Cecilia Blomstedt, who's the one who's been really the hands-on work in the lab. So in summary, cyanogenic glucosides, they're natural, bioactive compounds that are effective in defence, variably. Defence theory is based on cost benefits. It just is not enough. There are a lot of anomalies accumulating in the paradigm, and we believe now that these processes are entangled and not alternatives, which has been what has been thought up until now. In conclusion, I would want to thank the Plant Ecophysiology Group, my collaborators. There's many more people not pictured here, funders, family, sponsors, mentors, and also in this environment, a big special thank you to my family, to my husband Andy, and to my long-suffering children that watched in primary school their mother start a PhD. So thank you for your attention.
Thank you, Ros. We've got time for a couple of questions. Ooh, one down here.
Thank you so much for a really interesting talk. So I grew up in Kenya, and cassava is something we ate very regularly, and I had no idea about its, the cyanogenic effects. So what's, just out of curiosity, what is the most effective way to actually eat or reduce that chemical before you eat cassava?
Well, I'm sure what you probably don't realise, of course, you would always peel it before you eat it. Right, so if the core of the plant is, 100 or 200 ppm, the peel will be over 1,000. So never eat the peel. Now I'm sure you know that. The most effective way is to, particularly if you grind it, or if you're doing it whole, if you're giving it in chunks, make them relatively small chunks and soak it before you cook it, and then tip the water out. So that's the most effective. But I think you demonstrate that there is a great need for increased knowledge, yes, and that the increased growth of this plant into areas as they become drier, because it's a phenomenal crop in dry conditions, the knowledge, the rate of planting it is faster than the knowledge of the need to be careful with the processing. The other thing, of course, is to have a balanced diet. If the more sulfur amino acids you have in your diet, the more you can tolerate, because you can excrete as thiocyanate.
We have time for one more question, I think, if there's any burning question. Yes.
Beautiful talk, Ros. Thanks very much. I noticed that the toxic level is much higher for ruminants than monogastrics. Is that because it's rumen processed or what?
I actually don't know the answer to that. There is some truth in what you say. The other thing, of course, is that in the past people thought if you dried out the hay and made hay, it would be fine for the cattle to eat because, it's not going to be activating the enzyme. But in fact, even if you inactivate the enzyme, the rumen can release the cyanide. But I'm not sure exactly. Different species do respond differently in their tolerance to hydrogen cyanide. And I don't fully, I'm a plant scientist.
Okay. Thank you, Ros.
Thank you.
So noting that Mary mentioned cyanides in her talk as well, in sponges, and there's a mystery of why there's cyanide in seawater. So I'm hoping that you two can get together and solve that over morning tea. But before I announce morning tea, I'd like to remind all our fellows who've joined us this ceremony to sign the charter book this week, and that if you haven't had your individual portrait taken yet, to make sure you do so in the Becker room. But of course, I'd like to thank everyone for such a terrific morning session, such wonderful inspirational science. So if we can just give everyone a round of applause, please, just for a moment. Such an incredible meeting with this. I love it. So please do enjoy some morning tea in the Jaeger room, the Dorothy Hill room, or outside under the marquee. For those of you with dietary requirements, those options will be in the Dorothy Hill room. We'll reconvene here at 11:30, so that's, I think, about exactly 30 minutes. So 11:30 sharp, don't be late. You might miss out on some science. Thank you, everybody.
Should a good bottle of wine be sealed with a cork or a cap? There was a time when the high-end wine world scoffed at the mere mention of screw caps.
It might seem a simple thing, but that required an enormous amount of research.
It was in fact industry leaders in Australia who led the push, eager to increase consumer choice. Research has shown that screw caps offer a better seal, meaning oxygen can't sneak into the bottle. The result is a crisper and more well-preserved wine, suited to most varieties of white. Some winemakers insist that fuller reds benefit from a little oxygen in the bottle and therefore age better with corks. But screw caps have another benefit. They prevent the wine from ever being corked, a term used to describe the presence of undesirable chemical compounds almost always transferred from poor cork batches. Corked wine has a characteristic odour that some compare to a wet dog.
We understand so much about the underlying science in Australia that we virtually get it right every time.
Professor Peter Hoy is Vice-Chancellor of the University of Adelaide, but he was also Australia's first Professor of Viticultural Science and then Enology. In other words, an expert in the science of grapes and wine.
This is where science always comes out on top. It enables things because people trust it.
Professor Hrvoje Tkalčić is a modern terranaut. Instead of exploring space, he explores the Earth's inner core.
The inner core is a planet within our own planet with its own complexities.
Complexities he's worked to understand.
Here you can see the inner core.
Through studying seismic waves generated by large earthquakes. These waves traverse through the Earth's interior as vibrations. And by analysing information such as their speed, amplitude and shape, Professor Tkalčić can make inferences about the Earth's internal structure and dynamics.
We use seismometers, these sensitive instruments that sense the ground motion during the passage of waves. We use it in the mode of an inverted telescope. So instead of the sky, we point it to the center of the Earth.
In 2018, Professor Tkalčić and his PhD student published groundbreaking research that found the first unambiguous proof that the Earth's inner core is solid.
What we try to do...
They came up with an innovative approach to detecting shear waves in the inner core, a type of wave that can only travel through solid objects. The challenge with detecting these waves is they have such small amplitudes they can't be observed directly. But Professor Tkalčić's team overcame this by developing the so-called correlation wave field method.
The best way to explain it intuitively is to think about the similarity of the tiny signals that we observe many hours after large earthquakes in the seismic wave field. The similarity between two tiny signals becomes our tool.
A tool that also allowed them to measure the speed of the inner core shear waves.
We found that it was lower than anticipated from the previous models of the Earth, and that also meant that the inner core is a bit softer than we anticipated.
Earthquakes aren't the only seismic activity Professor Tkalčić is interested in. He's also studied Marsquakes using just one seismograph. He and another PhD student were able to scan Mars' core. They used mathematical trickery to turn the 20 or so Marsquakes they had detected into virtual receivers and their single receiver into a virtual source.
And so by applying this mathematical trickery on Mars, we were able to detect the presence of Mars' core and actually measure its radius.
As a university student, Professor Tkalčić was initially interested in pursuing astronomy, but he soon found his calling in the earth sciences instead.
I realized that a knowledge about other worlds and other planets of the solar system is predicated on our knowledge about the Earth.
His own contributions to that body of knowledge has now seen Professor Tkalčić elected as a Fellow of the Australian Academy of Science.
Conducting research in this area really, fulfills our role as pioneers in the grand journey of discovery.
Helping the environment was something Professor Kylie Catchpole always wanted to do.
I really didn't see myself as an environmental activist, though, and I didn't really know what to do with it. So I studied physics. I got to the end of my degree and I thought, well, what shall I do now? It wasn't really clear.
A question that ultimately set her down the path of solar energy research. Today, she's a world expert on all things solar and jointly leads a group here at the Australian National University on advancing perovskite solar cells. While silicon has long been the dominant material used in solar cells, perovskite has emerged more recently as a low-cost alternative with potential to be as efficient as silicon. A potential proven with world records set by Professor Catchpole's team. In 2022, they took perovskite solar cell efficiencies to 22.6%, breaking their previous record of 21.6%.
Perovskite cells now have efficiencies that are similar to silicon solar cells, so just a single perovskite cell, they have efficiencies, the top efficiencies around 25%, whereas the top silicon cells are around 26%.
Professor Catchpole has also led the development of more efficient tandem solar cells. These systems involve stacking a perovskite cell on top of a silicon one, an advancement that could push the solar efficiency ceiling even higher.
The perovskite cell will absorb the blue light really well and give you a higher voltage, and then the red light will actually pass through the perovskite solar cell and be absorbed by the silicon solar cell, and then that will give you additional voltage. So together, that can give you a higher efficiency.
In theory, the efficiency limit of a two-cell tandem system sits as high as 44%. But more efficient and affordable solar power isn't just the end game for Professor Catchpole. She also sees it as a means to help produce another type of renewable energy, green hydrogen.
We'll need hydrogen to produce various materials to refine metals, for example. And if you can produce those using solar energy, then you can reduce the cost of hydrogen.
In another project, her team connected their solar cells with a catalyst to directly generate hydrogen at high efficiency. Efforts that Professor Catchpole hopes will accelerate our path to decarbonisation, both globally and here in Australia.
There's an extremely bright future for renewable energy in Australia. There's just so much opportunity. We're really blessed with the amount of renewable energy resources we have, and we should make use of them.
A message she now shares as a new Fellow of the Australian Academy of Science.
The war in Ukraine has had a devastating impact on the country's people.
We have 9 million displaced people within the country. We have 5 million displaced who are outside of the country.
That includes many scientists working on everything from medical research to the future of space exploration.
So the impact is huge. Imagine you out there, working in your lab, and all of a sudden you have to give up everything and move out.
Thanks to an $800,000 donation from the not-for-profit Breakthrough Prize Foundation, the Australian Academy of Science is now extending a helping hand to Ukrainian scientists.
This opportunity allows Ukrainians who are impacted to collaborate with Australia so that their research effort can continue.
The initiative will sponsor visits to Australia by Ukrainian researchers and make it easy to send data and samples to Australian research facilities with the results returned to Ukraine.
That is really important so that the research capability that's required to help rebuild their nation in the fullness of time is there and is not depleted over the course of the war.
To rebuild Ukraine, we'll need support of the world, and I think these connections which will be built as a result of the program will help us better help Ukraine in the future.
For more information, head to science.org.au/Ukraine research.
You're looking at what brought Professor Madeleine van Oppen to Australia.
Coral reefs have such beauty, they're just amazing, and they're really important for the marine environment because coral reefs are home to about 30% of marine species, so they're incredibly important in that sense.
In 1997, she took up a postdoctoral position at James Cook University. The following year, the world witnessed its first global mass coral bleaching event, another stark reminder of the consequences of climate change.
When you see the damage, that is very frightening.
Professor van Oppen started to investigate the relationship between corals and the tiny algae and bacteria that live within them, known as microbial symbionts. A relationship that we now know is vital to the coral's health and survival.
We also now understand that the microalgae that live in the coral tissues play an important role in the level of heat that the coral can cope with.
Coral bleaching occurs when intense heat waves cause corals to expel the algae living in their tissues.
The corals cannot live without these microalgae, so we often see a high rates of mortality following these intense summer heat waves that cause coral bleaching.
But Professor van Oppen's research has shown it's possible to also harness those microalgae to help the corals cope better with heat.
So certain species of microalgae give the coral better protection against heat than other species. We're sort of playing with that. Can we make them more tolerant to heat by manipulating that relationship?
A question that has since paved the way to a whole new approach in coral restoration known as assisted evolution. The concept was first introduced in a paper Professor van Oppen published in 2015 with her colleague and renowned coral biologist, the late Ruth Gates.
We are accelerating adaptive processes, and those are natural processes that happen in the field. There's quite a bit of evidence that this might not happen fast enough if we don't help these processes a little bit. So we're basically speeding up adaptation.
In the labs at both the University of Melbourne and Australian Institute of Marine Science, where Professor van Oppen now works, she's seen promising results. In one experiment, her team subjected microalgae to increasing temperatures to improve their heat tolerance before reintroducing them back into the corals.
We showed that they increased coral heat tolerance, but without compromising coral growth. So we're very excited about that.
They've started small-scale field trials to see if those outcomes will also hold true in nature.
Restoring reefs with enhanced corals is going to be really important because if we restore with just the stock that is there, that has just bleached, then maybe the next heat wave we might lose it all.
But she says restoration efforts are only part of the solution.
There's a limit to what we can achieve, so the most important thing is that we deal with the emission of greenhouse gases and that we stabilise the climate.
A message she now carries forward as a fellow of the Australian Academy of Science. Michelle Hobbs spends a lot of time at some of Australia's most beautiful waterways. She's searching for one of the world's highly threatened and imperiled groups of animals, the freshwater mussel.
Typical day in the field, we rock up in the truck and we walk down and have a look, see if the site is suitable. We will deploy a water quality probe, take some measurements of that, and then we'll start looking for mussels. So that means sticking your hands in all of the dark holes and in the mud on the sides of the banks.
It can be laborious work, but it's all part of a critical effort to collect baseline data on mussel populations in Australia.
It's really important to get a handle on what the populations are like at the moment, so we've got something to compare to in the future.
It's important to be aware of any declines in numbers or changes in distribution given the enormous role mussels play in our ecosystems and communities. Not only do they clean the rivers they live in by removing algae and bacteria from the water, they're also culturally significant to many Indigenous peoples worldwide. But mussels are facing increasing pressure from threats such as dams, water pollution and extraction, as well as climate change.
We really have to turn to the First Peoples to incorporate their knowledge. There's an enormous wealth of information there that we can make use of.
That's an approach Hobbs is taking in her own research as a PhD candidate and associate lecturer at the Australian Rivers Institute at Brisbane's Griffith University. She plans on working with First Peoples across Queensland and New South Wales to bring their insights on water management to the forefront. She's also looking to travel to Canada and the USA to collaborate with Indigenous researchers there. Hobbs is one of 2 recipients of the 2023 Aboriginal and Torres Strait Islander Scientist Award, which recognises outstanding students and early and mid-career researchers in the physical and biological sciences.
It's a huge honour, it really is. I know I stand on the shoulders of everybody who's gone before me, so I just really hope that I can make a really positive contribution with my research.
Stephanie Bopark describes herself as both a scientist and an artist.
When I started out at university, I just knew I loved chemistry and I loved being an artist. And so I just studied both and I kind of let it lead me to where I've come to today.
And that's to study the chemistry of eucalyptus dyes, including the ones she uses in her own artworks.
I want to know what causes the colour, like what compounds are involved, what combination bind together to make the dye itself. I just want to know the bigger picture of how dyes work.
This curiosity first came about when Bopark was doing an internship on Indigenous knowledges of climate and weather patterns in Western Sydney. The internship got her thinking about how natural dyes change across the Indigenous calendar seasons. To answer those questions, Bopark is now making her own dye in her lab at the University of Wollongong, where she is a PhD student and associate lecturer. She's in the process of doing this with her favourite species, the Eucalyptus cinerea, which produces a bright red dye. Bopark says she ultimately wants this process and her PhD project to be collaborative and community-led.
This project, I'm making it start off really open so that we can be driven in the direction that community wants it to be.
Bopark says she's excited to receive the 2023 Aboriginal and Torres Strait Islander Scientist Award, but not just for the recognition. She has been searching for a way to reimburse artists and knowledge holders for their help on her project.
So this enables me to do that the right way and just make sure that people get the benefit that they deserve for their knowledge.
Distinguished Professor Hrvoje is at his happiest when he's making things. He built his first transistor radio at the age of 10.
Little radio I can hear. I was so excited.
Professor Yu grew up in China during the Cultural Revolution. Universities were closed, so he figured that once he finished school, he'd become a village electrician. But his plans changed after the death of Mao Zedong.
I had the opportunity to enter the university exam. Did pretty well, so I went to this University of Science or Technology of China.
And so began a long and successful career in electrical engineering, one that brought him to Australia in 1989 for a research fellow position at the University of Adelaide with legendary applied mathematician, the late Ren Potts.
I was so surprised. My English was very poor. Written was all right, but English so poor. But I think he probably sees some value in me, which I couldn't see.
Professor Yu was determined to experience everything Australia could offer, so accepted a lecturing position at what was then known as the Capricornia Institute of Advanced Education in Rockhampton. He was there when it became Central Queensland University and was soon named a professor. But Rockhampton was a world apart from his hometown in China, Harbin, known for its ice sculptures and winter days of minus 30 degrees.
That's the reason why I chose Melbourne. I went to Rockhampton so hot. This is actually just right.
His time here at RMIT has seen him receive international recognition for his contribution to the theory and application of discontinuous control systems. A simple example of these systems would be a light switch, where the control action changes suddenly, as opposed to a dimmer switch where things change more steadily. Discontinuous systems have a central role to play in things such as robotics and smart energy grids. Complex mathematical theories need to be applied to properly understand how each component interacts.
How to ensure the system, because there's so many on and off, like switching, on and off, and how to maintain the systems continue to supply when you need it. That's the challenge.
Professor Yu considers mentoring students to be a major part of his role.
So I always tell them that first thing, when you come here, you think about 10 years later where you want to be. And we design the program for you to reach your potential.
It's clear that many of Professor Yu's students see his success as an inspiration. He's certainly had an incredible journey, from making transistor radios as a child in China to being a Fellow of the Australian Academy of Science. Cancer is a leading cause of death in Australia and disproportionately affects our Indigenous communities.
Aboriginal people are about 14% more likely to be diagnosed with cancer compared to non-Aboriginal people, and also about 20% less likely to survive for 5 years after diagnosis. So there's a massive gap there.
It's a gap that Dr. Justine Clarke is on a mission to tackle as an Indigenous genomics researcher and recipient of the 2024 Aboriginal and Torres Strait Islander Award from the Australian Academy of Science. Indigenous Australians still face many barriers in accessing standard and precision cancer care, but Dr. Clarke hopes her research will help change that. At Telethon Kids Institute in Adelaide, she's begun work to build up a knowledge base of Indigenous Australian genomics to drive advancements in clinical care for Indigenous Australians living with cancer.
The exciting thing about it is that we can learn about our DNA and find new treatments for cancer that are targeted to specific genes. And we can also find better uses for our current treatments, better diagnostics, better screening, and that's what we call precision medicine.
Dr. Clarke plans to work with members of the South Australian Aboriginal community to better understand the cultural implications of this research and ensure it will ultimately benefit Indigenous Australians. She will also travel to New Zealand to meet with Maori colleagues with hopes of establishing collaborations there.
Doing it together is the best way forward to create a global agenda where we can improve cancer outcomes for every Indigenous person.
It's work that Dr. Clarke feels incredibly proud to be a part of.
I always think of my ancestors, and they were the first scientists in this country. And I think of the legacy of people that have come before me that have fought for a better future for our communities. And I'm just honoured that I get to do that now through my research.
Professor Louis Moresi has some planets on the boil.
There's a big block coming down, watch.
He often encourages his students to make lava lamps like these ones as a way of demonstrating Earth's evolution.
The density of the hot versus cold liquids, they play off against each other in these really complicated ways. So the blobs would be maybe continental crust, and the background liquid, we think of that as maybe being a little bit like the mantle of the Earth.
Professor Moresi is an expert in planetary scale geodynamics.
My interest is in how the Earth formed and how it became how it is today, with plates moving, turning itself inside out, creating mountains, creating the oceans.
Earth is covered in tectonic plates. Interactions at their boundaries can lead to major geological events such as earthquakes and volcanic eruptions. Professor Moresi builds computer modelling tools to better understand the formation of those plates.
Now, the reason we're interested in that is because the process of plate tectonics stirs the whole Earth in 3 dimensions. So the plates going round into the interior and coming back out again, that recycles a lot of interesting elements, and those might well be elements that are important for sustaining life in the long term.
He also wants to know why Earth appears to be the only planet in our solar system that has tectonic plates.
And the really interesting question, I suppose, is if you look at exoplanets, planets around other stars which might be a bit larger or a bit smaller, or maybe have a different history, maybe they have a different heat content, maybe they're made of something very slightly different. Would those planets potentially have plate tectonics? So the study of plate tectonics has very big implications for understanding whether distant exoplanets may be suitable for life.
One of Professor Morasi's software creations is called Underworld, which can be used in both laptops and supercomputers to study geological problems. He insisted on the source code being available to researchers everywhere.
It's very important to me because I really do actually believe in open science from that perspective, that if you want to do something, you want other people to be able to reproduce your work really quickly. You want other people to build on your ideas. So if they have access to the best tools and I have a bit more time to think about how to improve those tools, then it's a win for everybody.
Born in London, Professor Morasi moved to Australia more than 25 years ago. Today, he's based at the Australian National University, which is also home to one of Australia's most powerful supercomputers.
It is sort of the national university, which makes it a little bit special. And, although we can access computers from anywhere, we can also access the people, we can talk to people. There's natural collaboration that develops with other people who you run into.
He sees becoming a Fellow of the Australian Academy of Science as valued recognition of the earth sciences.
It also gives a sort of an opportunity to let people know about the importance of the Earth as a planet, the planetary evolution, to be able to explain a little bit how the Earth evolves and why it's important to understand that.
Most of what Professor Dmitri Golberg studies can't be seen without an electron microscope. His research involves studying nanomaterials at the atomic level.
You see everything like in real life, but everything downsized to 10 million times. It's about 10,000 times thinner than a human hair.
In the lab here at the QUT Centre for Material Sciences, Professor Golberg synthesises his own nanomaterials. Then, using a technique known as in situ transmission electron microscopy, he manipulates these structures and observes how they change under different conditions such as heat, stress and light. Through tensile strength tests, his team discovered carbon nanotubes are about 100 times stronger than steel.
In theory, it was predicted that all these nanostructures are much stronger. But before these tests were initiated in the microscope, people actually didn't know what's the real properties of these nanomaterials.
Professor Golberg began his research career in Moscow before joining the National Institute for Materials Science in Japan in 1995. There, he became one of the first researchers in the world to study the properties of boron nitride nanotubes.
By serendipity, we found that these tubes exist in nature because at that time only carbon nanotubes were known to the society.
It turned out boron nitride nanotubes are not only as mechanically strong as carbon, but they also have some other impressive qualities.
Compared to carbon, which can be easily oxidized, boron nitride is very stable to any type of oxidation. So it means for any type of high temperature applications, boron nitride tubes are preferable opposed to carbon.
Today, boron nitride nanotubes may be used to reinforce aluminium, a popular material for aircraft. It's research with a wealth of real-world applications. Professor Golberg has more than 130 patents, primarily in polymers.
Once you put these nanomaterials into the polymer matrix, first of all, you can increase the strength, and second, you can dramatically increase the thermal conductivity.
Beyond the applications, Professor Golberg also has a deep appreciation for the images he sees under the microscope.
When I was a boy, I was very much interested in painting, so I have a choice where to go to become a painter or scientist, and I found that this electron microscopy is a good match between art and science.
In 2016, Professor Golberg received an Australian Laureate Fellowship
prompting him to move to Queensland, where his children were living. He says he's honoured to now also be a Fellow of the Australian Academy of Science.
In Australia, I think people of different nationalities, they can feel Australia home. And I'm still very much happy that at some point of my career we came to Australia.
This was initially meant to be just a holiday home for Professor Eric Warrant.
I love the snowy mountains, ever since I was a kid.
But it turns out this would also be the perfect spot to study the 1,000-kilometre migration of Australian bogong moths.
Somehow these moths can migrate from all around southeastern Australia to a really specific destination, all heading to the same place. And this place they'd never been to before.
That place is a few select caves in the Australian Alps.
Look at how they're covering the walls. It's incredible.
And up in there too, look.
Yeah.
Every year, about 4 billion moths from all over southeastern Australia arrive to summer in the cool alpine caves.
How do they know the direction to travel in? But a very other obvious second question is, how do they know when to stop?
To find out, Professor Warrant built his specialised Snowy Mountains lab.
And because we're dealing with the magnetic sense of the moth, we've made everything in the lab, including the entire lab building, out of non-magnetic materials so that there's no interference from magnetic materials.
Professor Warrant's team discovered that not only do the moths use the Earth's magnetic field as a compass, they're also able to navigate by the stars.
And that screen allows us to project the starry night sky above the moth. Then we can rotate the night sky and see if we can get a reaction from these visual neurons in the central complex of the brain as the sky rotates, and we do.
His work on bogong moths is an enduring connection to Australian science, but as a professor of zoology at Lund University in Sweden, he's renowned internationally for his research on dim light vision and navigation. He's studied the visual and navigational abilities of nocturnal and deep-sea animals.
Extraordinarily good vision can be found even in rather small animals like insects. So nocturnal moths, nocturnal beetles, we've found have phenomenal night vision, not only because of this very sensitive type of compound eye which they possess, but also because of the specialised types of neural tricks that they use in the brain.
Neural tricks that have caught the attention of companies.
Toyota approached us and was very keen in developing camera systems that they could mount in cars for use at night to allow drivers to detect animals on the road and even pedestrians on the road.
Professor Warrant did his PhD at the Australian National University before taking up a postdoctoral fellowship in Sweden, where he's lived since.
I usually say I have two homes, and that's very much because I could never permanently leave Australia. It would be impossible for me to do that.
He says being elected as a corresponding member of the Australian Academy of Science is a great honour.
It's especially heartwarming because it's the academy of the country where I was born and was educated. And I find that election to be something that is more special than being elected to any other academy anywhere else.
Now to growing concerns about the deadly coronavirus.
Can the spread of this highly infectious disease be contained?
As word spread of a potential global health emergency, Professor Sharon Lewin was up early every day. She'd jog while listening to COVID-19 updates from the New England Journal of Medicine.
I actually do really like physical exercise or ways to be completely distracted from all the other issues that cloud your mind in a busy work week.
And as director of the Peter Doherty Institute for Infection and Immunity, there was plenty on her mind. A joint venture of the University of Melbourne and the Royal Melbourne Hospital, the Doherty played a key role in formulating Australia's pandemic response. The Institute's scientists were the first outside of China to develop a lab-grown version of the virus.
And we made a decision very rapidly to share it globally, and the virus was available to over 70 different laboratories around the world.
The The institute also created the first COVID PCR test in Australia and diagnosed the first patient.
Professor Sharon Lewin is the Doherty Institute's director. Sharon Lewin.
Professor Lewin became a familiar face on Australian television, sharing findings from COVID modelling and updates on vaccine development.
I never thought to myself, we're under immense pressure here, we must deliver. I was very conscious that science, public health, it's a real group effort.
She says there are plenty of lessons from the pandemic, including the vital need to effectively communicate science to mainstream audiences.
Science plays an incredibly important role, but science is only useful if it's done in partnership with the community and also our political leadership.
And she believes the world's leaders must take steps to ensure low and middle income countries aren't left behind in the next global health crisis.
Welcome back, everyone, as we continue the presentations from our 2024 Fellows. This session will be facilitated by our Foreign Secretary, Professor Francis Zaparovich, who we heard yesterday is happy to be referred to as Madam Secretary, and Council Member Professor Alan Anderson. You may not know what Alan does. Alan Anderson is best known as the Ant-Man. He's a globally leading ant ecologist and studies their responses to environmental stress and disturbance. His work has been applied in land management and in environmental assessment and monitoring, as well as in fire management to help biodiversity conservation. Francis, over to you to kick off the next session. Thank you.
So thank you, Anna Maria. I would like to introduce Professor Dmitri Golberg. Dmitri Golberg is a leading expert in fabricating and analysing inorganic nanostructures. He has developed novel imaging techniques to explore nanomaterials' electromechanical, thermal and optoelectronic properties in real time. His work links nanomaterial structures to functional properties impacting modern and future technologies. So please welcome Professor Dmitri Golberg.
Thank you so much, Francis, and thank you so much to the Academy. It's a really great honor, and I feel humbled. And first of all, I would like to say many thanks to my nominator, Professor Hrvoje, who is in the audience, and of course to my family and to my beautiful wife, who is also in the audience, who supported me for over 40 years of our marriage. And second acknowledgement goes to my former group in Japan, where we lived for more than 20 years, and we actually established all these methods, how to make nanomaterials, how to analyze them in electron microscope. And I moved with my family to Australia 8 years ago, and first success at QUT was we secured very big grant from Australian Research Council, and we were able to establish a new electron microscopy lab, and this microscope shown here is one of the best now in the country. It is so-called double aberration correction system. It means that we have about 45 picometers spatial resolutions, and nowadays, routinely, we can see individual atoms. Plus, we have a lot of manipulators within the microscope. For example, this movie shows you how we can deform and analyze mechanical behavior of graphene nanoribbon. This manipulator is driven by a piezo motor, and if you look at this scale on this corner, it's about 10,000 times thinner than in human hair. So just imagine the scale, but still we are able to do these mechanical tests. And when I moved to Australia, I was very fortunate to organize a very big so-called Center for Material Science at QUT. This is one of the biggest centers now at our university, and we have more than 90 academics and more than 200 students. And I co-lead this center together with Professor Catherine Smith. Okay, just coming back to materials, this periodic table shows you that we have boron, carbon, nitrogen, oxygen, sulfur, phosphor, and selenium. And the color code is like this. So if you look at any type of metal, for example, zinc, we have zinc sulfides, zinc selenides, zinc oxides, and zinc phosphates. And all these inorganic materials can be shaped in different morphologies. It could be nanoparticles, nanotubes, nanowires, tetrapods, mesoporous materials, and so forth. And just with respect to optical band gap, we can create materials from UV range to boronite to infrared range of carbon, and all these semiconductors in between, very diverse materials. I would say we prepared more than 50 different chemical systems in nanoscale. First topic I would like to touch upon is carbon nanotubes. This research became booming since 1991, and this structure is very thin, just 1 nanometer in diameter. And first discovery, and I think it was very unexpected one, because my generation, maybe you remember, we had these thermometers with mercury when we put it to our body and measure the temperature. And in this case, we have mercury, but in this nanothermometer, we put liquid gallium inside tubes, and we found that the height of this column is just proportional to the temperature. And finally enough, we got Guinness World Record book sign that this is the smallest thermometer in the world. It's not scientific, but I think it was very impressive and encouraging for media, for example. And then we came to more serious science, and we decided to analyze what's the mechanical strength of these structures. On this picture, you can see that we put carbon nanotube into the microscope, and we have two contacts on the left and the right. We just put current. And if you look carefully, the tube here becomes thinner and thinner. And again, the scale is only 50 nanometers, 10,000 times thinner than human hair. And finally, we can end up with just single atomic layer. And then we can do this very simple test. We just retract our hold in the microscope, and we measure the force, which can be recalculated into the strength. We found carbon tube is 100 times stronger than steel. Very good structural material for the future. And this experiment was also was very lucky for us, because we were able to hook the core of the tube, which is made of different layers, and retract this core out of the shell. At the same time, we measure electrical resistance. And we found that electrical resistance of this system is just proportional to the length of this core. We call this material nano-rheostat because it's really performs like a rheostat in microvolt, but it's nanovolt, only 10 nanometers scale bar. So we continue to dig into nanotube research. And what we finally did several years ago, we decided to merge tensile deformation in a microscope and resistive heating by using currents. And we were able to create, for the first time, a transistor, because we have 3 contacts now in the microscope. And this semiconducting channel shown on the left corner is only 2.8 nanometers in length. This is the smallest ever semiconducting channel. And that was just a combination of our manipulations inside the microscope. Next, my favorite topic, as mentioned in the booklet, boron-nitride tubes. These tubes were not known until 1994, and then by serendipity we found this by using very high pressures and very high temperatures in so-called diamond anvil cell, we can create these structures. And finally, we got very high yields of these materials and very good crystal structure, very pure, just boron and nitrogen signals. And importantly, this is very primitive experiment. We just hit the tubes in air, and you see boron nitride is white, carbon is black. Boron nitride doesn't absorb visible light, but this gain in weight and loss in weight corresponds to oxidation. So carbon tubes lost weight at 600 centigrades. It means they are just gone. And CO2 or CO formed. And boron nitride is stable until 1100 centigrades. And then we decided that we can do the same experiments with boron nitride in a microscope. In this case, it's bending deformation. We just squeeze a tube between two contacts. You can see that the tube is heavily jammed. But once I retract the piezo-driven electrode, the tube completely restores its original shape. No defects left. Very robust and very elastic material. Then we decided to analyze how about elastic modulus. This special resonance technique can be applied on a microscope, and we found that Young modulus of tubes is huge, 1 terapascal, comparable with diamond. So we have a very elastic material, we have high strength material. Why don't to try to use it as an addition to composite? And you know, aluminum is very popular material for aircrafts and airspace, and we found that whenever we try to put boron nitride tubes into aluminum, it could be nanoscale, microscale, or it could be macroscale. We always increase the strength and the thermal conductivity. So the gain is almost 8 to 10 times sometimes. And another interesting phenomenon, when we have sponge made of these tubes, this movie shows you, again, very elastic, and this sponge can soak the oil from the water. And if the oil is on the surface, again, the same effect. And because tubes are very thermally stable, we can use just a burner, burn this material, and the oil is gone as organic solvent, and the sponges remained. So we can use it many, many times. And if we do continuous pumping, we can clean the water out of the oil completely. So my plan is to clean the Brisbane River by using this technique. Okay, time is up, so just a few more movies. We found another property. Boron nitride nanomaterials are so-called superhydrophobic. The water droplets jumping on the surface forever. There is no any wetting, so this can be used for car windows or house windows very effectively. Okay, graphene, another interesting material. We found that if we put this electrode to graphene, the electrode made of tungsten eats graphene. And this is very important for electronics, because in this case, we should know which type of metal we can use for graphene electronics. Okay, finally, detail organized nanosheets. This movie show you how we can dispatch individual atomic layers from the crystal. This is type of Scotch tape technique, which used for synthesis of graphene these days. So I skip maybe last part of my talk because time is up. and I hope final. So we can do battery research as well. So this is just mimicking lithium-ion battery, and we can see how anode is swelling under lithiation. I hope I convince you that this is a very new method which can be used for analysis of many materials properties, and thank you so much. I apologize for not keeping time. Yeah.
Thank you. So that was a really exciting talk, and I can understand why he wanted to go over, but we won't let him. So do we have one or two questions for Dmitri? Because while we're waiting, I have several. Andrew, thank you. Andrew Holmes behind you. I didn't see the other one, sorry.
Thank you very much for your talk. How about processing boron nitride? How do you process it if you're going to put it on a windscreen?
We use induction heating furnace, and we use some precursors made of boron oxide and some metal oxides, and very high temperature, vapor phase, and from the top of the furnace we put ammonium gas. So this is vapor phase reaction, and we have grams of boron nitride tubes, which can be spread as a solution on any type of surface. It's not CVD, it's called induction heating. It's more like more high temperature and more fast time.
And Elaine, just there. Yep.
Thank you. If we're going to put the materials into airplanes and things, what's the lifespan of the nanomaterials? Do they degrade, and are there any biological consequences, like what happens if the nanomaterials get into cells, for example?
It depends on nanomaterial. For example, boron nitride is very stable. It can be kept in air for forever. But some materials, for example, like carbon, can be contaminated and oxidized very quickly. So for electron microscopy, we always need fresh samples. And we keep samples in outer high vacuum chambers before we go to the microscope.
So hopefully after he cleans up the Brisbane River, he'll start on the Yarra. But thank you very much, Dmitri. So next speaker will be introduced by Professor Alan Anderson. Thank you, Alan.
Thank you, Francis. Hello, everyone. Our next presenter is Professor Michael Kearney. Like me, Mike is an ecologist, so his research is especially important. His transformative work has forecasted the future and fate of biodiversity through development of mechanistic species distribution models. The mechanistic nature of these models enables projections for the novel environments that changing climates will bring, delivering significant benefits to fundamental and applied biology and the well-being of people and the ecosystems we rely on. Thank you.
Thanks very much, Alan, Madam Secretary. It's been so much fun to be part of this meeting and so fascinating here on Nullarbor country. I'm learning so much, and I want to start by thanking my nominator, Zheng-Xiang, and also the supporters and the Academy for welcoming me into this scientific family, as was nicely put previously. And I have a lot to thank from members of the Academy actually in my career. My PhD supervisor was Professor Rick Shine, whose brother did the reno for this building. And also, just in particular, a couple of people who have been mentors my whole career, Craig Moritz and also Ari Hoffman, members of the Academy. And I also want to thank my family. My wife's here and my daughter. I think my parents are watching. Hi, Mum. So I'm an ecologist, as Alan said, and I'm going to use Mary's puzzle metaphor as well. One of the big puzzles I like to try and solve in ecology, and it's one of the kind of big questions in ecology, is what limits where species can and can't occur. And as you can see in this figure, there's a whole lot of pieces that are biological, a whole lot of pieces that are physical, and we've got to stick them together somehow. And just to pick an example that's, oh, there's an insect flying past me now. It's not a random example. This is a grasshopper called Warramaba virgo. It's actually got relevance to the society because it was discovered by Michael White, and I took the photo of his signature in the special book yesterday. He was became a member in 1956. It's interesting because it's a clonal all-female species, and what you can see there is the distribution of one genotype. We've recently discovered that it's just one genotype. So, what limits that? If you actually go and study the species in the wild, it occurs on shrubs in semi-arid areas, lays eggs in the ground, but it will have limits in terms of what temperature it can persist under, what combinations of humidity, rainfall, and so on. And we've got this concept in ecology called the ecological niche, which is just a depiction in multivariate environmental space of those conditions that allow them to persist as a population or a species. And so we've got a way to take this concept and use it to model species distributions, and we call this niche modelling. And it's really been pioneered here in Australia. What we need to do this modelling is take some information about the organism and combine it with some environmental layers. And the reason that it was pioneered here in Australia was because we had environmental layers first. There's an interesting reason for that, which you can ask me about later, but Mike Hutchinson here in Canberra at the ANU developed that method. And then most of the approaches, the first way this was done, and one of the dominating ways that this is done these days, is what you can call a correlative method, where you start with the phenomenon of interest, the distribution itself, and you link that with the environmental layers in a statistical model to make inferences about the probability of distribution. And we've also pioneered this area, partly because we had the layers first, and we had some great scientists, and someone who's really pushed this field along is Jane Elith, who I think is here in the room as well. And these are really powerful models. They're process implicit, so they can pick up any process that's in some way statistically related to those layers. But I actually get a real buzz out of trying to understand what limits species distribution. So if you want to do that, then you need to take a different approach and start instead with the organism itself, measure things about it, measure its traits, and link those with a model of some important process and map that out to the landscape, some measure of performance as a result of that process. And this is satisfying in terms of understanding what the mechanisms are limiting a species, but it's also really important for predicting to novel conditions because, of course, if you're doing a correlation, then if you take that, you're making an induction when you take that model to the landscape, and if it's beyond the training data, then it's an extrapolation, whereas with a mechanistic model, if you can make one, then you're making a deduction and you're not extrapolating to novel conditions. So that's sort of the goal. How do we make a mechanistic model? And there are so many processes you could think about limiting species. But I guess the approach I've been taking is to look at the thermodynamic constraints, because organisms can never escape the laws of thermodynamics. And organisms are really interesting to think of from this thermodynamic perspective, in that they're very far from equilibrium, remaining in a steady state or going through a steady trajectory through their lives. And in thermodynamics, the approach is to define a system, to draw a boundary around some part of the universe of interest and follow the flows of energy and mass in and out of that system. And so the challenge is to try and work out how to do that for organisms. And if we can do that, then we're really capturing the fundamentals of what allows an organism to survive, the things that you'd be front of mind if you were dumped with no resources out in the desert where this little lizard occurs. You'd be thinking about temperature, you'd be thinking about your water balance, finding food, those sorts of things. I've depicted these processes with these particular words because the actual equations connect together in this particular way. And if we can actually view the organism in this way, then we have a very holistic and powerful view of what limits it. It turns out that a lot of the theory to do this already exists from work done in the 70s, 80s and 90s. And so here's an example of a book about the microclimate that we need to understand to do this kind of analysis. Biophysical ecology is applying heat exchange principles to understand how energy and water fluxes through organisms. And then this book on the dynamic energy budget theory is how we can think about the metabolism of the organism in a thermodynamically formalised manner, where you can actually compute things like the heat balance and the entropy production from first principles. So these sort of parts existed, but what I've been trying to do is work out how to stick them all together into what I've called a mechanistic niche model to make inferences about where species can occur. And I'll just give you an example of this using, it's an old example, but it's an oldie but a goodie. It's the cane toad in Australia. And as many of you will know, it came here from South America and Central America via Hawaii in 1935, and it's been spreading across the country ever since. And the question is, how far is it going to spread? That's obviously critical for managing it. And some various predictions have been made. Here's an example that was made back in 2007. And it's a correlative model, and you can see the black line is where the toad was at the time of the prediction, and the green is the prediction. And you can see I'm not particularly happy about this prediction because they're coming to Victoria where I live. You can see Canberra's fine. But this is a statistical model, so it may be extrapolating. I mean, it is extrapolating because this is a species that's invaded a novel environment. So to take a more mechanistic approach, my colleagues and I measured some things about the cane toad. In fact, this was measured by my colleagues up at Charles Darwin University, Keith Christian and Chris Tracy. Put cane toads down a very simple racetrack, put them at different body temperatures. So these are body temperatures. This is how fast the toad was hopping. You can see toads don't hop particularly well below 15. They're starting to have trouble around 35 as well. But if you're into cane toad racing, and some people are in inland Australia, 30 degrees, you can get them going almost 2.5 k's an hour. So that's their physiological constraint. Then we can actually calculate the body temperature of the cane toad with the biophysics and plug that response in and actually calculate how far could they move in a year. And that's what you see in this map. And that matches what we see in the spread of the cane toad across the top end. Roughly 55 kilometres an hour is how far they're going. We predict 65. We predict slower spread down south. But you can also see that we predict they couldn't really move much at all down in the very southern areas, and that's because in the warm time of year, it's also dry, they're evaporatively cooling, it's too cold for cane toads, and so happily this is an extrapolation and we don't have to worry about them coming to Victoria, at least in the short term. And so then adding some more information about the development of the larvae in ponds and simulating ponds filling up and drying, we can make a map that's, in this case, the number of months per year that a cane toad can breed, and that's our final prediction that we made. And you can see, this is where we expect it to finally go, so almost to, not quite to Perth, and not quite into Victoria. That map has been used for making management decisions about the cane toad, and what I've just flicked to is the 2050 prediction for where they might go, and you can see Victoria's, maybe they'll get into Malakuta, Canberra's still safe. But what we also did, some colleagues were looking at the effect of restricting toads' access to water in arid areas and showed that that's an effective control, and we did, with that same model, some calculations of radii, how far toads could go from the artificial and natural water points throughout inland Australia. All the blue points are natural water points and all the orange ones are artificial ones. And that led a couple of colleagues, Ben Phillips and Tim Dempster, to propose the toad containment zone, that if we blocked artificial waters in this area, then we might be able to stop toads from getting into the beautiful Pilbara. And thankfully, the West Australian government is going to support this, and hopefully cane toads will stay out of Western Australia and Perth as a result. What I've been trying to do is make this sort of approach more accessible to ecologists. I certainly didn't do any physics when I was aiming to be an ecologist. I didn't think I needed to, but I think there's a lot of power that we can harness from collaborating with physicists and engineers to do ecology better. So this software is my attempt to make this more accessible to ecologists. And as I said, this is a challenging problem to understand where species can and can't occur. It's a challenging puzzle. And what I do when I do puzzles is start with the edge pieces. And what I've been trying to say in this talk is that these thermodynamic principles you can see as the edge pieces of the puzzle. And yeah, I hope that we can take this approach further by creating more interdisciplinary and multidisciplinary collaborations to make better predictions and create a better understanding of what limits species and where they'll go in the future. Thanks very much.
Yeah, thanks, Mike. I think that's a really great example of the importance of mechanistic understanding in science, isn't it? And so that allows for much more robust predictions than those based purely on association alone. So we've got time for some questions. Rod?
I think the correlative models are really powerful and excellent too.
Thanks, Michael. Great talk. I guess a question would be that cane toads aren't just going to hop to Victoria, they'll probably get a ride as they have in other places. If they make it to Victoria, could they Could they survive?
Well, those calculations are not assuming anything about dispersal, so they're basically asking if they were there, could they survive?
So the microclimates and stuff they'd encounter in Victoria?
Yeah, I mean, there could always be some little microclimates that are constructed that allow small populations to persist, but it's at the very least it's saying they're going to be easier to control. They're on the edge of existence in Victoria. That's what the models are saying. Yeah. It's not a well-designed room for roving microphones, is it?
Thanks, Michael. Great talk. One of the things that species conservationists and governments face is, in the face of climate change, when to translocate, when to move to ex situ conservation, and we generally do it too late. And I'm wondering how your models could be used for more timely interventions.
Well, yeah, the actual one example of a climate change translocation did use these models. It was a collaboration with Nikki Mitchell at University of Western Australia on the western swamp turtle. And they had, this is a classic case where there's only one distribution point, right? There's just one swamp, or two nearby, where they were persisting. And we were able to make inferences about whether it would be better to move them north, which was the plan, or move them south. And they moved them south, and they're actually doing well down south. So yeah, no, it is something that we can use to make those sort of decisions.
One last question. Thanks for a great talk. I love that approach. The limitation, though, is the sort of parameterisation in your experimental animals. How do you account for the genetic diversity that there is likely to exist in very large numbers of animals?
Yeah, that's a really great question. And the thing is, I guess it tells you what the traits are that you are interested in that might evolve, and it gives you a target for the traits to look at for genetic diversity. So obviously it's a trait explicit model, so you can explicitly ask, what if I change this trait, what is the sensitivity, and then it can help you also target what traits to actually look for genetic variation in. So yeah, that would be my answer to that. But you also said, yeah, the point is often made that we need a lot of data for these sorts of models, and it's sort of true, but probably the biggest barrier is training, actually, because we don't get taught in these methods as ecologists.
Thanks, Mike. I see there's some other questions, but I'm sure Mike will be happy to have a chat with you all at lunchtime. But please join with me and thank you. Our next presenter is Professor Matthew Kiernan. Matthew is an expert in neurodegenerative diseases, particularly motor neuron disease and frontotemporal dementia. He devised and introduced neurophysiological techniques that enable ion channel function to be studied in vivo in humans, which have delineated normal function, mechanisms of disease, and therapeutic targets. He's also implementing novel therapies based on these discoveries and using his techniques to measure responses to treatment that are now being trialled worldwide. Professor Matthew Kiernan. Thank you.
Thanks very much. So thank you, and maybe just to continue on the theme that was started yesterday afternoon, reconciliation. This is a indigenous rock art painting from 40,000 years ago, which is a network. And this is really the theme of my presentation, a network of patients, a network of clinicians, clinician researchers, and international researchers and collaboration. And I suppose we're based physically in the Randwick precinct, and that's the coastal network which extends down to Malabar and La Perouse, and very strongly connected to Prince Henry, which was the medical centre for those regions, and very strong community support. I suppose I've been very lucky to work in an era of neurology, which is a therapeutic era. So when I started in the 90s, there were no treatments for multiple sclerosis. The first treatments were introduced, interferon therapies, then intravenous infusions, and ultimately now monoclonal antibody therapies. So if an 18-year-old presents with a loss of vision, the first episode of multiple sclerosis, she'll be treated with alemtuzumab, a monoclonal antibody, and she'll never have another episode of MS again in the course of her life. So it's really transformational. And in fact, the inventor or pioneer of humanised monoclonal antibodies, Sir Greg Winter, received all of his seed funding from Sydney horse racing enthusiasts and comes back to Sydney regularly. In fact, had an honorary degree from the University of Sydney a couple of years ago. And he actually sold monoclonal antibodies back to the Medical Research Council for £7 billion. It generates about £21 billion per year. And it's a really transformational therapy. But there are great also examples here in Australia, and this is Michelle Farah. When I was doing neurophysiology diagnostically, I was charged with having to do all of the tests in babies, infants, and children, which is quite complicated for an adult neurologist. So I realised we needed to train a paediatric neurologist. And Michelle, during her training, then thought she'd like to do some research. And so we asked what she'd like to do it in. I was working in neurodegeneration, so she focused on spinal muscular atrophy. And we started by looking at the natural history. And these children would die within 6 to 12 months of birth, type 1 and type 2 spinal muscular atrophy. And then Michelle mentioned that the NIH said this is the most likely condition that will have genetic therapy and treatment and a cure. And it seemed very unlikely that this would be possible. But during the course of her research, Michelle worked into the concepts of pathophysiology and markers of effect and treatment outcomes. And then in the next few years, with understanding the mechanism of the condition, so a specific genetic abnormality in survival motor neuron, genetic therapies became available and were introduced, and Michelle introduced those therapies to Australia and was part of the global introduction of therapies. And this has really generated a whole new, these children who would have died within 6 to 12 months of birth are now achieving normal motor milestones well into their adolescent lives. And in fact, this is Mackenzie, who died of spinal muscular atrophy. And Michelle pioneered genetic testing for reproduction in couples to try and ensure that this wouldn't happen again. And subsequently then the introduction of newborn screening for these lethal conditions. So Michelle is now treating babies before they've developed the syndrome with genetic therapy, so completely transformational. And I think the sort of the message is by understanding the mechanism, you can come up with therapies. And for us as neurologists, the pioneering work was done by Hodgkin and Huxley, and these are original pictures of their studies. And they were based in Cambridge, but they realised they wanted to try and understand how nerves conduct. And at that stage, there was a lot of theories that perhaps it was a physical process. It was a sort of a shake going down the nerve that was doing this. They felt that it was chemical and particularly related to ion channels. And so this is from their original studies. They tried looking at crabs, cuttlefish, frogs and lobsters, but they couldn't get any of the techniques to work. And then unfortunately, World War II broke out, and they were clearly very brilliant individuals, and they were taken into British intelligence and developed the radar system, and that was the turning around of World War II. They then came back into research after the war and came up with the concepts of saltatory conduction and nerve impulse progression. And that was really transformational. So I've been fortunate with academic builders, and in fact this is Professor Jim Lance, who started neurology in Australia, is the first professor of neurology and also a fellow of the Academy. And he spent his time looking at migraine headaches, and again, a phenomenologist. So he put together the histories of 500 patients with migraine, and then working with Pat Humphreys from GSK in the United Kingdom, they came up with the first treatment, Imigran, for headaches. And that put, I think, Sydney and Australian neurology on the map. And this is actually Oliver Sacks, who called me out of the blue and said that he wanted to meet Jim Lance to talk about migrainous phenomenon. And so that the reputation of Australian research had spread. And David Burke, I started neurology in the decade of the 90s, which is the decade of the brain. And I called David for a job. And he had just started the Prince of Wales Medical Research Institute with Ian McCloskey, and I can see Simon Gandevia here in the audience. And they took me out to the corner of where this building was, and they said, one day this will be a major research institute. It just looked like wooden huts. This was a TB hut. And in fact, I thought they were a bit delusional at the time, but they were right. And this is now Neurosciences Research Australia, so I'm pleased to have come back there last year. And our studies were looking at ion channel manipulation. So can you use physiology to alter the activity of ion channels, particularly sodium and potassium at that stage, and come up with concepts of conduction failure and improvements? And I think it's important for us as clinicians to embed our research in large programs. And this is Glenda Halliday, who really brought us all together in a neurodegenerative focus, using the patients that we see in clinics to drive biospecimens, to drive basic science approaches, but also the brain donor program, understanding the spread of pathology in the brain, and again, trying to get mechanistic insights. So a number of the techniques that we developed, these are all built in the laboratory and subsequently been commercialised. And the importance of that is they become available to groups around the world to study and also to better understand patient symptoms and conditions. And in fact, Digitimer, who've commercialised the software, have also built stimulators now, which are FDA approved, which allow us to study patients in a diagnostic and a research laboratory. So I've been more interested of recent years in neurodegenerative conditions, and part of the problem has been to try and understand brain function. And really, we've tried to translate these peripheral studies into understanding cortical function, cortical motor function, and cortical excitability. And this is done with transcranial magnetic stimulation. And this is actually reduced inhibition. So this is a single patient with motor neurone disease. And then when we start them on neuroprotective therapy, they get a pseudo-normalization. So they come back towards normal, but they never approach normal, and the condition continues to deteriorate. But I suppose we're now starting to get the idea of the mechanisms, the physiology and the function that may be underlying these neurodegenerative conditions. And I think it's important to try and bring all of these streams together, whether it's the brain banks that Glenda has pioneered, the new technologies and function, to really try to understand these conditions. Because until we have proper mechanistic insights, we're just sort of shooting in the dark in terms of therapy. So we're here as a clinician making the diagnosis, and it's an inevitable decline. But what has happened in the 30, 40, 50 years before, all the way back to conception? And it's really by only trying to tackle these issues that we're going to be able to come up with effective therapies. Now in motor neurone disease, and adult motor neurone disease, the first therapies are available. So again, antisense oligonucleotides. And in fact, patients who have these conditions are now turning the corner. So they present with weakness, and when they get treatment, power starts to come back to their limbs, which as a neurologist is something that we've never seen. But it shows the importance of testing everyone who presents with these conditions for genetic abnormalities. And taking this further, going back to the harbour idea, we've been able to, as part of an international consortium, it's called Project Mine or InMe, which has been driven by an industrialist who cleans harbours, to try and get all of the genetic information in sporadic ALS patients. And this has led to new understandings that brain and mind conditions are linked. So for instance, in neurodegenerative conditions, there's higher incidences of autism spectrum disease, schizophrenia, bipolar disease. And this has been driven by large consortia. So really, we've been lucky to have a community of patients who have engaged in research. We really need a multidisciplinary research environment. We need to be able to diagnose patients better, and that requires understanding the pathology. And it's really through the global networks, and we've been very fortunate through international philanthropy. And we're starting now to see treatments. And in fact, in Alzheimer's disease, we hope that in the next 6 to 9 months, the first monoclonal antibody therapies will be approved by the TGA. So it's really a completely transforming landscape, and hopefully much better patient outcomes. Thank you.
Thank you, Matthew. I really like the way you introduced your talk in the context of networks, because we all know that networks are so fundamental in nature, but they're also so fundamental in human life, aren't they? And they have been here in Australia for more than 40,000 years. Any questions for Matthew?
Matthew, I enjoyed your talk. Can you answer this question for me? Is there a chance that you would see the onset of mental decline or some of these disorders first before you saw the onset of the actual physiological conditions with ALS?
Very good question. So an occupational therapist, Ineda Miyoshi, spoke to the partners of patients, and they'd been reporting abnormalities 5 or 6 years before they presented with weakness. And the most common issue is apathy, but they noticed also impulsivity, frustration, irritability, and a start of a gradual disengagement. I think we can get to the bottom of this if we have PET tracers looking at those proteins like TDP43, but at the moment it's more historical, but yes, and that's probably why our therapies haven't been very effective. We need to go -5 years before the condition begins. Thanks.
I'd like to ask about ion channels because you mentioned them. So what do you think of the comments or the theory that A beta 40 and 42 form ion channels in neuronal membranes, although they're not very good ion channels because they're not very selective, but they do let ions through?
Yeah, so I think this is part of the issue about protein and protein abnormalities and function. And this is a debate that's gone on since time immemorial. What's more important, the anatomy or the physiology? And I suppose I would say it's probably more the physiology. So when we see TDP43, probably the whole process has gone through hyperexcitability, and then we're left with the protein abnormality. So I think by understanding the connection with amyloid, sodium channels, the whole process as a function, until we understand that properly, we're not going to have effective therapies. So monoclonal antibody therapies directed against amyloid are effective in Alzheimer's disease. They're clearing the amyloid, but actually the patients aren't getting better. So the cognitive decline is slowing down and they're plateauing, but they're not improving. So I think there's a lot more to learn.
Talk, and so marvellous to see that these intractable problems now are really coming within our grasp. I wanted to ask you the role of mitochondria and exercise more widely, because that seems to have a key part to play in these degenerative diseases.
Yep. Well, very hot topic. And mitochondria clearly the energy sources of all of our cells, and all of the treatments that we've done for mitochondrial approaches haven't worked to date. But I think it's too far gone, it's too late. And exercise is also a very controversial area. Patients know that exercise, a lot of these conditions, we know high performance athletes get them. We know Neil Danaher in Australia has generated now about $150 million of philanthropy. It's very common in AFL players, football players, tennis players. So exercise is part of the puzzle. And I suspect it's in probably an epigenetic process, but it isn't very well resolved. And so at this stage, we encourage all patients to exercise, but it's not borne by any major scientific understanding. Thank
you. Our next presenter is Professor Glenn King. Glenn is a leader worldwide in the study of arthropod venoms and the development of venom peptides as pharmacological tools, human therapeutics, and bioinsecticides. He has made seminal contributions with respect to our fundamental understanding of the evolution, ecology, production, and functional and structural diversity of arthropod venoms. This has resulted in safer ways to control disease-spreading pests and to protect crops, work recognised by the 2023 Prime Minister's Prize for Innovation. Thank you, Glenn.
Thank you, Alan, for the kind introduction. Thank you to the Academy for this extraordinary honour. And I want to start the talk by acknowledging those people without whom I would not be here. Firstly, my PhD advisor, Philip Kuschel, who's been a good friend and mentor for more than 30 years now. My postdoctoral advisor in Canberra at the University of Oxford, David Craik, who sponsored my nomination, whose work on Disulfide-constrained peptides has been a real inspiration to our group. And importantly, my exceptionally tolerant family, my daughter Gemma, my son Aidan, and most importantly, my wife Susan, who's in the audience, who we've been on this journey together for 30 years now. I want to thank the many agencies that have sponsored our work, both government and philanthropic. And most importantly, I want to thank the incredibly talented students and postdocs that I've had to work with over a period of more than 30 years. I believe my most enduring scientific legacy will actually be my mentorship of these students and postdocs who are, after all, the next generation of science leaders in Australia. I got interested in the problem of insect pest control in the mid-1990s when the world was becoming more acutely aware of the problems with respect to potential hazards to humans. Remember, all chemical insecticides are neurotoxins. We started to become worried about their effects, particularly on young children. We became more aware of their effects on fragile ecosystems, particularly their effects on non-target organisms like pollinators, such as bees. And of course, we'd been using some of the same chemical insecticides, in some cases for more than half a century, so it was inevitable that insect pests would start to evolve resistance, and that was happening. And so in thinking about more eco-friendly ways to try and control insect pests, I turned my attention to the best insect killers on the planet, and they, of course, are spiders. Spiders are really good insect assassins because over a period of about 400 million years, they've evolved these potent venoms that enable them to rapidly immobilise their prey, and what that does is turn prey capture from a physical battle to chemical warfare. And so my hypothesis was that if we interrogated the venoms of these spiders and understood their pharmacology in particular, we might be able to come up with better ways of controlling insect pests. Now that hypothesis could have failed very rapidly. So I'm going to show you one data slide. This is the very first experiment I ever conducted on spider venom. So this is where I tried to separate out, fractionate out using a process called HPLC, the various components found in the venom of an Australian funnel-web spider. And I had not worked on venoms before. I assumed these venoms would be very simple, much like snake venoms. And after all, why would a spider need more than half a dozen or so insecticidal toxins to kill its prey? And I was really shocked when I did this experiment because there were just lots and lots and lots of peaks. There weren't half a dozen, there weren't a few dozen. There was clearly at least 100 components in the venom of this single spider. And the really surprising thing was the first few peaks that eluded were due to small molecules, but the majority of the venom was made up of small peptides, so tiny proteins a bit smaller than the size of human insulin. And what we now know from proteotranscriptomic work we've done in the last 5 years is that the venom of the Gari funnel-web spider, for example, expresses more than 3,000 peptides in its venom, which makes it probably the most complex chemical arsenal in the entire natural world. So these venoms are extraordinarily complex. The other really exciting thing was we found that almost all the peptides in spider venom had the same type of three-dimensional fold called a cysteine knot or a knot fold in which the protein chain, which is just a linear string of amino acids, is cross-braced by something called disulfide bonds. But in these peptides, they have a particular configuration. If we look at the top disulfide here, and the bottom disulfide here, and intervening sections of the polypeptide backbone over here, you can see that they form a loop. And the third disulfide actually dives through the centre of the loop, which you can see better in the video. So the orange disulfide dives through the centre, effectively ties this protein chain into a pseudo knot, which gives these peptides really extraordinary properties. So for example, these peptides are highly resistant to proteases. They're heat resistant. You can typically boil them and cool them down. They retain their pharmacological activity. They're resistant to UV. And most importantly, what we were able to do by interrogating the venoms of a range of Australian spiders was find some of these peptides that were orally active at killing a range of crop pests, but they had no activity on bees, and they had no activity on mammals, fish, and birds. And that seemed to be the basis of a more ecologically friendly insecticide. So in 2006, I founded a company called Vesteron Corporation to try and take some of these peptides and manufacture them at a scale that would be commercially viable, and they've been very successful in doing that, and I'm proud to say that they've won a vast number of green technology awards along the way, including one from the US Environmental Protection Agency. So they now sell 4 bioinsecticide products in North America with registration pending in Europe. And in 3 of those products, the 3 I've shown on the left, the active ingredient is a peptide from the Australian Blue Mountains funnelweb spider, believe it or not. So a peptide from the Blue Mountains funnelweb spider is now being sprayed on broadacre crops. This peptide has a novel mode of action. It's safe for bees. These are one of the only insecticides in the world that don't have a bee warning on the label. And they're so safe for humans, they have what's called a 0-day pre-harvest interval. So a farmer can spray their crops in the morning and they can harvest it for market in the afternoon because there's no toxic residues. What we learnt by studying not just spider venoms, but a range of arthropod venoms, is that almost all of them were dominated, their venoms were dominated by these small peptides. And what's more, by studying the pharmacology of these peptides, we found that the vast majority of them targeted ion channels. And the reason that became important in terms of our interest in human therapeutics is that it turns out ion channels are the second most common human drug target after G protein-coupled receptors. And they're actually very hard to target in many cases with small molecules. And so when I moved back to Australia, this won't go forward anymore. Oh, there we go. So when I moved back to Australia to the IMB, our focus became trying to take some of these peptides, the targeted ion channels, to look at human diseases. And the 3 we're interested in is the chronic pain associated with IBS and endometriosis, pharmacoresistant genetic epilepsies, and in particular, what I'm going to talk about today very briefly is acute cardiovascular diseases such as heart attack and stroke. And I wanted to mention that because some of you probably read about this in some of the media coverage, much of which has been fairly hyperbolic. But we discovered a peptide, an incredible peptide in the venom of the Gari funnelweb spider. The 3-dimensional structure is shown at the bottom there. And it's an incredibly potent inhibitor, so it has, for the pharmacologist in the audience, an IC50 of 500 picomolar for a channel that we thought was important in the neuronal degeneration that you see after stroke, a channel called ASIC1A. And what we found is when we administered that peptide up to within the first 4 hours after stroke onset, we could reduce brain damage by up to 80%, which was extraordinary. And then we found that it could also protect the heart during a heart attack and importantly extend the period for which we could keep viable a heart that had been procured for transplantation. On the basis of that, with my colleagues Bob Graham, Nathan Palpan, Peter McDonald, we started a company called Infenza Bioscience to try and keep this technology in Australia. Bob and I raised $23 million via Zoom during the COVID pandemic. That was an interesting experience. And the company is now set up at the Translation Research Institute in Brisbane, and we're on track to start phase 1 clinical trials in the second half of next year, targeting a particular extreme form of heart attack called ST elevation myocardial infarction. And the point I want to make right at the end here is I've talked a lot about our translational work, but it's really been underpinned by a basic science pipeline that really provides the foundation for our translational research. So we've looked at the composition, the pharmacology, and the evolution of a range of arthropod venoms. We were the first to study the venoms of centipedes, assassin bugs, caterpillars, and you'll be pleased to know ants as well. We found that they've evolved in lots of different ways. So spider venoms largely evolved by massive expansion of a single ancient gene. We found caterpillar venoms that have evolved by horizontal transfer of pore-forming toxins from bacteria. And we found in ants a really extraordinary case of Gilbertian mimicry, where the ant makes a mimic of a hormone found in its major predator, the echidna, which sensitizes the echidna to bites by that ant. So once again, I'd like to finish by thanking the students and postdocs, which it's been a joy to work with. For those of you that like a shorter synopsis of our work, there's a few of us in the lab that play instruments and sing, and we put together a song that describes our work. It's called Peptide, and you can go to YouTube and watch that video. And if you'd like to know more about the work that I described at the end about developing a drug for stroke and heart attack, there's actually a Catalyst episode on that, so you can go and watch that on ABC iView. And with that, I'll end and happy to answer questions.
So it's good to know, isn't it? If we ever get bitten by a funnel web, we can take great comfort in knowing that the venom has important, broader societal benefit. Any questions?
Hi, thank you for an absolutely brilliant talk.
Thank you.
Could you tell us just a tiny bit about why the bees are happy with this? I mean, they are insects after all.
Yeah, look, it's a great question. We got lucky. So bees weren't part of our initial screen. So the way we discovered these insecticides originally was we screened a whole bunch of insect pests, and we screened then those peptides in a range of mammalian neuromuscular preparations, and then we tested them in live newborn mice. But bees weren't part of it, so we only found that out later. Obviously now it's included as part of the screen. But we can find extreme selectivity. We have 2 examples where we have a peptide that will kill German cockroaches but won't kill American cockroaches. So you can get extreme species selectivity. Yeah.
Thank you for your great work, Glenn.
Oh, there you are. Sorry.
I think you just answered the question, but how can the funnel web venom be so toxic, and yet when you take out its components, you can find something that's very safe? So that's a puzzle. Is it due to this? Is the total toxicity a mixture of many things, and when you take them apart separately, they can be innocuous in certain conditions? Or is it a matter of delivery, like through the blood versus somewhere else?
It's a matter of the fact that there are, as I said, 3,000 different peptides in there, and we know precisely which one is responsible for killing us if we get bitten by a funnel web. And I can tell you about the mechanism of that later. But the curious thing about that is that that toxin works in insects and primates and virtually nothing else. So if your dog or cat gets bitten by a funnel web, they're probably going to be okay. So this gets back to this species selectivity, and it's very hard to predict species selectivity. But the point I want to make is that no venomous animal has evolved to kill us. Whenever it does, it's just an extreme coincidence, right? Except for snakes, which obviously prey on other mammals. But there are over 100,000 species of spiders, and only 4 can actually kill us. So most spider venoms are completely innocuous, including the venom of the world's biggest tarantula, the Goliath tarantula, which is big as a dinner plate. So that spider can bite you and it'll cause no harm.
Thank you very much, Glenn. That was an amazing talk.
Thank you.
Very inspiring. I've got a slightly selfish question, actually. There are lots of different species of funnel web spiders.
Yes.
Are they all equally toxic? Because I'm asking this because when we're doing field work in the Snowy Mountains in spring, there are Kosciuszko funnel webs everywhere.
Yeah, yes.
We try and avoid them, obviously, but how toxic are they? Do they differ in toxicity, the different species, or are they all pretty much the same?
They do differ, but they're all toxic. There are gender differences, so if you get bitten by a female funnel web spider, Sydney funnel web spider, you're going to be okay. They don't make much of the toxic components. So we published a paper a few years ago in PNAS that suggests that the toxin that kills us is a defensive molecule used by the male spiders when they're wandering to try and find a female, so it's for defence against vertebrate predators, which is why they have it. The females tend not to have it. So if you get lucky and get bitten by a female spider, you'll be okay down in Kosciuszko. It's only the males. It's always the males that are the most toxic. And I'm sure the females will agree with that.
Thanks, Glenn. This is probably a good note to end on, male toxicity. And yeah, we're out of time. So I'll now hand over to Francis to introduce our next presenter.
So thank you, Alan. Our next presenter is Professor Zheng-Xiang Li. Zheng-Xiang Li is a renowned geoscientist whose work has led to paradigm shifts in our understanding of how the Earth's engine works. This is important because it catalyses the formation of deep Earth resources as well as climate and environmental changes. He co-developed the dynamic supercontinent superplume geodynamic model, addressing the driving forces of tectonic plates. Please welcome Professor Zheng-Xiang Li. Thank you.
Thank you, Madam Secretary. Yeah. I also like to thank Dima Müller and Katie Grice sitting here, probably also Ellen Chivers in the audience somewhere. And some others who made it possible for me to be in this great hall and rubbing shoulders with some of the world's brightest minds, which is particularly important for someone from Perth. The world is the most isolated city. Anyhow, my topic is, I also like to thank many other people who support my career, and starting with my many team members, present and past, and my many national and international collaborators, my mentor, Professor Chris Paul, who is probably watching us from up there somewhere, yeah. And last but not least, my family, with my wife sitting in the audience. Yeah. Anyhow, my topic is a living Earth, and the topic is rather large, but I'm better known to be able to talk fast. Hopefully I can go through this. Yeah. And a living Earth, because Earth breathes as volcanoes, and the Earth reaches like human beings, and can do a lot of damage. And Earth even grows. Here is a picture of the Mount Everest, the world's highest point, almost 9 kilometers above sea level, and it's still growing by a few millimeters each year. This was caused by the northward bulldozing of the Indo-Pacific, Indo-Australian plate into Asia. But after all, to me, Earth is heaven. Yeah. But Earth wasn't always like that. 4.5 billion years ago, Earth first formed as a fireball, and quickly, as it cooled down, became a water ball, with a bit of land popping up out of water here and there, possibly as volcanoes. Then land grew, and the continents grew, and they create together, including becoming bigger continents and cratons, and from somewhere between 3 to 2 billion years ago, plate tectonics started. And for the second half of Earth's life, for the 2 billion years each, Earth started supercontinent cycles, what I call supercycle plate tectonics. And in between, the world becomes snowball Earth. The Earth become all covered by ice cap, yeah, which is rather dramatic. Accompanying this evolving Earth's surface was the, oops, it's not moving. Accompanying this surface evolution was changing in the Earth's internal engines. So at the beginning, 4 billion years ago, when Earth first formed, the main process was differentiation. It's a gravity-driven kind of layer cake formation. But then soon, after the Earth starting cooling down, the heavy stuff starting dropping down, and the hot stuff starting going up, you're starting the convection, kind of starting the remixing process. And then this process was aided by plate tectonics somewhere 3 billion years ago. And as the continent grows, the plate getting bigger, so was the convective cell size. And once you started the supercontinent cycles, you're starting the hemispherical scale convection, which dominated the process even today. So what I call the later part of this history called supercycle plate tectonics. This is what I'm going to focus on next. Along with the evolving Earth's tectonics are also the air we breathe. The air we breathe wasn't always like what we have now. So at the beginning, there was very little oxygen. So you can see from 4 billion years, that what was very little change until 2.5 billion years ago was a major oxygenation event, still not much compared to present day, and this maintained until 500 million years ago, as the explosion, the time of the life explosion, 500, 600 million years ago. And so life evolution also kind of take a long time to progress to what we have today. So earliest life in the record is what we have in the Pilbara, in Western Australia, 3.5 billion years old. Stromatolite. It's a single cell life, and possibly formed in hot springs, and probably associated with volcanoes. Actually, the same single life, simple life, and still live with us. And if you go to Perth, next time you drive south 7 kilometers, you find this kind of trembolite. It's one of the most primitive life on Earth, and still around us. And the life didn't really flourish on Earth until the great oxygenation 600, 500 million years ago. And we started to have multicellular complex life. Human beings really came in the very last minutes. Now we move on to the supercontinental cycle. So to ordinary people's eyes, the Earth is made of two types of surface. One is continents, which account for 1/3 of the area. The rest are covered by ocean. But in the eyes of geologists, there are different oceans. You can divide the Earth's surface by what we call the Pacific Ring of Fire. So the Pacific Ocean was a much older ocean, was a super ocean 200 million years ago, and the Atlantic and Indian Ocean was a much younger ocean, which wasn't there 200 million years ago. It's really during the breakup of the last supercontinent, Pangaea, those oceans was born. And the Pacific Ocean wasn't always there either. The Pacific Ocean didn't start to form until 700 million years ago. One older supercontinent, Rodinia, starting to break up. You starting forming the Proto-Pacific. And at the same time, there was an even older ocean outside of this Sebastian Girdle, this is Ring of Fire. So now come to the concept of supercontinental cycles. Everybody knows the supercontinent Pangaea, formed 300 million years ago, broke up 170 million years ago. The idea of Pangaea actually was the first kind of hypothesized by German scientist Wegener over 100 years ago, but wasn't accepted by the society until 60 years ago, in the 60s, 70s. And that's all we know about supercontinents until 35 years ago. So we learned in the last 35 years, there was more than just one supercontinent in the Earth's history. So there was an older one called Rodinia, formed 900 million years ago, broke up 700 million years ago. And before Rodinia, there was even older one, formed 1.6 billion years ago. So if we count the time interval between the supercontinents, almost exactly 600 million years. So you're starting to see a 600 million year cycles, kind of formation, break up, formation, break up. And if this cycle continues, we are due for another supercontinent in 280 million years in the future. So here I'm going to show you a movie which I produced a couple of years ago, and using all the information we have with the geology, geophysics, how Earth evolved in the last 2 billion years. So at the beginning, continental growth into possibly the first supercontinent, Luna, at 1.6 billion years ago. So Luna did a bit of gentle dancing, and that's Australia here. It didn't look exactly like what we have now. The Luna breakup from the next supercontinent, Rodinia, over here. So Australia is still here in the middle of Rodinia, changed the neighborhood a little bit, broke up. And that's the one snowball Earth time. Then from Gondwana, many people know about Gondwana, it's a half supercontinent. So keep moving on. That's one life, the explosion of life. Oops, I need to fast forward, push the wrong key. Come on. Here we go. Gondwana is going to collide with North America, we call Eurasia, with Baltica and Siberia, forming next supercontinent, what we know, Pangaea. Australia here with the Chinese bloc moving north, forming Asia here, and the Pacific Ocean surrounding the Pangaea. And Pangaea broke up at 180 million years ago. Here Australia, here India is breaking away, moving north, kind of going to bulldozing into Asia, forming Himalaya. Australia moving northward by about 7 millimeters per year. So what's driven the process? That's the dynamic process we think we're starting to understand over the last 30 years. We can even simulate in a supercomputer all the process of the plate, how the plate driving the mantle kind of subdivision, mantle convection, and which again break up the supercontinents. Here is Here is a map showing the combined the coupled surface evolution with the mantle structure for the last 2 billion years. And here, this one just showing the cycles, the supercontinental cycles, 600 million years, from 2 billion years to now, the Earth surface and the Earth dynamics. So I want to finish my talk and with a bit of fun. So if the Earth is going to evolve with 600 million year cycles, so what's going to happen next? There are a few ways to form next supercontinent called Amasia. America is going to join with Asia or Amasia. Okay, and one way is close the Pacific, with the Atlantic Ocean become the next super ocean. Here, Amasia, you got Australia in the middle, and the Atlantic becomes really big. Another way is close the Atlantic, the Pacific Ocean becomes super ocean again. Okay, a third way is you close another, so they join up on North Pole. And then we did a bit of computer simulation, and so what's driving the process of which way it goes, and the answer is the Earth cooling telling us there's only one way to go. That means the Pacific has to die. Yeah. So this is a cartoon, just a fun cartoon. Okay. So what might be happening in the next 280 million years? We keep drifting north, colliding with Asia. Then America drifting westward. We moving eastward a little bit, and so in 280 million years, we'll become the world center stage. Yeah. So the good things will become the world center. The bad things will lose a lot of coastal real estate. Yeah. Yeah. But I don't think that's for us to worry. It's a long way to go. Thank you. Yeah.
So thank you, Zheng-Xiang. Do we have any questions? Got time for one. There's a question just here, I can see. But I did like the analogy that volcanoes are just the earth breathing.
So I'm wondering why the cycle was always to go from multiple continents to a single continent, as opposed to, say, 2 continents. Is it something to do with the topology of the surface and the motion thing radial?
No, yeah, I think it's eternal dynamic. It's using an example like what they call it's the middle of Earth, the energy level, the viscosity, telling also the process. So what form of the supercontinent is the downwelling. When the core starts going down, they like a flow. They start together. They tend to join together and become a single flow. That's what draw all the continents together. So it's part of the process. Yeah.
Okay, I think I misread the clock. We could have one more. No? Oh, Lynn's got one. But I do like now he made the analogy to Middle Earth. It keeps getting better.
It's just marvellous to see these simulations and into the future too. In your terrific video that you made, you said you used magnetic sort of signatures. There must be other things you look at in the rocks to see who matches up with whom. Could you tell us a little bit more about that, please?
Thank you. Very good question. Yeah, you're absolutely right. The magnetic needle is what the record of Earth's magnetic field, which come 90 degrees out in the South Pole and go horizontal in the equator, then go 90 degrees north in the North Pole. So you imagine the fossil field trapped in rocks, you can tell the latitude of the continent at the time. And you using this to plot the pole out, you can draw a kind of DNA, the path, the floating path, a continent or continents together in the past. But to make what we made, the Earth's history, you need more than that. You need all the geology, all the fossil. For the last 500 million years, you have a fossil record. The fossil, all the geology, the mountain building, and everything we have. You saw one of the beginning of my animation, I listed some of the evidence we use there. Yeah, so we simply use everything we have. Now we try to utilize the machine learning, the AI, to help us to more objectively to reconstruct our Earth history. Yeah, thank you.
So let's thank Zheng-Xiang, and I'll hand over to Alan. Thank you.
Our next presenter is Professor Georgina Long. Georgina is an oncologist and scientist specialising in melanoma, who has led an extensive program of clinical trials, revolutionising the way melanoma is treated worldwide and leading to Australian government funding of 10 new melanoma drugs that significantly increase survival. She also introduced the first new checkpoint inhibitor drug into clinical oncology in over a decade. Her recent work is now revolutionising how operable cancers are treated and has been recognised by her being awarded the 2024 Australian of the Year, jointly with colleague Professor Richard Scolyer. Please welcome Georgina.
Thank you. It is a huge honour to be a Fellow of the Academy of Science and be surrounded by such esteemed colleagues who have such a depth and breadth across so many disciplines. It's wonderful. I'm delighted to be here to be talking about something I'm so passionate about. Before I did medicine, I did a PhD in organic chemistry and a Fulbright Fellowship to Scripps Research Institute in the 90s as a postdoctoral fellow there. So I'm very proud to be part of this scientific family. I do want to thank, though, the teams I work within. Particularly in medicine and in fact in science, team science is so important. At Melanoma Institute Australia and the University of Sydney and the hospitals that I work at as well, and also my family, my husband, children, my parents, all of those people I love dearly and my siblings. But in 1957, in Australia, the connection was made between UV and sun exposure and cutaneous melanoma. So today I'm talking about skin melanoma, Australia's national cancer. That association was published in a small rag called the Medical Journal of Australia by Lancaster and Nelson. The incidence of melanoma has risen ever since, and it still is rising in Australia, although the rise is starting to plateau. It's still going up, but not as much each year. It also is the most common cancer in our 20 to 39-year-olds in this country. So I'm delighted to be able to say the work we've done has made an impact, but we are still diagnosing it every 30 minutes in this country. The good news is, though, is that the mortality, the death rate from melanoma has dropped, and that's the yellow curve at the top. So if you look at 2014, and these are epidemiological graphs. This is very unusual. I'm not showing you survival graphs from clinical trials. This is epidemiological. We can see a drop in the mortality, and we expect that to head down towards 3 per 100,000. The impact has been enormous. On the right there are two of my patients, Adam and Josh. I've been looking after them for over a decade now. They were diagnosed with stage 4 advanced melanoma with secondaries around their bodies. And I treated them on clinical trials, and they're alive and well today with children and working full-time, full lives. They would not have survived 9 months when they were diagnosed over a decade ago if we had not had the clinical trials they participated in. This is Josh with his baby. That's a few years after he'd completed 2 years of treatment. And that's Mia. Her name's Mia, after Melanoma Institute Australia. And there she is. I think she's now 6. At a cafe with her parents. And on the left is Bert at 102. And at 101, he was diagnosed with advanced melanoma. And my colleague next to him, Alex Menzies, gave him only a couple of doses of immunotherapy, because the question would be, why are you giving drug therapies to a 101-year-old? Well, this 101-year-old was at home, independent, living on his own, and he had a lot of symptomatic metastases. Only 2 doses melted away, and I'm very happy to say he lived to 105, at home, independent, because he had a full and a very high quality of life. So I'm now going to be switching and talking about optimising cancer immunotherapy, because we do have a long way to go. Currently, where we are is probably equivalent to the 1960s and chemotherapy. So there are a few things I want to touch on and how we can do this across cancer. Immunotherapy, particularly checkpoint inhibitors, are now the most used drug therapy in cancer. Just to touch on the staging in melanoma, and staging of solid tumours and cancer is very similar. Stage 1, 2, and 3 are what we call early stage cutaneous melanoma or early stage cancer. And stage 4 is what we call advanced cancer, and that's where a patient has secondaries. Now, stage 1 and 2 is just the primary lesion. Stage 3 is where it's spread to local lymph nodes, and stage 4 is the distant spread. In Australia, more than 90% of melanoma is early stage, and in fact, the earlier it's detected, the more curable it is with simple surgery. Most people in this country, so that diagnosis every 30 minutes, most of those are stage 1. Less than 10% is stage 4. About 50% of people who are diagnosed with stage 3 and have surgery only will go on to get stage 4 melanoma. And about 35 to 45% of the high-risk stage 2 after surgical resection will go on to get stage 4 melanoma. The two areas where we've made the greatest leaps and bounds in melanoma and also in other cancers, having done the work in melanoma over a decade ago, are the BRAF and MEK inhibitors. These are targeted therapies. About 40% of cutaneous melanoma has a BRAF mutation within it that we can target with these oral tablet drug therapies. And the checkpoint inhibitors, particularly anti-PD-1 checkpoint inhibitors. You can see a patient with a hemithorax with the yellow circle, full of melanoma that completely disappears within a few weeks, actually. And on the right is a patient with lymph node metastases and liver metastases completely disappeared. He's still alive and well 12 years down the track after immunotherapy on a clinical trial. Very different. The targeted therapies target the melanoma cancer cell directly, so it's direct cancer cell kill. However, checkpoint inhibitors do not target the cancer directly. They target the immune system, particularly T cells, but also other cells, and get the CD8 T cells to kill the cancer cells. I'm not going to bore you with too many Kaplan-Meier survival curves, but I think this represents where we are today with melanoma in terms of the drug therapies. I do not have chemotherapy here. If I did have chemotherapy here, you would see a survival curve with a 12-month survival of about 25%. So this is the first checkpoint inhibitor we used in purple. But I just want you to look at the orange curve at the top. That is our best treatment, our most effective treatment. 2 checkpoint inhibitors together with a 5-year overall survival of 52% and a 6.5-year overall survival of 49%. But we're getting so good at giving long-term durable control that we no longer look at the overall survival, we have to look at the melanoma-specific survival in advanced melanoma. And when you look at the melanoma-specific survival in red, you can see that it's much higher at 5 years. It's 57%. People are living long enough to die of other causes. However, the problem's not solved. We still have 44% of patients dying of metastatic or advanced melanoma. And what we learn in melanoma, we can take to other cancers. This is another patient of mine, Adam, who died within a few weeks of his stage 4 diagnosis. He had been treated for stage 3 melanoma with surgery followed up by drug therapy. So the question is, what are we doing for that 44%, and what can we learn from that for other harder to treat cancers? So I just want to touch on 4 areas that we're really focused on. Optimizing the current immunotherapy by using it in earlier stage after surgery. That's called adjuvant treatment. That improves the recurrence-free survival, so decreases the risk of recurrence by 45% compared with just surgery alone. We've now shifted immune therapy, particularly before surgery, just shifting the same drugs forward. We reduce the risk of recurrence, death, or progression by a further 70% compared with giving the same drugs after surgery. We're working on minimizing toxicity, because if we have too much toxicity, too much immune stimulation, we then have to suppress the immune system, and that is bad for the cancer and survival. And we're doing that by using biologics that target different toxicities very specifically rather than a broad immunosuppressant. And we're learning to use these immunotherapies very differently to chemotherapy, not with these dosing intervals that are done based on the cell cycle, but more on reading the immune system. And so this means you may have variable cycles, you may only need 1 or 2 doses, it's not given at a strict regimen. And lastly, from what we learn with the bad melanoma, we can apply to really hard to treat cancers that are traditionally considered to not have an immune microenvironment that would make it treatable with immune stimulants. And a good example of that is my colleague who was diagnosed with GBM, but it's very early still. We've got some fabulous lab results that are really exciting. But other cancers too, we're now using immunotherapy. There are many immunotherapies I'm working on. We have about 20 clinical trials that are active, from T-cell engagers dragging the immune system into the tumour, mRNA technology, not just personalised cancer vaccines, but delivering drug therapy into the cancer cell using mRNA technology, cell therapy, and what we call antibody-drug conjugates, delivering a payload into the cancer. We're now predicting poor outcomes. We're using this in clinic now, where we use genomics, we use the patient clinical profile, the tumour immune profile, as well as the gene expression profile to predict whether patients will respond to our current immunotherapies or whether to put them on a fast track into clinical trials. And this is working very well. So just to finish off, the survival in advanced melanoma used to be 5% in 2009. It's now 55%. But we have to get to 0 deaths from melanoma. But the best way to do that is prevention, stopping glamorization of tanning, being aware of how to be sun-safe in our sports across this country, at the beach. And that photo on the top right was only taken a month ago when I was competing in a triathlon, actually a duathlon in Townsville at the World Championships. And that is a friend from, or part of the Australian team. And look at that burn. So we've got a lot more work to do to prevent melanoma, and it can be done, and that's the sun safety message. I want to thank patients, their families, the teams I work within, and my international and national colleagues in cancer research. Thank you.
Yeah, thanks, Georgina. What an inspirational story, isn't it? Questions?
Great talk, and congratulations on your election to the Academy. I just am interested to know about the initial detection of melanoma and how effective is that, given that, you know, from personal experience, you go and see a skin specialist, they give you a visual check. How effective is that in actually detecting those first onset of melanoma?
That's a great question. So with the right expertise, and I think we're pretty lucky in Australia, most of our general practitioners, our dermatologists, they're very well aware of melanoma. And there is a figure that can give you a measure, and that's the benign to malignant ratio. So how many times is someone cutting out something that ends up being benign and not malignant? It is experience, it is knowing the tools. The detection is not perfect, the sensitivity and specificity, but it is operator dependent. So we use things like dermoscopy. I'm not a dermatologist, I'm a medical oncologist, so I see patients after the horse is bolted. But dermatologists are very good and well-trained. GPs know how to use those tools to up that sensitivity and specificity. The good news is to support the humans doing the initial diagnosis. AI is becoming very powerful. But the software of, taking photos of lesions and sending them in to learn what's malignant, what's benign, is still not well tested, and that's some of the research we're doing. I haven't touched on it today, but as a team at Melanoma Institute Australia, we work at prevention level. In fact, it was work at MIA that showed that sunbeds caused melanoma, and now they're banned across the country. But diagnosis, early diagnosis, so there's a lot going on in that space. But just a public health message, though, we're introducing a screening program for people at high risk of melanoma. The best thing people can do, besides primary prevention, is know the skin you're in. And if you see something changing, it doesn't have to look pigmented or a mole-like, go and see a doctor. But you've got a great question there, is who is that doctor and can they do the diagnosis. In Australia, we're very lucky. People are very well trained. 20% are tricky. 20% are really tricky lesions to diagnose.
Georgina, that's a fantastic talk. I just have this question in terms of PD-1 therapy, and we have been used for this end-stage melanoma, but you have mentioned there's a screening program to identify high-risk group. Do you think at some stage, if we can really understand the balance between the benefit and the toxicity, can we use the PD-1 therapy as a preventive therapy for this high-risk group?
Another great question, and I'll give you my short answer, absolutely not. So when we look at anti-PD-1 therapy in our patients who have advanced and early stage disease, we're using it in stage 2 and 3, they still are developing new primary melanomas. Not at the same rate as they would have, but they still do develop primary melanomas. So it wouldn't be a preventative therapy based on the science and what we're seeing. Also, I do think it's not a sort of treatment that you would want to give someone just to prevent a primary melanoma.
One last question.
On extraordinary work. It's just so exciting to see, and science underpinning it all. Most melanomas are skin ones, but there are other ones from the eye and the brain and the like. Could you say whether your therapies were working for those as well, please?
Sure. So when melanoma is in the brain, it's a metastasis. So it's come usually from a cutaneous melanoma and spread to the brain. And in fact, it was our trials at MIA that are designed by us where we showed that combination immunotherapy is very effective in melanoma that's spread to the brain. In fact, a cure rate, dare I say cure, of about 55% in those patients. The two melanomas that are not skin melanoma that you mentioned are behind the eye, so ocular or uveal melanoma, very different beast to cutaneous melanoma. We're working in that space, and there are some drugs that are effective, but it's a different cancer. It just shares the same name, biologically very different. The other one is mucosal melanoma, so melanoma that arises from the inside mucosal lining. And again, we're working in that space too. It is responsive to some of the drugs we use in cutaneous or skin melanoma, but not quite as responsive. And so that is another area where we're trying to, and we're getting there on how to get the immune system to recognize these very poor immune environments, low tumor mutation burden, cancers that aren't displaying a lot of weird, crazy antigens or peptides that the immune system can hang on to.
Please join with me thanking Georgina one more time. And I'll hand over to Francis to introduce the next presenter.
So thank you, Alan. It's my pleasure to introduce Professor Budiman Minasny. Budiman Minasny is acknowledged for his groundbreaking soil mapping and modelling techniques to unlock fundamental new knowledge urgently needed to protect and enhance soil carbon stocks and to sustain agriculture and ecosystems worldwide. Please welcome Professor Budiman Minasny.
Thank you, Francis. Thank you, and it's a real honor to be elected as a fellow, and I would like to thank my my sponsor and Professor Alex Bradley, and also my colleagues at the University of Sydney, including Kathy and Eddie Holmes. So I'm a soil scientist. I'm going to talk about soil, and when I was young, when I was little, my mom always told me don't play on dirt. But I grew up studying soil science at the university in North Sumatra in Medan, Indonesia. So when we study soils, we like to dig up the soils and look at the soils and characterize the soil, look at different colors, feel the soil, feel the texture, and because it tells us something about the very fine. The very top layer of the earth, because this is what is going to what supports us. And as I'm doing my Master of Agriculture at the University of Sydney and continue with my PhD, and then I start to learn and we start to discover that the soil that we dig up and try to characterize is in fact, it's one of the most important component of the ecosystem, of the terrestrial ecosystem. And it is one of the most important component that will help us if we want to study or if we want to address the existential challenges of the world. We know that the existential challenges it's global and it's everywhere and it's a complex system. But in order to tackle, for example, food security, water security, climate change, biodiversity, ecosystem, and energy security, we also need to tackle the soil itself. And in fact, soil, it is the most according to me, it's the most important one, but the one who connects to all these existential challenges, because 95% of our food is still grown on soil, and soil is in fact store the most fresh water in the terrestrial ecosystem on the land, and it's the only source of water that the plant can take. And in fact, soil, the amount of carbon stored in the soil is two times more than if you add up all the biomass, all the plants on the earth and all the carbons in the atmosphere. And more than 56% of our biodiversity live on earth, and so much more. But within the soil that we see that it's if we consider as uniform, but it's not uniform, it's composed of the mineral components and the organic components. And it's these interactions between the mineral and the organic components that form all this distribution of all this porosity, different size porosity that helps, that makes it works, that it's going to support us in water regulation. Different pore size, that means that the different amount of water can be held by the soil, and it can transmit the water from the atmosphere to the soil and to the groundwater. It is also storing lots of carbon, and in fact, which I'll talk about later, a small amount of carbon that it can store can effectively mitigate or draw out carbon from the atmosphere. It is one of the most diverse system on the earth because of all these different porosity that it holds, that the nutrient that it holds, that the microbes and the plants and the interactions that can make the soil living. And what we've been doing for the past 20 years at the soil science at the University of Sydney is we try to understand, because the soil, the way the soil vary across the system, vary across the land, the continent, and the globe is not random, but they obey some principles, and that what we want to try to understand is what we can model, what are the controlling factors of that make the soil vary from one place or the other. And if we can model that, that means that we can map them and we can understand how they are distributed in the world, and that we can understand how it changes over time. And when we can understand whether it's going towards a better or positive or negative, then we can monitor it to see how we are tracking it. And if it is under degradation, that means that we can regenerate, and if we can forecast what's going to happen to the systems. So one of the product that we generated is that because soil itself is not randomly distributed, from all of these existing soil observations that the surveyors have collected for the past 50 years, we try to get all those data and try to put a bigger picture of the understanding of how the carbon in the soil, the organic matter that makes the soil functions distributed across in Australia and across the world. So this is part of the terrestrial ecosystem research networks, and we try to make maps of a soil organic carbon towards all Australia. For example, this is our farm in the Nerilie in Nerilie. So the farm is around 22,000 hectares. So if at the first release that we make a map of at the 90-meter resolutions, that we can see the distribution of the carbon in the farm. But we further now with the improvement in the computation, improvement of the data, that means that we can even pinpoint to 30-meter resolutions. That means that this kind of information is ready for use for farm management and for carbon farming initiative and so on, because now we can have more details to understand that how the carbon, how the soil vary in the landscape to enable management. So, but the soil itself is not a static variable, it changes with time. And the variables that change always with time is the soil organic carbon, the amount of carbon in the soil. That is an indicator of the fertility of the soil, but it's also the indicator of how the soil functions. If the loss of carbon in the soil, that means that it will be less aggregated, it will be more prone to erosion, and that will have that will lead to land degradation. To understand that, we collected soil samples because we cannot, because the way carbon change in the soil is not instantaneous, it's instantaneous. It takes a lot of time to let it equilibrate. So in order to understand how the carbon change because of our human activities, we go out and sampling in a way that the similar soil type we have met before. We selected the sites that are still under remnant vegetation, which we call as a genosoil, as a soil that are developed naturally under its condition. We call it a genosoil, and soil that are under modified human practices, for example, under cropping or under different land uses, which we call phenosoil. So for the same soil type, we collected the soil that are under natural vegetation and under human practices or human disturbances. And what we found is that the amount of carbon compared when the soil is under natural vegetation decreased significantly. The largest decrease is under irrigated cropping, followed by non-irrigated or dryland cropping and under pasture. So it's consistent throughout the landscape that we see that there has been a decline in the soil carbon throughout the landscape. So under improved pasture, many soils have lost about 10 to 20% of their soil carbon since they have been converted. And under cropping, there are losses from 30 to 50% of soil carbon. And this trend is relatively universal. It's found in Australia, it's found in the US, it's found in Asia, different parts of the world. That means that the amount of carbon that in the soil has decreased, and that carbon, we know, when it's released to the atmosphere, it becomes CO2. So that is part of the greenhouse gas. And that means also the soils under agriculture, there are potential to store more carbon in the soil. So this is in Australia, but how about globally? How do we see ourselves at the contribution of carbon globally? So mostly in the global carbon budget, we see that most of the, more than 70% is due to fossil fuel emissions. But some 10% is about this part is about land use change. So how is this land use change going to contribute to soil carbon? So because in the global carbon budget, we know about the loss of carbon through fossil fuel emissions and deforestation, but we don't know how much of it is changing in the soil carbon, whether it's going to increase the carbon through photosynthesis or it's going to release the carbon. So we did a modeling through global modeling. What we're trying to say is that because we can now track the changes in land use at different parts of the world, because of the change of land use, we know that mechanistically it's going to decrease the amount of carbon in the soil. And for example, in Brazil, working with colleagues in Brazil, we know that the clearing of the Amazon is not just removing the biomass from the above ground, but it's also releasing or decreasing the amount of carbon in the soil. So what do we found? We found that there's still deforestation rates for the past 20 years is around 10 million hectares per year. And the annual loss of that carbon in the soil is around 2.2 petagram or billion tons of carbon per year, which is, if we look at all the overall carbon stock, it's not that much. It's only 2 per mil or 2 per 1,000, but it's actually 20% of the fossil fuel emission when we compare that. That's still huge. So agriculture, the way we practice it at the moment, still a big contribution of the global CO2. And sorry. So, and if we compare it with the potential of the soil to store carbon, it's still much less than the amount of the carbon that is released through our activities. It's not just the carbon that is lost through land use change, but it's also soil is releasing methane from paddy field production and also nitrous oxide productions from fertilizer. So soil, we need to we need to have ways of restoring this the soil in the carbon in the soil. It's not just for climate change, but also so that it can improve the functions. Are there ways that we can increase the multifunctionality of soil through improving our management? Of course there are. Australia already practices crop residue retention and reduced tillage, but the one that we haven't done a lot is cover crops. That means that in between the seasons of crops, that can we add crops that are increasing the biomass. And in fact, our PhD students show that we can improve the soil system by additional improving the cover crops. So this graph is showing the slaking index. That means that if the soil is wetted by the water, if it slakes a lot, that means that it's going to increase the erosion. But by introducing cover crops, we are able to reduce this slaking. Okay, so one final one.
Just one.
Just one. So, because the more we study about soil, the more amazing things that we found out. So, because in our building, there's a Professor Eddie Holmes, who is a virologist, and he told me one day that he wants to study the virus in the soil. So I said, okay, let's do what's the virus is doing in the soil, and we collected samples from our farm, and indeed that within our farm in the University of Sydney, we can identify 1,000 novel RNA virus in the soil, which we don't know what are they doing and what are their functions yet. So there's still much more that we need to learn about. Thank you very much.
Thank you. So we're really glad that Budiman was able to finally play in dirt. But I'm going to punish him for going over, and I'm not going to allow him to have any questions. But please save them for lunch, because you are standing between us and lunch, and we've got one more speaker. So please thank Budiman again. Thank you.
Our last presenter before lunch is Professor Hrvoje Polo. Hrvoje is a biochemist and stem cell biologist who has made seminal contributions to our understanding of cellular reprogramming by developing and combining cellular models and genetic techniques and computational approaches. He has also made major contributions to the embryo modelling and stem cell fields. His work has driven the translation and expansion of reprogramming advances into additional research areas and industry. Please welcome Hrvoje.
I would like to start by thanking my proposer, the supporters, and all the members of the Academy for making me a fellow, and it's a real honor to be among you. So I have so many people to acknowledge and to thank for me being here. I asked the Academy to give me another 15 minutes, but they say that you get hungry. So I put them all in one photo. So this is all the people I want to thank. I especially want to thank, of course, my parents, my sister, my uncles, my aunties, my cousins. I drove them crazy when I was a kid. So I really thank you. I want to thank all my friends of life, my friend from the Faculty of Biochemistry, of Albert Einstein when I was doing my PhD, and all my colleagues through this year. Especially thanks for my family that they put up with me every day, and they actually allow me to be a scientist. But I have to thank my mentors. I had 3 amazing mentors, Susana Jesui, Pablo Evelson, and Marina Travasio. During my undergraduate, they introduced me to academic science. Ari Melnik was my PhD supervisor, and Konrad Hockerlinger, my postdoc supervisor. I couldn't have found better supervisors than them too. And I want to thank Christina Mitchell, Ross Koppel, and Angel Lopez. Since I came here to Australia, they support me and they mentor me in becoming a group leader, which was very important. But I will definitely not be standing here if it was not by my colleagues and my lab. These are 3 snapshots of my thank you slides, acknowledgement slides. I think I captured all of them. I told them this the other day, and I will tell them this now publicly and in the internet. Without you guys, I will not be standing here. I'm just a reflection of the hard work that you put every day. So I really thank you all. So I work in self-aid. So let's start from the beginning, development. So as you may know, or you will about to learn, the oocyte gets fertilized. We give rise to the zygote. The zygote keeps differentiating. And then this will become a blastocyst. The blastocyst is the early embryo. It's at day 6. It will implant, and after implantation becomes a 3-laminar embryo, and if everything goes well, you get a beautiful baby. If you are lucky like me, this happened twice, and you get a beautiful twin sister. And the amazing thing about my twins and all of us, and honestly think for 1 second on this, is we are all made of many hundreds of different cell types, but they all came from one cell. So definitely all the information to make all the hundreds of different cell types in our body was in the zygote. But what happened with that information during development? John Gordon answered this question many years ago by taking the nucleus of an adult cell, putting back into an enucleated egg of a xenopus, and he was able to rederive an entire organism. And with that, he demonstrated many things. One is genetic information is not lost during development. The corollary of this is every cell of your body, of the trillion cells that you have the capacity, has the potential to make you again, which also means that every cell of the body has the potential to make any other cell of the body. That's amazing. If you really think about that, it's amazing. And then the other thing is that the genetic information is not all information that you have. Otherwise, all your cells will be the same. And with that experiment, he basically founded, in my opinion, the field of epigenetics, that at the same time Conrad Warrington was proposing, which was these forces. He was proposing this famous epigenetic landscape, where he said that there was these forces taking the genes of a cell and basically making them more active or less active. And the idea was a cell, for example, in the inner cell mass of the embryo will get, all the genes will get these forces, and they will make them differentiate that cell until you get all the mature cells. And this landscape is very famous, but actually he drew how can that landscape be made of? And what he proposed was that there was these lines pulling the genes and these pegs pulling the lines. And actually, 60 years later, we realized that this is quite accurate. The lines are all the chromatin modifications that we always talk about, histone modification, DNA methylation, etc. And those pegs are the transcription factors that we direct these chromatin modifications to shape the landscape. So therefore, if we can know which transcription factors do this work, we should be able to control cell identity by modeling, by changing the landscape. And that's nuclear reprogramming, which is we put some transcription factors and we, for example, can reprogram B cells into macrophages, or the most common class type of reprogramming, fibroblasts into induced pluripotent stem cells. And furthermore, this landscape, these cell transitions that are regulated by these changes in the landscape, not only affect development and differentiation, reprogramming, but actually aging is a process of this kind, and you can even argue that disease is a project of this kind. So therefore, because we are interested in answering how this landscape change in cell fate, we've been working in absolutely all these aspects of biology, which is actually one question, how the landscape change to produce cell fate changes. So we have been working in how pluripotency is maintained, we have been working in differentiation and development, in disease from lymphomas to Alzheimer's, in aging, and today I will talk a little bit about reprogramming. So in theory, during reprogramming, we imagine the cell go up this landscape and become induced pluripotent stem cell. But actually what I think that we should imagine is something different. The landscape is changing inside the cell, and is more of that taking the carpet out of the cell. And because of these dramatic changes in molecular events, is that there is epigenetic memory. And this is something that Ryan Lister and myself, we co-discovered independently, meanwhile we were doing our postdocs. And I think that the beautiful part of the story is that when we came back to Australia, we worked together for the last 10 years trying to understand the process, and when we understood, we were able to find a way to solve this process. And by understanding nuclear reprogramming, we also realized that it's not an stochastic event. Reprogramming happens in a very clear series of molecular events. It doesn't matter from which cell you start, they all follow different molecular events, but very clear. And because we have such a good understanding of the mechanism, we were able to come and postulate new transcription factors way of regulating cell identity. This deep understanding of the reprogramming process also makes us realize that during reprogramming, not only the pluripotent cells were made, another type of cells, which are the trophectoderm genes or networks, were getting activated. The trophectoderm is the cells that will go and make your placenta. So we were able to capture these cells during reprogramming. We call it induced trophoblast stem cells. And then with those induced trophoblast stem cells, we can create placenta in vitro. And now we have an endless source of placenta cells in vitro that, for example, during the COVID pandemic, we were able to use to model and predict much ahead of time that the virus was going to be able to infect placenta cells. We also realized that when you just leave the cells that are being reprogrammed and you put it in 3D, they start to self-organize into these structures that are blastocyst-like structures. We call it blastoids, and they became the first models, in vitro models of the early human embryo. And having such a powerful now model that is scalable and tractable, we can now go and try to answer questions about what happened during those initial 2 to 3 weeks of implantations of human development. And this basically opens a window into the black box that the early stages of development in human are. So what we are going to do in the next 10 to 20 years. We will still working in this, trying to understand how a cell becomes another cell. You saw today many of the talks talk about this. Basically, it's not only important for the things that I discussed, it's important for sexual dimorphism or sexual selection, and we are going to keep working in understanding the epigenetic mechanisms, cancer biology, neurodevelopmental disease, degenerative disease, early embryogenesis, and even marsupial biology. Because I like to understand this, and also because this is what the people in my lab love to work. So why they will not be able to work on this? Yes. So I will finish with one summary slide that I've been using for the last 10 years, that is basic research matters. We didn't know that we were going to create these models of placenta or early embryo. We were trying to understand a very fundamental mechanism. And by understanding that, that empowered us and gave us the tools then to use for all these different, in this case, medical applications. So for all the young researchers in the room, please do not shy away of doing fundamental research. And with that, thank you.
Thanks, Jose. Look, I know that you're all really hungry for questions, but I only allow 2. So who'd like to ask the first one? No, well, I will do that. I saw that you you had marsupial biology there for the future. Can you say a little bit more about what you're doing there?
So, and one of my students, Ellie, we are trying, because we can generate models of the human embryo, we decided that why not to try to generate models of marsupials, of embryo marsupials. Since marsupials have this amazing property that so during development, there is a moment where the embryo starts growing and all the nutrition and oxygen comes by diffusion. And then as eutherian mammals, we have a placenta, we connect it, and that allows us to keep growing. But marsupials solve it in another way. They are just born and they just go to the pouch. So in theory, it will be amazing because we are able to make a good model that becomes, rather than a model, a real embryo, eventually. We could make an entire organism completely in vitro. First that. Second, because as you may not know this, but many marsupials generate a placenta, but a very short-lived placenta. So it's very difficult to study. So with this, we think that we can study those properties of that 1 day to 2 days placenta. So we thought that was a great model to understand mammalian development.
Jose, wonderful. Basic science really matter. Let's really agree with you. And the basic science is about ask the question. The question start all the following investigation. So can you just give one fundamental question you think is matter for your future research? You are talking a lot of things you can do, but what's the fundamental question is matter?
Thank you, Dee, for such a question. Different people have different questions. In my opinion, I found amazing that the cells remain the cells that they are through life. Yes, when one transcription factor that goes out of whack, the cell will convert into another cell. So this is what John Gordon called the resistance to change. The fact that your body maintains the cell identity of every cell with the potential to actually change constantly back and forward is an amazing thing. And this is through cycles of division, cycles of the immune system coming and playing around, but the cell remains what it is. So for me, I call this elasticity of the cell, how much you can perturb a cell until it doesn't come back to where it was. That's a fascinating question because I think that actually holds, from a mechanistically perspective, it's an amazing question to answer, in my opinion. And from a, for instance, medical perspective, I think that holds the secret for regenerative medicine, how much you can change and then bring it back to what actually the first state. So I think that that's a key question in biology.
Thank you, Jose. Please join me thanking Jose. So it's time to break for lunch. We reconvene at 2:30. But before you all go, please join with me in thanking all the presenters for such a wonderful session.
This farm near the New South Wales city of Wagga Wagga is a long way from war-torn Ukraine.
These varieties here, they're all spring canola, and in Australia we mostly grow spring canola.
But it's familiar territory for Marina Zhu and Svetlana Omelchuk.
Big surprise for me that we have a lot of in common
things in agriculture in Ukraine and in Australia. It's really was like, you know, Australia was something very fine, different from us, and when we are here, we look and wow, we have the same thing. So we are very interested in.
Marina and Svetlana research canola at the Ukrainian Scientific Institute of Plant Breeding in Kyiv.
For both countries, it's an important export crop, and for the globe, countries like Australia and Ukraine that basically provide the world trade of that commodity, what happens in those countries, in both of our countries, is important to world trade.
And it's what's happening in Ukraine right now that has brought these young scientists to Australia. When war broke out, the US-based Breakthrough Prize Foundation teamed up with the Australian Academy of Science to ensure Ukrainian researchers could continue their work.
Ukraine is actually a powerhouse, particularly in genetics and in plant science, so it's important for us to keep those links open. But whatever helps Ukraine also helps Australian science and international science.
Like everything, the work of scientists has been seriously interrupted by the conflict.
It's impacted all spheres of our life, not only science, because you always are under stress, you're always worried about safety of yourself, of your family, your friends, and it's hard to plan your experiments and projects when you think just how to survive.
Але життя змінилося, але ми якось продовжуємо працювати. Дуже вдячні всім, хто нас підтримує, всім країнам, також Австралії, які надають допомогу.
One of their hosts in Australia was CSIRO agricultural scientist and fellow of the Australian Academy of Science, Dr. John Kierkegaard.
They told me sometimes they're travelling along roads which have mines. It takes them hours, 10 or more hours to travel safely to see some of their field experiments. Quite challenging, and I found them remarkable, but in their pragmatism and determination to sort of keep the work going.
Dr. Kierkegaard had hoped other Ukrainian scientists would join the Australian trip, but fighting-aged men have been barred from leaving Ukraine. Australia has made sure they still have support, including remote access to scientific infrastructure, including supercomputers, microscopes and telescopes.
Science and technology has clearly underpinned the growth of canola as a crop in both countries. The only way to sort of stay ahead of that game is that scientists around the world collaborate, share ideas, share information, and that's what conferences like this and exchanges like this can really promote.
Ukraine knows science will play a major role in rebuilding the country after the war.
And it's all about the human capital. We can rebuild buildings, right? It's not a problem, but we need to keep our human capital. It's our competitive advantage, the talent that we have. And we need to nurture the talent. We need to help the talent to grow, develop, and become better. And I think this will be of huge contribution to Ukraine's reconstruction eventually.
The support of Australia and Australian people are really important for us and for Ukraine now, because I know it's important to feel that we are not alone in this need. And we really appreciate all that you do for us.
Distinguished Professor Brajesh Singh says there's a very simple reason why we should all care about soil.
All terrestrial life is dependent upon the soils to sustain it.
A single teaspoon of topsoil can contain up to 6 billion microorganisms. That makes soil one of the most biologically diverse materials on the planet, and one that is critical for plants, including most of the world's food crops.
They are entirely dependent on the soil microbes to provide them the nitrogen, the potassiums, the phosphorus and other chemicals the other elements that it needs to grow.
Professor Singh is a world-leading soil ecologist. His work has helped shed light on the highly complex nature of the ecosystem beneath our feet and how that ecosystem is adapting to climate change.
All the data we have today suggests that soil biodiversity is vulnerable to the climate change. If you change the soil biodiversity, if you reduce the soil biodiversity, the service and the functions they provide will be reduced.
Professor Singh helped edit the Global Soil Biodiversity Atlas that brought together the findings of more than 150 researchers across 26 countries. It was a major piece of work, but scientists think they've still only isolated around 1% of soil microorganism species. Professor Singh believes countries, including Australia, should keep track of soil biodiversity as part of their global reporting obligations.
You cannot deliver a solution for a global challenge without high-quality science.
His own high-quality science is helping farmers to implement sustainable approaches and minimise the impacts of climate change. That includes the development of patented technologies to detect a soil problem that becomes more common as the weather warms, food and environmental pathogens.
We need to understand where they are distributed so that our own human health is managed.
Professor Singh believes all soil ecosystems are now facing similar threats.
In the natural ecosystems, you're looking at how naturally planted microbes interact. But the pressures, now we're putting all sort of pressure there as well. We're putting climate change, we're putting pollutions. Not many parts in the world where there is no chemical pollutions.
He says becoming a Fellow of the Australian Academy of Science is an unexpected honour and one he hopes will help make a genuine difference.
We need to come together, not just as a researcher or the scientist, but as a society, to tackle these issues more vigorously than we are doing at this moment. Because unpredictability of its consequences means we can't plan. And if we can't plan, the repercussions can be more severe.
Professor Georgina Long grew up believing all of us can have an impact.
In my family, it was what you were passionate about, what you were good at, and how you could make a difference. How are you? Come on in.
That mission to make a difference has seen her become a medical oncologist.
So all of that's normal.
And one of the world's leading researchers of melanoma.
Melanoma is Australia's cancer. We have the highest incidence of melanoma in the world. When I went into it, there were no effective drug therapies. It was pretty depressing.
Professor Long would go on to lead an extensive program of clinical trials.
I'm just selecting my antibody.
Resulting in 10 new melanoma drugs, including immune checkpoint inhibitors that help T cells recognize cancer cells as an enemy.
So I lived through this incredible journey of all of a sudden, patients were doing a Lazarus. They were dying and then they were living. High-dose ipilimumab.
Her latest trials have centered on combination immunotherapy targeting multiple checkpoints. The results show the approach categorically improves survival rates.
And as time goes by, we now know that about 50% of people with melanoma that's spread, so advanced melanoma, are having long-term durable control of their cancer. Just short of a cure. We're not brave enough yet to say cure, but I'll say it, it's a cure.
Her research saw her become Joint Australian of the Year with pathologist and fellow melanoma researcher Professor Richard Scolyer in 2024. When Professor Scolyer was diagnosed with an aggressive form of brain cancer known as glioblastoma in May 2023, Professor Long was determined to intervene.
This problem was too big, and the grief was so great, and I wanted hope for Richard.
That hope would be found in Professor Long's game-changing research into treating secondary melanoma tumours in the brain. Specifically, the work that she led with her colleague in the Netherlands showed that immunotherapy could be used to shrink a tumour before surgery and improve outcomes. So could the same also be true for glioblastoma? Professor Scolyer consented to the treatment, which involved a pre-surgery immunotherapy regimen devised by Professor Long and supported by experts worldwide.
The ideas made sense. They were grounded in experience. Of course, there were many unknowns, and they were grounded in science, and that gave hope.
A year on from his diagnosis, Professor Scolyer is cancer-free, and Professor Long is working to publish their results and establish clinical trials based on the treatment. Professor Long says that's the beauty of science.
Whatever problem we're faced with that really, really matters to humanity and to our planet and to the universe,
it's going to be in science, the answer.
A message she can now share as a Fellow of the Australian Academy of Science.
For Professor Zheng-Xiang Li, green tea is more than a drink. He credits it with helping him to think.
When I'm doing research, we sometimes need a great ideas. We need to be relaxed in some way. And tea probably is one of the catalysts, in my life, I believe.
The thought he puts into preparing tea reflects his broader approach to research, considered and meaningful with a desire for impact. Professor Li is an antimicrobial pharmacologist on a mission to combat superbugs, strains of bacteria that have become resistant to almost all current classes of antibiotics.
This means in the clinic it's very difficult to identify an effective antibiotic to use in patients.
Superbugs are on the rise as bacterial cells develop ways to outsmart antibiotics.
For example, they can degrade antibiotics, they can modify the antibiotic target to minimize the bonding of antibiotic molecules with the target, and they can also pump out the antibiotic outside the bacterial cells.
The World Health Organization has identified antibiotic resistance as one of the 3 greatest challenges to global health. But it's a challenge that many of the world's major pharmaceutical companies aren't tackling.
Big pharmas have left antibiotic market because they're minimal profit.
So Professor Li's team at Monash University's Biomedicine Discovery Institute is taking up the fight in 2 major ways. The first is to improve the way we use antibiotics already available on the market.
We try every effort to optimize antibiotic use in patients.
That means using just the right dosage regimens in individual patients to treat the infection while minimising drug resistance and toxicity. His research led to the first scientifically based dosing guidelines for last-line antibiotics known as polymyxins.
And that's very exciting because that have been widely adopted by hospitals around the globe and have changed clinical practice greatly. That's very rewarding.
Professor Li is also developing novel peptide antibiotics to treat deadly infections caused by bacterial superbugs, something made possible by 2 decades of fundamental research undertaken by his lab.
We took the drug from concept in the laboratory through the drug discovery pipeline and then get into clinical trials. We can see the true value of our knowledge and also program can create for global health.
He says he's deeply honoured to become a Fellow of the Australian Academy of Science and wants to use the platform to advocate for rapid clinical translation of breakthrough biomedical discoveries in order to target major global challenges.
Professor Willie Zwanapul is a world leader in computer systems research. His pioneering work in operating systems and distributed computing underpins much of today's cloud computing, work that began with his PhD at Stanford University in the 1980s.
The PhD was based on the internet. It was to see if we could, this is going to sound terribly mundane now, but in those days it was a big leap forward. It was to see whether we could access files over the network.
At the time, local disk storage had a long list of reliability issues, and creating backups was cumbersome and time-consuming.
Most notably that they would crash quite often.
His thesis demonstrated the advantages of a networked storage system, which was adopted first by Sun Microsystems and later across the industry. Professor Zwanapul says witnessing the commercialization process greatly influenced his outlook on research.
It evolved quite rapidly, so Sun Microsystems, which was then still on campus, became a company. So I think there's sort of a very productive give and take between the industry and the academia, at least in my field.
Over the next few years, while an assistant professor at Rice, Professor Zwanapul turned his attention to the idea of sharing computer power over a network.
In the network, most of the time, most of the machines are idle. there's not much going on. And so there was this idea of how could we coalesce all this computing power to work on really big computations.
His work on distributed shared memory and the resulting trademarks system overcame the major obstacles faced by earlier systems, enabling multiple computers to work together on a problem in parallel. Professor Swanepoel spent more than 20 years in the United States before being enticed to Switzerland to lead the School of Computer and Communication Sciences at EPFL. During his tenure there, he led a paradigm shift that saw the university rise from relative obscurity to a world-renowned institution in the field.
The thing that gets me up in the morning is to work with young people and help them in, sort of guiding their career.
At the heart of his academic leadership has been a commitment to supporting the growth and success of the next generation of researchers. A commitment he brought with him to the University of Sydney in 2018 when he became Dean of Engineering, a position he held until 2024.
Their first role should be to produce the people that will make technology advance. That, to me, is number one, and perhaps number 1, 2, and 3 of what the university should do.
His outstanding dedication to the advancement and promotion of computer science has now seen Professor Swanepoel elected a new Fellow of the Australian Academy of Science. Professor Emma Johnston investigates how humans interact with marine ecosystems.
My work has primarily been in coastal marine ecosystems, which is where humans have the most impact because we tend to love living near the coast and we use coastal ecosystems for all of our transport and our recreation, and we get a lot of food from them.
Global shipping means that none of those ecosystems work in isolation.
We actually have this mechanism for transporting species from one country to the other on ships, and that could be either in the ballast water or connected to the hull of a ship.
Some of Professor Johnston's research included laboratory and field experiments, which identified new drivers of invasive species success and clearly demonstrated their ability to rapidly evolve in new environments.
In many of the ports and harbours that I work in, there are more than 300 different species that you can see of marine organisms that are introduced. They're non-native.
Understanding this paves the way for better management strategies, such as dredging up contaminated sediments to help improve outcomes for native species. Professor Johnston believes in translating research into action, particularly evidence-based public policy. She was chief author of the Australian State of the Environment report in 2021.
We are at the forefront of climate impacts, and without rapid, drastic, urgent, unimaginably fast carbon emissions reductions, we stand to lose a lot of those precious ecosystems.
Professor Johnston is Deputy Vice-Chancellor Research at the University of Sydney. She's become a highly influential voice for science, having served as President of Science and Technology Australia and Dean of Science at UNSW. She's determined to make the sector more open and inclusive, but says that requires a whole-of-society approach.
It's the schoolyard where they're encouraged to do particular activities. It's their role models that they see as they go through high school and the choices in subject that they're encouraged to make. And then in their actual undergraduate and their career, it's about building in the flexibility so that people can have a diverse array of different cultural backgrounds, but also lifestyle choices and come in and out of scientific careers.
Research funding is another key priority for Professor Johnston. She says government and industry investment is proportionately much lower in Australia than in many advanced nations.
We have incredible minds and incredible fundamental research being done, but sometimes we cannot follow through because the investment in the translational work, in the innovation, in the bringing the product to market, the money is just not there.
Professor Johnston sees becoming a Fellow of the Australian Academy of Science as not just an honour, but an opportunity. She wants to work with other fellows in promoting the value of science and guaranteeing a vibrant sector.
Science is a method that has enormous potential for benefits for the whole of society.
Taking medicine in the future Could be as simple as eating a salad.
The example that we're actually doing at the moment is to have a multiple sclerosis drug in tomatoes so that people with chronic multiple sclerosis could maybe have their Greek salad and have some level of medical protection from the disease.
These drugs are based on molecules known as peptides. They are smaller than proteins and carry out important biological functions such as regulating other molecules, and some even act as hormones. Several peptides have pharmaceutical potential, including as potent painkillers. But because most break down if they're taken by mouth, Professor David Craik and his colleagues have engineered them into more stable circular peptides called cyclotides. Cyclotides are naturally found in some plants, so Professor Craik's team can embed them into edible plants such as tomatoes.
One of the issues with current painkillers is that often they don't work. And then we also know with opioids there are horrible addiction problems in the so-called opioid crisis. This is a different class of molecule that doesn't have those addictive effects.
Professor Craik says the potential applications extend beyond chronic pain and disease to areas including agriculture.
We could be creating a new biofarming industry in Australia where farmers could be, rather than growing a crop that might be worth $100 a tonne, it could be worth $100,000 a tonne by producing a high-value medicine in those plants.
The innovation isn't far from becoming reality, with the first crops potentially commercialised in the next few years.
Obviously there's lots of regulatory and social and ethical issues that we would need to address in doing this, but I think it does open up a new world for combining agriculture and medicine and delivering medicines in a novel way.
The average Australian spends at least 90% of their time indoors. But how often do you think about the air you're breathing in? Indoor air pollution is considered a serious risk to public health in societies around the world. Despite that, most countries don't have any indoor air quality standards.
Every drop of water we drink from the tap, its quality is highly regulated. Every piece of food we take to our mouth is highly regulated in quality. Indoor air, which we take into our lungs 12 times a minute, is not regulated at all.
Professor Lidia Moravska from Queensland University of Technology was named one of Time magazine's 100 most influential people in 2021 for pressuring the World Health Organization into acknowledging that COVID-19 could be spread through the air, particularly indoors. Now she's leading a new push for international action. Professor Moravska and a group of global experts have used the prestigious journal Science to publish a blueprint for mandating indoor air quality in public buildings.
Our paper, which is a consensus of over 40 scientists and experts from many disciplines from around the world, is the best practice, better than anything else which is happening anywhere in the world.
The group proposes standards for 3 key indoor pollutants: carbon dioxide, carbon monoxide, and PM2.5, which are particles so small they can lodge deep in the lungs and enter the bloodstream.
This is my favorite little monitor. It measures carbon dioxide. Together with carbon dioxide, we emit other things, in particular pathogens, bacteria or viruses if we are infected. So if concentration of carbon dioxide increases, potentially concentration of these pathogens increases as well. And it fits into my handbag, so it goes with me everywhere.
The scientists also want to ensure mechanical ventilation systems remove and dilute pollutants at a higher rate than their production. She points to schools as an obvious place for action, where many classrooms are now being fitted with air conditioning.
One issue with this is that while it provides a good thermal comfort, it does not provide fresh air. It just recirculates the air, so it doesn't do anything to improve air quality.
Outdoor air quality is already regulated in many places in line with the World Health Organization's global air guidelines. Professor Moravska says countries such as Australia can now lead by example for indoor air as well.
We know how to do it. We know how important it is. why won't we start now?
Kathleen Folbig has always insisted she never killed her 4 young children.
Did you kill Caleb?
No!
Did you kill Catherine?
No!
Did you kill Sarah?
No.
Did you kill Laura?
That's a position she maintained while exhausting all of her legal appeals and during 2 subsequent judicial inquiries. 20 years into a 25-year prison sentence, the justice system has now accepted there is reasonable doubt about her guilt.
I think the nation will look at the case of Kathleen Folbig as a major miscarriage of justice.
Ms Folbig was convicted of smothering her babies Caleb, Patrick, Sarah and Laura. The 4 died on separate occasions between 1989 and 1999. But at the time of her conviction in 2003, there was no way of knowing if gene mutations played a role in any of the deaths.
In fact, it was only in 2003 that the first draft of the human genome sequence was completed. Now, since then, it has become possible to sequence whole human genomes and exomes in a much faster and affordable way.
That's Professor Carola Vinuesa, who analysed sequences from DNA extracted from old heel prick samples of 2 of the Folbig children.
She was concerned that the analysis of that genetic information had not been fully heard during the first inquiry into the convictions of Kathleen Folbig. And it was those concerns and her resolute understanding of her science and her scientific integrity that in some ways didn't let her sleep at night.
Professor Vinuesa took those concerns to the Australian Academy of Science, where she is a fellow.
The more we looked at it, the more we too became concerned around the way science had not been heard in that first inquiry.
The science was complex. Research undertaken by Professor Vinuesa and complemented by independent experts around the world showed that Ms Folbig and her 2 daughters possessed a rare gene mutation known as CALM2G114R,
which encodes for calmodulin. Calmodulin mutations typically are associated with cardiac arrhythmias that can cause sudden unexpected death in children and adults, both while awake and while asleep.
The second inquiry, which was instigated at the urging of prominent scientists, including 3 Nobel laureates, also heard medical evidence about epilepsy and respiratory problems, which could help explain the deaths of Ms Folbig's 2 sons, Patrick and Caleb.
There is a reasonable doubt as to Ms Folbig's guilt.
Retired Chief Justice Tom Bathurst KC accepted that the weight of the evidence cast reasonable doubt about Ms Folbig's guilt, recommending her pardon. A key difference in the way the second inquiry considered medical evidence was the role played by the Australian Academy of Science.
I think now that with this new evidence, it's beyond reasonable doubt.
This is a clear indication that the independent scientific advice has an important role to play in the justice system.
The Australian Academy of Science was granted leave by the inquiry to act as an independent scientific advisor to it. I think unique to this case, and the role the Academy's been able to facilitate, is that the inquiry's been able to hear from a range of experts from the right subdisciplines to give a complete picture of the sort of science that is complex, and some of it's still emerging, that's been able to shed light on the possible causes of death of the 4 Folbig children.
The Academy believes the case serves as a dramatic example of the need for a more formal mechanism to re-examine cases after appeals have been exhausted when new science is revealed.
Science is always emerging. Nothing is going to stop the advancement of knowledge, nor would we want to do that. It would be an enormous missed opportunity if we couldn't bring about some of the law reform that's needed so that science can more effectively inform the justice system.
Billabongs are bodies of water left behind when a river alters course
or after floodwaters recede. These are some of the last remaining in Melbourne and were once an important gathering place for the local Wurundjeri people and neighbouring tribes.
Slow, I'm going to get through.
When Dr. Joe Greet first started working here alongside the Wurundjeri Narrap team 5 years ago, things were looking grim.
And most of the sites were filled with weeds, there were few frogs, no water birds.
That's because the billabongs weren't getting the water they need to remain healthy.
The water coming down the Birrarung is only 2/3 of what it was pre-colonisation, so the Birrarung doesn't connect with its landscape, with its billabongs as frequently.
A collaborative effort involving the Narrap team and Melbourne Water has begun turning things around.
We are starting to introduce solutions, hopefully to increase the resilience of these sites.
Solutions such as creating a drainage swale to enable water to flow more freely between the river and Billabong. Dr. Greet and Narrap Rangers are leading a monitoring program to better understand how native plants and animals respond both to these managed flooding events as well as natural flooding from the Birrarung.
We're seeing a drowning out or suppression of the terrestrial weeds, a flourishing of the native wetland vegetation, and the increased condition of these beautiful old river red gums. Just previously, the water birds seem to know when these billabongs are full. We've seen eel numbers increase.
Who's getting the gloves on?
And we see through our eDNA sampling that those sites that are more frequently engaged with the river have a greater representation of native fish and frogs.
But Dr. Greet says there's more to be done, not only to improve the health of our billabongs, but also to increase the role of traditional owners in water and land management. As a recipient of the 2024 Aboriginal and Torres Strait Islander Scientist Award from the Australian Academy of Science, he hopes to continue efforts to do just that.
We want to get together and hold a series of workshops and understand better from a Wurundjeri perspective how we can better assess the health of these billabongs, the health of country, and better manage them into the future.
Indigenous-led research is also crucial in the field of cancer genomics, where fellow award recipient Dr. Justine Clark works. In Australia, cancer disproportionately affects Indigenous communities.
Aboriginal people are about 14% more likely to be diagnosed with cancer compared to non-Aboriginal people, and also about 20% less likely to survive for 5 years after diagnosis. So there's a massive gap there.
Indigenous Australians still face many barriers in accessing standard and precision cancer care, but Dr. Clark hopes her research will help change that. At Telethon Kids Institute in Adelaide, she's begun work to build up a knowledge base of Indigenous Australian genomics to drive advancements in clinical care for Indigenous Australians living with cancer.
The exciting thing about it is that we can learn about our DNA and find new treatments for cancer that are targeted to specific genes, and we can also find better uses for our current treatments, better diagnostics, better screening, and that's what we call precision medicine.
Dr. Clark plans to work with members of the South Australian Aboriginal community to better understand the cultural implications of this research and ensure it will ultimately benefit Indigenous Australians. She will also travel to New Zealand to meet with Maori colleagues with hopes of establishing collaborations there.
Doing it together is the best way forward to create a global agenda where we can improve cancer outcomes for every Indigenous person.
It's work that Dr. Clark feels incredibly proud to be a part of.
I always think of my ancestors, and they were the first scientists in this country. And I think of the legacy of people that have come before me that have fought for a better future for our communities. And I'm just honoured that I get to do that now through my research.
Robots are often used to increase productivity and profit, as well as to save time and improve safety.
That might be underwater, surveying large parts of coral reefs. It's dangerous to have human beings under the water for long periods of time. Robots could do that job beautifully, and no one gets harmed or injured.
Professor Peter Cork is a renowned robotics expert who has pioneered aerial, marine and land robotic systems for mining and environmental monitoring.
The thing that I'm most proud of in the area of robotics is something that we take for granted, and that's hand-eye coordination. And it's particularly challenging if the object you're trying to reach is moving.
Professor Cork says the ultimate goal is to program robots to see.
Being able to see is something we take utterly for granted, but it's a capability that robots don't have, and it absolutely hinders them in being able to do the sorts of things that we expect robots to do.
He's also involved in researching deep learning.
So instead of writing a program that can say, this is what a human being looks like, we write a program that can learn, give it lots of examples of human beings and say every time this is a human being, this is not a human being. And it will learn some generalisation, some representation of what a human being is.
Global research is underway to coordinate discoveries and design the robots of the future.
There are people working on vision, people working on fingertips, people working on legs, all of these different components of the robot system being worked on simultaneously, and leads to a huge body of work which is going to give us in the future very, very capable and competent robots.
Our research and innovation is generating ideas and impact to deliver positive and lasting change for a better future.
As creators and innovators, together we work across diverse disciplines and 5 impact themes to solve the world's greatest social, economic and environmental challenges.
We ensure the innovations of the laboratory and state-of-the-art technology translate to the ward and treatment rooms on health's front line.
We place sustainability at the centre of our research, prioritise the protection of all species, advance a circular economy, and support the transition to renewable energy.
With world-class research teams and resources to match our ambitions, we create smart and ethical technologies to improve lives and our economy.
We strengthen society, culture and commerce through creative, contemporary and intercultural approaches to education, the arts and business.
From increasing community resilience to cutting-edge cybersecurity, when we see problems, we build ethical and innovative solutions.
At Deakin, we're delivering positive and lasting impact for a better future.
Deep thinking, where every move counts. That's a skill set Professor Andrew Wilkes has refined through chess tournaments like this one.
Chess taught me how to think tactically and strategically. In the sciences, those sorts of skills are incredibly important.
He was amazed in 2017 when Google DeepMind's AlphaZero AI program triumphed at chess against world-leading specialist software within hours of teaching itself the game.
If you could apply these sorts of tools to a similar process, drug discovery, it's a process that has some rules, many unknown unknowns, then you might be able to advance your programs that much quicker, that much more effectively.
And that's what brings us here to the Bio21 Institute at the University of Melbourne. Professor Wilkes co-founded a company based at the institute called Synthesis MedChem.
There are big machines, big toys, big equipment that can do amazing things here. And the sort of information that comes out of that structural biology, analytical chemistry, those sorts of things are incredibly important for us as we develop our drug discovery programs.
Professor Wilkes is a molecular and cancer biologist. During his time at the Ludwig Institute for Cancer Research in the 1980s and 90s, he discovered and named the JAK family of kinases, enzymes that play a critical role in how cells interact with their environment. That discovery significantly advanced our knowledge of immunity, opening new avenues for therapeutics. Professor Wilkes is also very much an entrepreneur. Before Synthesis, he founded one of Australia's most successful biotech companies, Cytopia.
Making the connection between the science and cash or investment, that's a little bit of a skill. There's still a translation gap in some way, where the potential value of a piece of science is still somewhat opaque to the people who have cash to invest.
Professor Wilkes' mission these days is to generate enough investment for early phase drug discovery before then passing the projects onto larger pharmaceutical companies to complete clinical development. That mission is enhanced by machine learning technology.
The computer will develop an algorithm by which it can improve the way the molecules behave. and you kind of go along for the ride.
It's not all left to the computer. Ultimately, each hypothesis must be subjected to biological validation.
But you can get a long way down the path much more quickly, simply using these AI programs and computational chemistry. We're all cyborgs now, in many respects.
Professor Wilkes says becoming a Fellow of the Australian Academy of Science is a massive honour, and one he hopes will encourage more investment in the complex chessboard of translational science.
This is no ordinary scientific lab. These field sites in the riverina New South Wales city of Wagga Wagga help Professor Leslie Weston improve our fundamental understanding of crop protection.
My entire career has been developed around looking at mechanisms, how things work, why things are working, and commercially, what does that mean for a nursery industry or horticulture, or in this case, broadacre agriculture or livestock producers.
Professor Weston is a plant biologist. She studies how plants interact with everything around them.
So specifically, plant interactions with pathogens, plant interactions with soil inoculants, plant interactions with weeds, and plant interactions with insects, as well as biocontrol agents.
Charles Sturt University is the perfect research base for Professor Weston's team. The campus is home to not only a working farm, but also state-of-the-art labs.
We can now assess, using mass spectrometry and metabolomics, the presence of the whole complement of chemistry that's present at any point in time, either in a plant or in the recipient organism, the animal or the pest.
These techniques have offered new insights into how plant roots release various molecules into surrounding soil and the resulting impact. This knowledge is then shared with industry and other scientists to create what she calls big picture solutions for farming.
Together we work on a systems-based approach to understanding how competitive crops work or how we can protect a plant or livestock from interactions that are detrimental.
It's work that comes naturally to Professor Weston. As a child, she spent a lot of time in glasshouses, helping out at her family's commercial nursery and garden centre.
My family's enterprise in terms of the nursery, garden centre, and production has probably always made me recognize that the industry is really what drives a lot of these discoveries too.
She sees her election as a Fellow of the Australian Academy of Science as a recognition of the work from her entire research team.
I'm also pleased that we're from regional Australia. We're hoping that this will bring an awareness of the types of research and the impacts that we can have on the community. So, very pleased that this happened.
From mobile phones to electric cars, rechargeable batteries can now power just about all things electronic. But they're far from perfect.
Battery performance worsens over time due to a combination of factors, including the battery material degradation, electrode degradation, electrolyte breakdown, and also environment issue as well.
Here at the University of Adelaide, Professor Zhaiping Guo is focused on developing the next generation of rechargeable batteries.
So if the battery has perfect performance, let's say high energy density, can be fast charged with long lifespan, very safe, and also very cost effective, then we are happy. That's our target, to develop rechargeable battery with excellent performance.
Her research group investigates novel electrode materials and electrolytes for lithium-ion batteries to increase the amount of energy they can store and extend their cycle life. They're also exploring more affordable and sustainable alternatives to the widely used lithium-ion battery. This includes potassium-ion batteries, which Professor Guo herself pioneered.
Potassium is in the same group in the periodic element table. So in terms of chemical properties, quite similar to lithium. Potassium is more abundant, it's cheaper. That's a key thing.
While these battery systems are still in very early stages of development, Professor Guo believes they have great real-world potential. In fact, some of her innovations have already attracted investors. For instance, her team successfully synthesized silicon-carbon composites to use as anode materials instead of graphite in lithium-ion batteries. And they're now collaborating with a startup company to scale up this technology.
Graphite has a relatively low capacity. Therefore, the energy density of current lithium battery is limited, normally below 250 watt-hour per kilogram. But with this silicon carbon composite to replace the current graphite anode, we can boost the energy density.
Professor Guo came to Australia more than 20 years ago to do her PhD in materials engineering at the University of Wollongong. She says being elected a Fellow of the Australian Academy of Science is a great honour and hopes it can inspire other young women in science to follow in her footsteps.
Being a woman in science is quite challenging but rewarding as well. You know, work-life balance is not easy thing to manage, but I'm proud today. I'm able to mentor the next generation, and I have very fantastic female scientists working in my team. I'm very proud of this.
You're looking at the largest single dish radio telescope in the world. It's called FAST and located within the mountains of southwestern China.
And that is by far the most sensitive radio telescope in the world. I first went there while they were putting the first few things on the ground, and it was amazing to see how quickly in China you'd come back a year later and the whole dish would be built.
At the heart of FAST is a primary multi-beam receiver designed and built by Australian scientists. China chose to collaborate with Australia because of our experience with the Parkes radio telescope in regional New South Wales.
The Parkes radio telescope is by far one of the greatest telescopes in the world. It's been upgraded many times, so it keeps getting upgraded. It's not a 60-year-old telescope. The most recent upgrade was just a couple of years ago with a very wideband receiver system that allows us to observe the radio waves over a much wider bandwidth than any other telescope on the Earth.
Parkes has special significance to Dr. Hrvoje. His first visit was as an international student.
I mean, the second you see the 64-meter big telescope there with wonderful weather, blue sky, I was really shocked. I thought this is the way to do astronomy.
He later returned to Australia to complete his PhD under the supervision of George Hobbs, before accepting a teaching position at Western Sydney University, where his research focuses on rapidly spinning neutron stars known as pulsars. The Parkes radio telescope has detected more pulsars than any other facility in the world.
Radio astronomy in Australia is really strong. The experience and expertise here are really sort of the most attractive for a student in China.
That's thanks in part to the work of people such as Professor Elaine Sadler. For more than 30 years, Professor Sadler has been at the forefront of research into astrophysics. Her team discovered a 5 billion-year-old galaxy using the ASCAP radio telescope in Western Australia.
Now, 5 billion years ago, the Earth didn't exist. So in the time that signal's been travelling to us from this galaxy, the sun has formed, it's made planets, the Earth has settled down, it's got oceans, life has evolved, we've got a technology, we've built telescopes, and there we are just in time to catch this signal.
Professor Sadler started working regularly with Chinese scientists 7 years ago. She says international collaboration is critical to understanding our universe.
I think one of the great things about working collaboratively with people is it allows you to build up the trust and the common interests that allow you to make advances in science.
Astronomy is a very collaborative science. You can't just do your own research simply on your own.
It's about actually exchanging your idea with different people, different background, different expertise. If we don't have that, we are not doing the best science.
So why does science matter?
Science is what drives our advances in medicine and what gives us new treatments, new vaccines, new techniques in surgery. All of those need to be evaluated, developed, many of which come from crazy ideas from fundamental science. Other advances come from astute observations by clinicians. So science is so critical to advances in medicine.
And I think this was one of the most beautiful examples of science in action, where every biomedical researcher on this planet over the last 3 or 4 or 5 years has read a paper, and many have written papers, about a virus that they had never heard of. I find this mind-blowing to what degree we have, as a community of scientists, come and tackled this new threat.
I'm motivated to research antibiotic pharmacology because I see the human cost of deadly bacterial infections. I think science is fundamental to discover the mechanisms, and then we can use the mechanistic findings to develop novel therapeutics. This kind of translation is not come out from a simple thinking. It come up with a long-term research. So that's why science is so critical.
Science is just the way that we learn to think. You know, we learn to gather data, interpret data, make decisions based on data. And over the last few years, it's been really surprising and horrifying, actually, to see that not everybody thinks that way.
We live in a world where we need to make informed decisions about how we build our houses so that they use less energy, so that they're more comfortable, healthier, better places to be. Even just down to the simple decision of, you know, whether or not you put insulation into your walls or into your
Good afternoon and welcome back to this, our final session of presentations from fellows elected in 2024. This session will be facilitated by Jim Williams, who's our spokesperson for integrity, and council member Professor Ian Wright. I've introduced both to you earlier, but you may not have been here in the earlier part of Science at the Shine Dome. Briefly, Professor Jim Williams' expertise has shaped semiconductor and quantum research, and he's the spokesperson for integrity as part of the Council and Executive Committee of the Academy. And Professor Ian Wright is a plant ecologist who applies the principles of economics to study plant evolution. To get things started, I'll hand over to Ian. Thank you very much.
Thank you, Anna Maria. So, welcome everybody. I hope you had a good lunch. Mine was a little bit rushed.
but I have something else to do, but it is delightful. So I'm pleased to introduce our next speaker, Professor Emma Johnston. So Emma was actually elected in 2022, but this is her first opportunity to get to the Science and Shine Dome. So she's here with us this year to sign the charter book. Don't forget to sign the book. Have your photo taken to present, which you'll do shortly, and to celebrate. So Emma Johnston is internationally recognised for her work in marine ecology, and she's also a highly influential leader, advocate and voice for Australian science. I've known Emma a little bit, for we were undergrads together many years ago at Melbourne University. I always thought that she'd become Australia's first woman Prime Minister. That Guernsey's gone, but you may still yet become a politician, who can say, once you get over your role at Sydney University. So anyway, please welcome Professor Emma Johnston.
Thanks, everybody. And it's lovely to be introduced by an old friend from undergraduate. That brings back some memories. This is not my first slide. Oh, it is. Let's get started. So thank you very much. I'm going to be talking about the great acceleration, particularly of our coastal ecosystems. But I want to start by acknowledging the Ngunnawal people. I recognise and honour their continuing deep connections to land and waters. And I acknowledge and welcome other Aboriginal and Torres Strait Islanders who may be joining us today. I always start by acknowledging all of the people, funders and collaborators who have been involved in the research, and because I'm doing a whirlwind tour of quite a large number of different research topics that I've been looking at over the last 20 years, there's a large number of photos here and organisations, but I particularly want to highlight the early career researchers, the interns, the postdocs, the PhD students, the volunteers who have been with us through these journeys and have really been the brains as well as the energy and the innovation in much of the research we do. So, many of you will have heard that the world is speeding up, and it's not just faster cars, faster drugs, faster communications. Natural ecosystems are also speeding up. Metabolisms, evolution, growth, life, and death. And they are creating ecosystems that we have not encountered before and that we have not relied on before. This acceleration is driven by many different factors, acting in concert, and the resulting dynamism requires us to shift our approach to research and science, our approach to conservation, and our approach to the way that we rely on ecosystems. And I tell you this story from my perspective as a coastal community ecologist, a multidisciplinary researcher, but also as chief author of Australia's most recent State of Environment report, and as a director on the board of the Great Barrier Reef Marine Park Authority for the last 8 years, or 4 mass bleaching events. Our life support systems are in decline. This is a report of our progress against SDGs, and you will note there is not much progress. We are within 5% of attaining 2 of our social goals, very important, but we are in a long-term negative trend on all of our environmental goals: climate, life in oceans, life on land. And they, of course, are the basis upon which all of our social goals can be attained. This is due, in large part, to the great acceleration of the use of our resources and the accumulation of the resultant pollutants in our natural systems. This is the work done by Stefan et al. Originally in 2004, updated in 2015, but it shows that incredible acceleration of activity and resource use. My contention is that all of the major ways in which we use and abuse coastal ecosystems are all acting in concert to increase the rate at which our ecosystems are working. Disturbance frequency is increasing. We're adding resources to coastal ecosystems, which speeds up and fertilises them, but also increases disturbance. And we're increasing the frequency of intercontinental transport and range expansions of species which are largely selected for their rapid rate of reproduction, their rapid growth, their weediness. This all creates a self-reinforcing cycle resetting session very quickly and seeding new communities with fast-growing species. And that has consequences. Very quickly, I'll run through the 4 major drivers. Heat, something you'll be very, very familiar with, and you will have heard some brilliant talks about already. But these are the daily sea surface temperatures at 60 degrees south and 60 degrees north, well outside charted territory. And the impacts of heat are twofold. One, increasing metabolism, growth rates, reproduction, until a point is hit where major disturbances take place, where stress tolerances are well and truly gone beyond. And what we see in marine and coastal ecosystems, and this is images from around Australia, are major disturbance events. From a community ecology perspective, disturbance events are anything short discrete that take out a very large number of species. And you can see mangrove die-offs, bleaching, and kelp forest loss. It's estimated that 40% of Australia's coastal ecosystems have been hit by a mass disturbance in the last decade alone. We've been using latitude gradients to explore spatial and temporal variation in the very fundamental nature of how communities assemble, and then what drives species coexistence. This is the very theoretical background that underpins most of my research through time, through my career, but it's very much underpinning our interpretation of what will happen when we use coastal ecosystems. And what will happen is that the tropics will move into temperate systems. Our theoretical work has shown on a number of different fronts that the tropical ecosystems are quite stochastic, and the temperate systems, and very much extends to our Antarctic work, are much more deterministic in the way that they assemble. This has really fundamental consequences for how they support biodiversity. In Antarctica, I'm now moving on to the addition of resources. We are actually adding resources to one of the remotest locations in the world, and we are adding light. So as the sea ice extent around Antarctica, and obviously in the Arctic, declines, and we are starting to see that now, we add light to the sea floor. We predicted this in 2013. We'd observed it in the Arctic. We predicted it for the Antarctic, where we weren't yet seeing changes to sea ice cover. And that's because the circumpolar current was protecting Antarctica, insulating it. But we predicted that the light would change, and we predicted that we would lose these incredible, quite unique, absolutely unique communities of invertebrates that live under the ice, mostly just very still, slowly growing. I imagine they might shiver, but they don't. And these are sponges, sea squirts, polychaetes, incredible diversity of invertebrates. And what will happen as the light is added is that ecosystem will speed up and the algal communities will take over, and we will lose a great deal of biodiversity. Another way in which we add resources to coastal ecosystems, of course, is through pollution. Very many sources of organic enrichment, but perhaps the most common and the most widespread is the addition of synthetic nitrogen, something that we have applied across all of our continents and something that has helped us feed the world, but we have applied it too liberally and it is fertilising our coastal systems. That's increasing productivity, but also, when it goes too far, increasing eutrophic events and low oxygen events, which are again another form of disturbance. A new form of addition of resources into coastal ecosystems is one that we have literally just published the first ever global studies of, and that is the wildfires that then cause runoff into our estuarine systems. They add silt and soil, and they majorly, we have found, impact coastal ecosystem productivity and nutrient cycling. We found increased trace metals, organic enrichment, nitrogen, phosphorus, and I guess one important finding here is that pyrogenic carbon, which is a very fast burn of carbon, is a very good indicator of where wildfires are having an impact in these coastal ecosystems. There is a concomitant impact on the biological diversity, and we use eDNA techniques to assist our discovery of that. We can extend that to metatranscriptomics, where we can look at the function of these systems. And here we see very clearly from many of our studies looking at the addition of nutrients into soft sedimentary ecosystems, the dominant habitat on the planet, that we can see when we push systems too far, we get the increase in ammonia, nitrite, hydrogen sulfide, and nitrous oxide, which is in itself a potent greenhouse gas, and one that is not generally considered in most models. The final way in which we speed up coastal ecosystems is through the addition of species, long studied as the transport of invasive species, mostly by shipping, but now also increasingly happening through range expansions as a result of climate change. We predominantly transport weedy species, as I mentioned earlier, and many of our research programs have understood and studied this effect so that we see advances for introduced species in systems that are impacted by humans. So I finish by saying this cycle is very important. We are resetting succession, we are introducing new cycles of weediness. The effective age of our coastal communities is reducing, with profound implications for coastal ecology and biodiversity. And in the near shore, I predict that temperate ecosystems will become, ironically, more biologically diverse, while global biodiversity declines. How general are these mechanisms? They are all rate mediated. And if you're not, as a community ecologist, thinking about rates, then you are missing most of the picture. For humans, this has profound implications. For scientists, we need to move from pattern to process, from structure to function. For conservation, we need to be thinking more agile approaches, temporal closures, biological and interventions, and you will hear from other researchers in this space very soon about some of those ideas. For us as humans, we need to eat lower down the food chain. We need to support our filtrators, the species in our coastal shellfish ecosystems that we have lost so many of, but that control nutrient addition in those important areas. We need to stop armouring our coasts and rely much more on soft sediment engineering actions and biogenic protection of coastal ecosystems, such as our reefs, our seagrasses, and our mangroves. And all of this is because we're speeding up coastal systems and we're speeding up natural systems in general. Thank you very much. I didn't see the clock until right at the end. I was pretty close.
Plenty of time for questions.
Oh, great.
A couple of questions for Emma. Oh, yeah, Bob.
Bob.
Well, just while we get a microphone to you, I'd just like to thank you again for that wonderful talk and wonderful examples of transdisciplinary research as well, bringing in omics and ecology and all these things to bear. And also you finished with some good news stories, sort of.
Yeah. Which ones were they? Yeah, not sure.
So you have some ideas for how to do things better.
That's true, that's true. And I think increasingly our work is in social sciences. So we're looking at stewardship and the incredibly powerful role that humans can play in protecting ecosystems when we think of it as a virtual circle, where the stewards protect our local ecosystems, value them, but in turn get so much back. And a lot of our social science studies are showing that, for example, in coastal ecosystems, where we have the full protection of those systems, so in fully protected marine parks, we get incredibly positive social circles where people are more optimistic, they value the ecosystem further, they take more action to protect that ecosystem, the ecosystem is in better shape and biodiversity is higher. And you get this very lovely connection between people, policy and place that provides a sustainable option for many of us. And I think the more that as scientists we extend our work into social science, the more impactful a lot of our work can be. So I answered a question that wasn't asked, but that's one of my special skills.
Yes, Emma, thanks a lot. Lovely talk. We hear a lot, we know that species are becoming extinct, and in Australia it's one of the worst. Do we have a handle on whether new species are being added and what the diversity of that is? Because that might give us a handle on what happens as climate changes, whether we can get new species that adapt to that.
So new species as in transported from other locations? Yeah. So, because there's always a question of when a new species actually has evolved, and that's a very tricky question to ask. But in relation to the transport of species, it is in marine ecosystems in Australia a tragedy that we don't know how many have been introduced, and we don't know how frequently that they arrive. And that's because we haven't, as a collective, described all of our coastal species. And I'm not just talking about the microbes, I'm talking about the macrofauna have not been described. So I would often work in an ecosystem where maybe 80% of the species that I'm working with, that I can see with my own eyes, have not been described by science. To layer on top of that the addition of new species, it's ironically often the new species that we can identify because they've been described in the US or Japan or the UK. So that's a first very difficult situation. Increasingly, we're relying on molecular techniques to fill the gap, turbotaxonomy, where all you need is a sequence and a visual image of the species in order to lay a claim to it being a separate species. Then once we get those databases, we can then get a better handle on how many species are being introduced. I think in terms of range expansion, we have better data, and citizen science is playing a really substantial role in us tracking range expansions. RedMap, for example, in coastal ecosystems, where individual stewards of marine ecosystems are logging when they see a species that they think is unusual, and through that process we are being able to map range expansions, and they're happening very, very quickly in marine and coastal systems. The very challenging situation we have is that not entire ecosystems aren't moving. So, for example, if Sydney was going to become a coral reef or a tropical ecosystem, you could imagine it functioning fairly well as an entire ecosystem and supporting biodiversity and ecosystem function. But what happens instead is that we get individual mobile species coming down, coral trout, for example, off Sydney Harbour, herbivorous fish, and we don't get the entire ecosystem. And so that's where you get the effective biological invasion situation, where there's a mismatch between what has evolved in that ecosystem and what has now recently arrived.
One quick question and one quickish answer.
One quick question, if I may. Yeah. At this meeting, we've heard quite a lot about wind turbines, and in particular offshore wind turbines. I was just wondering what your position was with respect to offshore wind turbines and their influence on the ecosystem.
I mean, the number one challenge to most biological diversity at the moment is climate change itself. So if wind turbines are a necessary part of the rapid transition that needs to be made in order to reduce carbon emissions at the rate at which we need to make them, then obviously there's a risk assessment to be done here as to whether or not the impacts of a wind turbine in a coastal ecosystem, and there are impacts, are lesser evil than what we would have if we don't rapidly transition. Now, my understanding in Australia is that wind turbine technology, a bit like nuclear, I don't want to introduce another red herring here, but is still far more expensive than our land-based wind and our solar. So there is a really big question about whether or not you would embark on that work. There may be certain circumstances in which the grid connections mean that it is much more favourable to have wind turbines in a particular area, and that is the solution. But I don't think as a generic solution, Australia is the right continent for it. All good?
Yeah, all good.
Thanks.
Thank you. Let's thank Professor Emma Johnston. And I'll hand over to Jim to introduce our next fellow.
Thank you, Ian. Our next speaker is Professor Hrvoje Tkalčić. Hrvoje Tkalčić is a geophysicist who has made fundamental contributions to the study of the Earth's interior. His breakthrough work in the understanding of the seismic correlation wave field opened the way for global and planetary seismology to illuminate the interiors of the Earth and other planets. Please welcome Professor Hrvoje Tkalčić.
Thank you very much. I would like to start with thanking the Academy for this special honor, and I would like to acknowledge my nominator, Professor Brian Kennett. He is also the one who asked me to apply for an academic position 18 years ago, and that's how I ended up in Australia. I would also like to thank to all of you for being here today, making our day a bit more special than it already is. And I thought I would start with how to pronounce my first name. Although the pronunciation was excellent, it's a Croatian phonetic pronunciation, and you just say Hrvoje. So everything you see, you pronounce. So the inner core of the Earth is really a planet within our own planet. That's how I like to think about it. If you, in your mind, imagine dismantling the Earth and looking inside the inner core, you would see a shiny object, almost like a star, that would shine in a white color, because the temperature approaches to 5,000 to 6,000 degrees, which is exactly the temperature of the sun's surface. Secondly, the pressures go up to 360 gigapascals. This is millions of times larger than the surface, the atmospheric pressure. So, despite these hellish conditions, there is order, and that is that in the liquid outer core that surrounds the inner core, there's a convection, vigorous convection happening, and the Earth's rotation, they give rise to the geodynamo. It's a giant dynamo, and I think it's fair to call it the beating magnetic heart of our planet. It extends to the space and protects life on the Earth's surface from solar wind and the cosmic radiation. So how does the journey to the center of the Earth look like? I don't have the time to cover everything, but starting from my PhD at the UC Berkeley, where I worked on these deep Earth subjects, the inner core and the lowermost mantle of the Earth, I worked with one of the most eminent seismologists in the world, Professor Barbara Romanovich. I was able to continue with my other interests, and when you move to a continent like Australia, you immediately recognize the importance of the proliferation of seismic instruments in the remote areas of our continent, and also in the vast Southern Ocean and the floor of the Southern Ocean. That takes you to, eventually, to Antarctica. It takes you to the moon, Mars, and the more mature I'm getting as a scientist, I realize the importance of popularization of science to children and to the broad audience, and that's something that I'd really like to continue working on. This is how my research group looks like, how it developed over the years. I would like to extend my gratitude to each one of them for working with me on interesting topics apart from the inner core, and I would like to share this recognition with all of them. But to give you a bit of a historical flavor of the journey to the center of the Earth, we could go back to the 17th century and the early recognition of the extreme amount of heat that's still trapped within the planet. And you can see this in this conception. Fast forward 2 centuries, we are in the mid of the 19th century, and in the Jules Verne novel, he explores this idea of a hollow Earth, and you have this subterranean sea with dinosaurs clashing for survival and giant mushrooms growing on the coastline. Then half a century later, in the early 20th century, some very familiar images start to emerge, and I like to call this era the dawn of seismology, and indeed we didn't have to wait too long for these early discoverers of the Earth's internal boundaries. My academic grandfather, Andrija Mohorovičić, was the first who recognized the boundary between the crust and the mantle. It was followed by Benno Gutenberg's work, who discovered the core mantle boundary. And finally, Inga Lehmann in 1936, who discovered the inner core. And then in 1970s, the decade I was born in, you get this really familiar image that I'm pretty sure resonates with all of you. You've seen it in the textbooks. You can see how the Earth's interiors research is dominated by seismology. in these seismic waves that propagate from the large earthquakes to the detectors or seismographs, we have the direct tool to study the Earth's interior. And if you follow it carefully, you maybe notice that the Inga Lehmann lived 105 years. So she's the one who studied the inner core, and these two other gentlemen studied the shallower layers of the Earth. So from here, we can conclude that the recipe for longevity is to study the inner core. So how does the modern research on the inner core look like? Well, this is Earth in the 3D and the Earth's interior. And you can see here the paths of seismic waves that propagate from large earthquakes, which are marked here by red dots, to the seismic detectors or seismographs, marked by green dots. And you can see the inner core in the middle. You can also see that the northern hemisphere is really well sampled, whereas the southern hemisphere of the Earth has a large gaps in sampling. And when you think about it, it's going to stay that way because despite all these academic deployments that we conducted here in Australia, in remote regions and in the surrounding ocean, we don't have a comparable coverage, a uniform coverage that, for example, medical doctors have. So we as a global seismologists have to be extremely innovative in the ways we sample the inner core and the inner Earth in general. So I hope to demonstrate on these few examples, the work from my research group, how we try to be innovative and to see what's inside the Earth's center. And I start with the inner core rotation. It might be intuitive to some of you because of the liquid in the outer core organizes itself in these vertical vortices. And because of the Earth's rotation, because of the large gravitational torque and the large electromagnetic torque, we have the inner core that spins together with the rest of the planet, but it has its own rotation, so which we refer to a differential rotation of the Earth. In seismology, we use the so-called seismic doublets or earthquake doublets. So these are repetitive events, in this case from South Sandwich Islands, recorded in Alaska. And we look at the tiny differences in travel times of the waves that are sensitive to the inner core. So here we have a doublet, two earthquakes separated by 10 years, one in red, one in blue, and you can see how incredibly similar their waveforms that are recorded in Alaska are. And that's incredible because they travel more than 10,000 kilometers through the Earth's interior, and they're 10 years apart. So to make a long story short, from these really tiny time differences and applying a fairly innovative method in geophysics, a Bayesian transdimensional geophysical inversion, we were able to basically not only take a snapshot of the inner core rotation, but actually reconstruct the history. And what we discovered is the decadal fluctuations of the inner core, differential rotation, which has relevance for understanding the geomagnetic field as well. This second example is the inner core solidity. So we move from the dynamics to the state of the inner core. And some of you might be surprised that, that this is actually a topic of interest, given that the inner core was discovered back in 1936. Believe it or not, the strongest or the most direct evidence that the inner core is solid would be a detection of shear waves. Well, it turns out because these shear waves, they don't propagate through liquids and plasma, this would be really a direct evidence that the inner core is solid. However, they are beneath our observational threshold. And what we did in this study, we abandoned the search for the direct signals of the shear waves. Instead, we studied the late part of the seismic wave field, which we call the coda, similar to music. And instead of looking at the direct signals, we look at the similarities between the signals. So these similarities of these highly reverberating waves that sample the inner core many hours after large earthquakes become our friends. So the signal in the similarity becomes stronger and more potent than the weak signals themselves. And by doing this, we found the evidence for the presence of shear waves in the inner core. And apart from that, we measured the speed of the shear waves, and we were able to establish that the inner core is surprisingly softer than anticipated. So now you might wonder how you go from the Earth to study another planet where you have a single instrument. And InSight mission carried a single seismometer, which operated for 4 years on the surface of Mars, recorded more than 1,000 Marsquakes. And so what we did here, we used the mathematical trickery to replace the locations of receivers and sources. So in other words, our single instrument became a virtual source, or Marsquakes, and all Marsquakes that we observed became virtual receivers. We then applied the same principle that we applied on Earth data, and we were able to confirm the existence of a Mars core and measure its radius. Recently, we were able to detect for the first time in the history of modern seismology the waves that propagate or spread through the Earth along the diameter of the Earth multiple times. And because they sampled the center of the Earth in an unprecedented ways, we were able, by studying their travel times, to demonstrate or to confirm the existence of the innermost inner core. So the innermost inner core, the journalists refer to it as the 5th layer of the Earth. And you can see that by this altmetric score that it actually attracted a lot of media attention. But what it really is a subtle change. It's not a change in a chemical composition like these first-order discontinuities. It's a change in the way the waves travel in terms of their speed. So they slow down or speed up in a different way than in the rest of the inner core due to the crystallographic structure difference. We don't understand really well what that crystallographic structure might tell us about the Earth history, because you can think of the inner core as a time capsule. And lastly, this is just fresh from press from the last week. By looking at these high reverberations, we were able to high-order reverberations, we were able to observe that seismic waves slow down in the outer core, in the liquid core that surrounds the solid inner core, and in its top, but not everywhere, just in the equatorial latitudes. So that defines a shape. In mathematics, it's referred as a torus or a ring structure, but again, journalists call it a donut. So all of a sudden you have a giant donut in the liquid core. But more importantly, the relevance of that structure, where the seismic waves slow down, might be that they contain a higher concentration of light chemical elements. And light chemical elements are important because they drive convection in the outer core. And because they drive the convection, that determines the behavior of a changing magnetic field, and therefore it has a consequence, again, for the life on the Earth's surface. Okay, so that brings me to the end. I would like to acknowledge the institutions where I was educated, University of Zagreb and University of California at Berkeley. But I would like to say a special thanks to RSCS and the ANU, because they created an environment in which I was able to take risks with my group and continue doing fundamental research. I'd like to thank my academic mentors on all 3 continents, and most importantly, to my research group and to my family for their continuing love and support. Without that love and support, my journey to the center of the Earth would be much less special. So thank you very much.
Thank you, Hrvoje. You took me back to as a very small child, where I wondered what you'd see if you kept digging and digging and digging. So you've answered that question in a great way. Thank you. So I'll now open it up for questions from the audience. Francis.
Hvala, and I won't ask the question in Croatian. But I wanted to ask you about the Earth and the shape of the inner core. So the outer mantle is not a perfect sphere, but when you draw it, everything's a perfect sphere. Is the inner core a perfect sphere?
Yes, you would think that the change in the shape of the inner core, actually we know that it's a very, very small, right? So, and that's not surprising given such a high pressures and the way the inner core grows from the center of the planet. So at some point in the Earth's history, when the temperature drops down enough, the inner core starts growing out from the center, right? That's why, and because of the combination of temperatures and pressures, the inner core is solid, right? And it's embedded in this metallic liquid. For this reason, these high pressures and the way the inner core grows, it's not surprising that it is almost a perfect sphere.
Sorry, I've been waiting at the back for a while. May I interject?
Okay, you can.
Thank you. I'm Nalini Joshi. I was wondering about this mysterious phenomenon of geomagnetic reversal, where the North Pole and the South Pole switch places. And I wondered, is that driven by the structure of the inner core in some way?
Yeah, very good question. We don't understand this fully yet. As you can imagine, because of these hellish conditions, high temperatures and high pressures, it's very difficult to replicate these conditions experimentally. Also because of the high temperatures, it's very difficult to achieve experimental conditions where you would actually study the magnetic field and how it behaves. So you can think of these seismological images that we produce as snapshots of the structure of the inner Earth, but there are also initial conditions for the geodynamo simulations, and that's what we can do. So we can simulate the whole phenomenon of the dynamo with the computer simulations, and intuitively you can imagine that the inner core is coupled to that, right? It actually contains a significant amount of magnetic energy, despite its small volume, which is less than 1% of the volume of the Earth. So these processes are highly coupled, and I hope that this new realization that there is a torus structure, this is where the light chemical elements are. And that's important to understand how the fluid flows and how it convects in the outer core, and that's of course related to initial conditions for the geodynamo and these simulations. So hopefully this can help us to understand the reversals as well. But you don't have to worry about reversals, at least on our time scale. They do happen occasionally, but you know, when we look at the intensity and the direction of magnetic field, that's what we can do. We can monitor magnetic field on the Earth's surface. And, you know, we can get down to maybe 10% intensity loss in the last couple of centuries. But that doesn't mean that the magnetic poles are going to flip.
We can take one more. I apologize, Nalini, for not looking up there. One more down here.
Thank you. Congratulations on finding the innermost inner core. I'm just wondering, in the future, with new methods, is it possible that there's an innermost inner core waiting in there to be discovered?
Yeah, so thanks. Look, basically the innermost inner core was proposed in 2002. So with our line of research, we confirmed its existence. And something I maybe missed to say, that I hope I convinced you that we are in a discovery stage when it comes to the deep interior. The image is getting sharper because of new methods, new data. And I wouldn't be surprised, right, that in the next decade or two, we come up with some mind-boggling discoveries, not just about the Earth's interior, but the interior of other planets. And so one of them could be another doll within the innermost inner core. But in a way, this is like a time capsule that must have captured some catastrophic event in the Earth's past that changed the way that crystals grow or changed their crystallographic structure completely, which we still don't understand.
We should move on. Thank you.
Right, from the consideration of very large objects, let's change sense of scale a little bit and talk about the consideration of very small objects. So our next speaker is Professor Jean Tyson. So Jean is an internationally recognised microbial ecologist and bioinformatician who has developed and applied novel approaches to characterising microbial communities. He has pioneered new methods for studying microorganisms from diverse clinical and environmental settings, allowing characterisation of many for the first time. This has enabled a more holistic understanding of microbial ecosystems and how they influence human and environmental health. Please welcome Professor Jean Tyson.
Well, thank you very much for that wonderful introduction, and thank you very much to the Academy. It truly is a great pleasure to be a part of such an amazing group of scientists. For me, I really need to thank, first of all, Margaret Shiel. Margaret has been a strong supporter of my research since moving to QUT. She is an amazing VC who puts fundamental research and research at the forefront of what she does in her job. I also need to thank Professor Phil Hugenholtz. Phil has been my mentor from the very start of my undergraduate degree, where I met him in the second year, and now he's truly my friend. I also need to thank Professor Jill Banfield. Jill was my PhD supervisor at UC Berkeley. Jill is an amazing Australian scientist who deserves to be part of the Academy, and part of my role here is going to be nominate her for that. She is? A corresponding member. Well, Jill, call out to you. I did look this up beforehand, so sorry. And finally, Linda Backel, who is a member of the Academy, and coming from such prestigious labs, of course, has set me up for my career. So where I'll start is that we are living in a microbial world. Microorganisms are the largest biomass on Earth. There are 10 to the 30 microbial cells on Earth. These organisms play essential roles in controlling the carbon, nitrogen, and phosphorus cycle, among many others. But our understanding of these organisms has been limited, in part because when we go to grow these organisms in the laboratory, what we find is that we're only able to grow a handful of organisms. Now, the reason that that's the case is because we don't understand the complex nutrient requirements, physical requirements these organisms need to grow in the lab. And this has really inhibited our understanding of microbial communities. And so when we look back at the early 1990s, what we saw is a big change in our understanding of microbial communities as a result of the introduction of molecular approaches for exploring these communities using single gene amplicon studies, where we amplified up a fingerprint from these organisms that's universally conserved. And what that allowed us to do for the first time is get a true understanding of the diversity of microbial life on Earth. And that changed this iceberg quite considerably. We thought we were studying the tip of the iceberg, but really in most environments, when we were growing these organisms, we were studying less than 1% of those organisms. The new approaches really opened the door to a better understanding of microbial diversity, but it was only a small part of the function that we could interpret from that single barcoded gene that we were studying from these microorganisms. What we needed was access to the complete genome of each organism that was growing in these habitats. And that's where my research started. I was very fortunate to work in Jill Banfield's lab at the time that we were developing a technique called metagenomics. And what that allowed us to do was go into an environmental sample where there were hundreds to thousands of microbial species, extract all of their DNA, and reassemble it into the genomes of organisms. Now, to continue Mary's analogy on puzzle pieces, for us the analogy was a single genome of an organism would be taking the puzzle pieces from that one organism and reassembling them into a genome. But in environmental samples, that's like taking hundreds of puzzle pieces from hundreds of puzzles and mixing them all together and then trying to reassemble those genomes. And as a result of that work, what was born was metagenomics, a technique that allowed us to get access to the genomes of these organisms for the first time. We could overlay on that a technique called metatranscriptomics that Emma just talked about in her previous slides. And what that allowed us to do for the first time in these natural microbial communities was understand gene regulation and gene expression of these microbial communities. And finally, we could perform metaproteomics, where we took bulk protein extracts from these cells in order to understand what their proteins were being expressed and how they were using them. Now, as I mentioned, where my work started was actually in a very simple acid mine drainage biofilm. And what you can see here is some footage I took with the video camera I could afford as a PhD student at the time, so the footage is not great. But this was work done in Jill Banfield's group, where for the first time we demonstrated that metagenomics could work. We took this biofilm that you can see right here, we extracted all that DNA, and we reconstructed genomes for the very first time from an environmental sample. In Jill's team, we went on and we were able to use proteomics and metaproteomics for the first time to look at what proteins were turned on in each of these cells, how these organisms were surviving in this extreme environment. So the waters here are a pH of less than 1, containing abundant toxic metals. And through these new approaches, we were able to show for the first time that we could truly understand what these microorganisms are doing. One of the other pieces of work that we did was for the, in a natural community, was able to study the evolution of CRISPR-Cas. And what that meant was that we were able to look at the warfare that was going on between microorganisms and viruses that were in this system. And we saw the evolution of CRISPR within these systems. And that's what motivated Jill to walk across campus and talk to Jennifer Doudna, setting the pathway for the development of CRISPR as a genetic approach. Now, what we've done since then in my team is we've worked on a whole range of different environments. But central to all of this has been the development of bioinformatic tools that allow us to take this vast amount of data and turn it into the genomes, overlaying on that the transcriptomes and proteomes. And so some of my most widely cited papers are actually in this tool development space. But that's now allowed us to look at engineered systems through to corals on the Great Barrier Reef, to the koala microbiome, and do large-scale surveys of looking at all of the Earth's metagenomes to understand more diversity, uncover novel lineages, uncover novel metabolisms that are encoded by the microbial world. Now, as I mentioned, where that started for us was the development of metatranscriptomics, where we were able to look at gene expression through the water column off the coast of Hawaii, showing that these microorganisms were controlling gene regulation using small RNAs that we were discovering for the first time. We went on and did work where we worked in the Strat Basin, and what we were able to do there in coal seam methane wells is discover really important microorganisms that were in the process of breaking down coal and turning that into methane. But what we uncovered in that process was incredible diversity and novel lineages that were important in the turnover of greenhouse gases such as methane, but also propane and ethane. We've also discovered unrecognized microbial lineages for the first time. This was a novel archaeal lineage growing in an engineered system fed with methane and nitrate. And what we were able to discover there was a completely novel archaeal lineage that encoded all of the pathways required for consuming methane coupled to the reduction of nitrate. So these organisms were eating that methane and consuming nitrate in the process. And what we've been able to do is take that out into the environment and show the importance of these organisms in a wide range of freshwater systems. Now, perhaps the most impactful work that we've done to date is looking at microbial communities associated with thawing permafrost. And what you can see here is Stordalen Mire in northern Sweden, which has been a site that we've been studying now for 14 years, where we've been focused on understanding the microbial communities responsible for the breakdown of permafrost and the peat matrix that permafrost is made of. What you can see here is our field team and a walkway that we use to access these permafrost sites. But the thing I really want to drive home to you is that this is climate change in real time. What you can see in the middle of the slide here is intact permafrost, where you can see this eddy flux tower measuring methane and CO2. And then as we pan to the left here, what you'll see is a transition into a bog-like area called sphagnum moss, and then further into wetland sites. And you can see there the boardwalk has sunk down into the mire, and this has only happened over the course of the last 10 years. So this is climate change in real time, and what we've been able to do is uncover these organisms. We've found the key methanogen that's producing methane at these sites and uncovered the metabolic pathways that these organisms are using to break down permafrost. Now, in the last few minutes, what I want to tell you is what we're working on now. And I think one of the biggest legacies I'm hoping to leave is the establishment of the Centre for Microbiome Research, which was established in 2020 as a result of my move from UQ to QUT. As the director of that centre, we moved over with 11 people, and we now have a team of more than 60, with 6 academic group leads, including 2 postdocs that are brought through the system and now future fellows of their own, driving their own research groups within the centre. We're based at the Translational Research Institute, and we're now a complementary team who are working together to better explore microbial communities across the globe. For me, my focus has now shifted to studying the organisms that live in and on our body. The way that we're doing that is we're going after specific diseases, and we're looking at the gut microbiome primarily. And here, we're studying the organisms that live in healthy individuals compared to a range of different disease states. We're doing that in the context of inflammatory bowel disease, anxiety and depression, and in my ARC laureate, what we're focused on is developing a predictive model for how microbial communities change. So taking microbiology from a descriptive study to a predictive study. And finally, we've uncovered really interesting novel drug delivery mechanisms from the human microbiome that we're now in the process of exploiting for targeted delivery of antimicrobials. Now, at the start, I told you about cultivation, and cultivation being a massive bottleneck in microbiology. What you can see here is a facility that we just built and opened in June of this year. This is a dedicated facility for high throughput cultivation of the microbial world. What we're focused on at the moment is the human microbiome, and we're targeting the gut microbiome, skin microbiome, oral microbiome, and vaginal microbiome. And what we're able to do here for the first time, using single cell deposition events that you can see that's performed on this flow cytometer on the right-hand side, is we're able to grow organisms for the very first time. We've now cultured more than 700 species from the human gut, most of these completely novel species that we've never had in culture before. And it's high throughput approaches like this that I think are really going to change the way that we're able to explore microbial communities and really validate the multi-omics hypothesis that we've been developing over the last 20 years. For me, what I see this is as an opportunity to develop new therapeutics or our next generation of probiotics, because really what we're able to do with this biobank is we're able to turn this into new drugs that will be developed for a range of different diseases. And I'm really excited about the future in this space. With that, I have to thank an amazing team of scientists. Throughout my career, I have had an enormous number of PhD students who have been exceptional and gone on to big things. The team at the Centre for Microbiome Research is an amazing group of people, and I love being able to foster their careers on a daily basis. Of course, I also need to thank the funders, because as we all know, funding is sparse. But we've been very fortunate to have funding from the ARC, the MHMRC, as well as the MRFF and, of course, the National Science Foundation. And without this, none of this fundamental work would be able to be done. And so I think it's with this that we all need to work to ensure that fundamental science continues here in Australia. Thank you.
Thank you, Jean, for a wonderful talk. Yet another example of great science communication as well. Such a pleasure to listen to these talks this week. Do we have any questions? Oh, here we go. Lynn.
Thank you for an inspiring talk, all the way from looking at permafrost through to the human situation. I think it's marvellous. Could you talk a little bit more about your work? We hear a lot about, say, methane being released as the climate warms. Is there any insights from your work on, to even tell us the level of danger of this happening and how we might take mitigating measures?
Yeah, that's an excellent question. It's been one of the focus of the work that we've been doing in permafrost. So it's currently estimated that the amount of carbon stored in permafrost is equivalent to the amount of carbon currently in the atmosphere. And if that was to be released, the consequences for global temperatures could be disastrous. Our work has really highlighted the key lineages that are important in that methane and CO2 release. Unfortunately, short of going and deploying some sort of antibiotic or large-scale microbial eradication program in these regions, we're not going to be able to do anything immediately. What we can do, though, is develop targeted delivery systems for key organisms that are responsible for that methane or CO2 generation, or the precursors of that, or try to redirect that carbon into other compounds. And so I really think that's the future, is targeted deployment to remove certain organisms that are causing the problem, or redirection. And I think that's where the future is going to be in this space.
Thanks, Jean. Wonderful talk. And it seems like what you began with in terms of those single cell culturing activities, you're going back to now, but on a much larger scale. How much do you think we will be able to predict the result of a community of microbes from the activities of the individuals?
Yeah, that's a great question. And part of the reason that we're developing this biobank of organisms is to ultimately go back and reconstruct them to see how they act when they're interacting with one another. I think one of the valuable points of having the organisms in culture, and the reason that we've gone back to making this a priority, is because we were generating all of these multi-omic observations, but we had no way of validating what was going on. So we could make a hypothesis that an organism was responsible for a key metabolic pathway, but we had no way of validating it. Now when we generate those hypotheses, we can go back and test it. And I think that's the true value. I think that environmental monitoring and microbial analysis is still going to be absolutely essential for really developing that global picture of what the important processes are that are shaping Earth systems. But I hope the biobank, at least in the context of the human microbiome now, but in the future other environments, will provide some valuable validation for those observations that we're making.
One more question up the back.
Thank you for an amazing talk, really interesting data. And I note in your last slide, you're starting to work on human gut microbiome as a cancer specialist, and in our lab, we've been looking at the gut microbiome as it relates to immunotherapy. But one of the controversies in the field, and I'd just like your comment on this from a cancer specialist point of view and researcher, is this concept of enterotypes and microbial ecosystems, which there seems to be sort of a very polarised view of that. I'm just wondering, from our perspective, what are your comments or thoughts on that, or have you come across this?
Well, Georgina, I've been meaning to come and find you, and you've been swamped by people, which is not surprising, because I actually wanted to talk to you about the importance of the gut microbiome in the context of cancer treatment and turning non-responders into responders, because that's obviously an exciting area of research. So for those of you who don't know, one of the big areas that's emerging is that you can take someone who is on the drugs that Georgina was talking about earlier today, and you can turn someone who's not responding to those drugs into a responder by modulation of their microbiome. They're not using the right organisms, so we should collaborate on that. So I think the enterotype definitions for me are breaking down. What we're seeing is a whole heap of diversity in the human microbiome that causes those traditional 16S, largely 16S based enterotypes to break down. For me, I think that what we're seeing is that this is actually a much more complex picture that needs greater study before we can conclude that someone fits into a certain microbiome type. And what we're seeing is the diversity of that. There's certain predictors. You can tell someone's microbiome based on their age, their sex, whether they drink, they smoke, all of these things. I don't want to minimise someone's microbiome down to one of 3 select enterotypes or whatever the number is now, because I think everyone's microbiome is unique, and whether or not you're going to have certain diseases is going to come down to whether you've got these key sets of organisms, not single organisms. And I think that's where the field's going.
Please join me in thanking Professor Dean Tyson. So, let me put my glasses on. So continuing on the theme of microbes, our next speaker is Professor Madeleine van Oppen. So Madeleine is an ecological geneticist and expert on microbial synthesis and climate adaptation of reef corals. She has revealed mechanisms by which corals adapt or acclimatise to environmental change, and built a platform of innovative assisted evolution technologies that harness the natural adaptive mechanisms to enhance coral climate resilience. And technologies critical to coral reef restoration in Australia and overseas. Please welcome Professor Madeleine van Oppen.
Thank you for that introduction. It's quite amazing to be standing here, and I'm very grateful for the recognition that my research is receiving in this manner. And I thank the Academy, and in particular I'd like to thank John Oakeshott, who nominated me for this fellowship. So let's talk about coral reefs. Coral reefs cover about 0.1% of the ocean surface area, yet they are incredibly important to support marine biodiversity and also in providing goods and services to human populations. Corals are home to about 1/3 of all marine species. They also have incredible economic value through provisioning jobs and by supporting industries such as fisheries and tourism. They protect our coastline from erosion. They contribute to human well-being by providing not only food and lots of products, but also because they have a very high cultural and cultural value. Sorry, I lost my train of thought there for a second. Unfortunately, coral reefs are declining rapidly across the globe, and that is due to a number of anthropogenic disturbances. And climate warming is really the biggest threat to coral reefs at this moment. Climate change not only manifests as a gradual increase in sea surface temperatures, as you can see here, but also as an increase in the frequency and intensity of summer heat waves. And it is those summer heat waves that drive the loss of the microalgal symbionts from the coral tissue, and we call that bleaching. And whole reefs can become white, as you can see in this slide, during mass bleaching events. Now, corals rely on these microalgal symbionts for most of their nutrition, and mass bleaching events cause the coral to starve and often result in extreme coral mortality. Now, it's generally believed among coral reef scientists and managers that there's 3 actions that we should take to prevent the further decline of coral reef. First, of course, we need to deal with the root causes of climate change and reduce greenhouse gases in the atmosphere. Secondly, we need to improve local conditions such as water quality by more conventional management. And thirdly, we need to develop and implement coral restoration interventions so that, well, basically until the climate stabilizes and coral reefs can recover naturally. Now, one such intervention is assisted evolution or human-assisted evolution, which is a series of bioengineering methods aimed at accelerating natural adaptive processes and enhancing coral climate resilience. Assisted evolution can target either the coral host animal or any of its associated microorganisms. And today I will talk about microbial manipulation. Now, of the many microbial groups that corals associate with, we really have only worked with the microalgal symbionts and the bacteria. And bacteria form a very diverse community within the coral polyp, and they occur throughout the whole coral polyp. You can see that here. They occur in the mucus layer that covers the outside of the coral, in both cell layers, in the gut, and in the coral skeleton. The microalgal symbionts, however, are more restricted in their distribution within the coral polyp, and they reside solely in the cells that line the coral gut, the gastrodermis. Now, coral heat tolerance is largely determined by their microalgal symbionts, with heat-sensitive and tolerant species occurring in nature. However, corals that associate with heat-tolerant symbionts are often nutritionally compromised, and that manifests in things such as reduced growth, lower fecundity, and things like that. And it's also important to know that even corals that associate with heat-tolerant symbionts have been observed to bleach during extreme summer heat waves. So we felt that this was an area that is probably quite suitable for human-assisted evolution. Luckily, we can culture a lot of the microbial symbionts, and at the Australian Institute of Marine Science, we have established an extensive culture collection of the symbionts. And we have subjected a subset of these, mostly the heat-sensitive symbionts, to laboratory selection or experimental evolution using elevated temperature as the selective agent. Once we've done that, we reintroduce the heat-evolved symbionts, as we refer to them, back into the coral host. Now, this is relatively straightforward when we're working with early life stages of the corals, the larvae and the recruits, because most coral species do not transmit the symbionts from the mother colony to the offspring. They have to acquire those symbionts from the water column. However, if we want to reintroduce these symbionts directly into the adult stage, it's a little bit more challenging because the adults have already established that symbiosis with the microalgae. And so therefore we have developed a chemical bleaching method that can remove more than 98% of the native symbiont community. And once we've done that, we simply expose these bleached coral fragments to the algal cultures, the heat-evolved cultures, and we've seen that in many, many different coral species, we can establish some new symbioses in this manner. And we have indeed seen in our laboratory experiments that when we introduce the heat-evolved symbionts, the corals have enhanced heat tolerance in the larvae, the recruit, and the adult stage. And what's even better, this occurs without compromising growth rate. So in other words, that trade-off we see between heat tolerance and growth in corals that associate with these natural heat-tolerant symbionts, we haven't seen that in our lab experiments. So it's pretty exciting. Now, about a year ago, we started a small field experiment where we developed adult coral fragments that either harbored a heat-evolved symbiont or wild type, and we deployed them at one location in the field for now. And these experimental corals experienced extreme heat stress in the last summer when the Great Barrier Reef had an extreme heat wave. And our preliminary data suggests that these experimental corals actually have enhanced tolerance. So actually it confirms our laboratory results, and I will show you this in the next slide. So these corals sit on little settlement devices. They're a few centimeters in diameter. We put them on a table which is placed right next to the wild corals. You can see that here. And during the summer heat wave, the colonies around the wreck bleach severely. You can also see that in this image, including corals of the same species as our experimental corals. Now, this graph here shows the response of the experimental corals. Each pie chart represents a coral fragment, and the colors represent the symbiont composition, the community composition of the symbionts in the fragments. So I've plotted a change in color, which is a proxy for bleaching status, over a 3-week period at the height of the summer heat waves, and I've also plotted the photosynthetic health of the fragments. And you can see that fragments that had heat-evolved symbionts, those are the ones that have black and purple colors, bleached less, and some actually increased in pigmentations, and they also had higher photosynthetic health compared to fragments that had the wild-type symbionts, which are shown in yellow. So we're pretty excited about this because this confirms our lab results, and it's the first field data on using these heat-evolved symbionts as a means to enhance tolerance in corals. And we're now in the process of increasing the scale of these experiments, placing experimental corals at multiple sites, different coral species, different symbiont species, and so on. And I'm also very happy to say that we've been able to push the upper thermal tolerance limits of naturally heat-tolerant symbionts. And so we are now running experiments where we test their performance within the coral holobiont. Now, the manipulation of bacteria is a less advanced intervention, and basically we are working on identified candidates. And some of the key criteria we use are first the bacteria need to be easily culturable. They need to form a temporally stable symbiosis so that the benefits will occur long term once we deploy corals on the reef. And they need to have traits that are likely beneficial to the coral holobiont, and actually quite challenging to figure out what traits we should focus on. So initially, because coral bleaching is driven by an overproduction of reactive oxygen molecules, those are toxic molecules by the algal symbionts which then leak into the coral cells, we're focusing, one of the key traits that we're focusing on is Ross scavenging ability of the bacteria. And then a second trait is the ability of bacteria to export carbon, because when corals bleach, they starve, and perhaps bacteria can help the coral survive that period of starvation. And the way we do this is via a combination of cultivation and genomic and microscopic analysis. So in this example, and please don't try to read everything on this slide, but here we cultured a representative portion of the bacteria that associate with this coral in this picture here. About 80 or so bacterial species we have there. We sequence their genomes, and then we use genomic prediction to see what sort of Ross scavenging features are present within that genome, and that's indicated by those colored circles behind the bacterial taxa. And we also looked for the presence of a transporter that may be able to export glucose. In a second example, we also looked at the localization of these bacteria using species-specific probes. For instance, here at the top right, in pink and yellow, you can see two different bacterial species that co-occur as clusters within the coral tissues. And as in the first example, we then used a whole genome sequence of the bacteria to identify potentially relevant genes and pathways, but we also looked in this instance at the host genome data so that we could try and understand interactions between the bacteria and the host. So using this approach, we now have a set of bacterial candidates that we are testing in corals via administration of the bacteria to the coral. And now I'd just like to stress how important thermal enhancements is in coral reef restoration. And I'd like to do that based on an example from the Caribbean last summer. So the summer of 2023 was the most extreme heat wave in the Northern Hemisphere. And in the Florida Keys, there's quite a bit of coral reef restoration happening. And then in this particular example, about 1,500 corals that were nursery bred had been outplanted to the reef. And during the summer heat wave, about 80% of these fragments of these corals died, and 5 of the 7 restored populations were completely wiped out. So these corals were not enhanced. Now, on the Great Barrier Reef, we also saw extreme heat stress during the 2024 summer, not as extreme as in the Caribbean, but mass bleaching events are accelerating. We had 5 mass coral bleaching events since 2016. Also, outplanting of corals on the Great Barrier Reef is beginning. And so if we do not enhance the corals that we outplant, it's quite likely that come the next summer heat waves, we may lose everything and a lot of resources and efforts will be wasted. I'm going to leave it at that. I'd just like to acknowledge the traditional owners of the land where we meet today, and also the traditional owners of the land and the sea countries where the research was presented. I'd like to thank my funders, and most importantly, my team members, without whom this work would not have been possible, as well as some of my really important collaborators. And thank you very much for listening.
Wonderful. Thank you, Madeleine. Do we have any questions? Oh, we have one up there. Nerilie?
Thank you. That was a wonderful talk and such important science for looking at how we can try and keep the Great Barrier Reef alive. And I'm just wondering, with the scale and the urgency of the problem, what's going to be needed to deploy this at the scale of the whole sort of Great Barrier Reef, and can it be done fast enough?
Yeah, the scale is a challenging question, but we're working on that. And one thing that is important that, to deploy an intervention at the scale of the Great Barrier Reef, we think we will need to involve industry. In terms of specifically enhancing tolerance via the manipulation of the microbes, and particularly the photosymbionts, because there are some symbiont species that are what we call generalists. They have a broad host range, so those are the ones we're working with. So if we enhance one symbiont species, that might provide benefits to multiple coral species. It's also quite possible that we can simply inoculate the sediments on the reefs, and because corals will then automatically acquire them. In the lab, we've demonstrated that that happens. Even the heat-evolved ones, they are expelled by the corals, and they can be taken up by other corals. We have demonstrated that in the lab. So those are possible ways by which we can maybe achieve this at the scale that is necessary.
Madeleine over here. So Madeleine, as you're getting towards deploying these evolved strains of the symbionts and so forth, are you getting any pushback around public concern of GMOs or genetic manipulation in natural ecosystems? Mm-hmm.
Yeah,
and if so, what are you doing about that?
Yeah, so these are not GMOs. So we have not genetically modified these organisms. We have simply exposed them to elevated temperature in the lab. So we suspect that genetic changes have occurred, or at least epigenetic changes, because the increased tolerance is stable over multiple years. We've demonstrated that. We haven't identified the genetic changes. So I think because they are not GMOs, I don't think that's going to be a big issue. I think initially the biggest issue was that, well, we cannot contain them because corals, even healthy corals, will expel them all the time, and there wasn't full understanding by the regulators, what they were or whether that was risky. So we're also working at assessing not only the ecological benefits, but also the risks. These organisms will end up in the environment, and part of that first small field experiment is to also assess the risk and to be certain that we can do this at a larger scale safely.
We have one more question up the top here.
What can ordinary people do to help coral reefs?
Well, most importantly, I think whatever you can do to minimize further global warming. So look at the way you live, what sort of energy sources you use, how many children you have is important too, because a lot of these problems are caused by the large number of people on this planet. So those are things you can easily do as an individual. You could also choose to become a politician and try and influence policy, or go into coral reef research and help develop some of these interventions.
Thank you, Madeleine. And a hand back over to Jim.
Thank you, Ian. I now call on Professor Lianzhou Wang. I can just find my notes here. Lianzhou Wang is a renowned researcher in material science and chemical engineering. He has made unique and enduring contributions to the development of functional nanomaterials for solar cell production, new generation solar cells, and batteries. Please welcome Professor Lianzhou Wang.
Good afternoon, everyone. First of all, I would like to thank Jim for the introduction. Also, thank the Academy for giving me the opportunity to stand here. Actually, I have never dreamed to, be able to be part of this prestigious academy. Because I was trained as a ceramic researcher, and which already have 1,000 years of history. And you think about, talk about ceramics, you can easily think about it like the potteries, porcelains, or even terracotta vases. And but in broad sense, basically the ceramic can also contain many other things. And like all inorganic non-metal materials can be considered ceramics, like concrete, glasses, and the modern ceramic also have many applications well beyond the traditional ones. But this all depends on the materials you prepared. Like if you look at the materials at microstructure level, like the composition, the size, shape, and also the processing can actually determine the property of the materials you prepared. Like if you're talking about the process for ceramic, and you can, it's like you starting with the raw materials, and you mix them with solutions, and then you mix them, and then to prepare the shape, we call it green body, and then you cook it in oven and in furnace. You may find some similarity of the ceramic processing with your cooking. So this is also the joke I quite often have with my students. So, and as you design the material, basically you like a cook a dish, but how good your dish looks like is depending on the scale of the chef. So then what's the trick? The trick basically is go back to the fundamental theory. Like here we have the nucleation, crystal growth of the materials. We have the interface engineering, and we also look at the dynamics, and so also the thermokinetics of the process, like phase changes. So in the past 20 years or so, in the past 20 years at UQ, and I have been focusing on the material design. And for the renewable energy application, we look at from the solar energy convert to chemicals, like to produce hydrogen for the CO2 reduction. We also look at the new type of solar cell design for the electricity generation. And we also actually look at the storage of the electricity and using battery system. But in the heart of all this system, actually, semiconductor material play a critical role. That's what we have been working on in the past years, try to apply the old theory and in the ceramic processing and for the new energy application. So, and I just use two examples to show what we have been working on in the past some years. And like the first example you might already heard from this morning's presentation is about the perovskite. Perovskite is a star material in the past 10 years or so, and for using as the light absorbing material for new generation solar cell, which can be very cheap and also have very high efficiency. And the perovskite material and can not only be prepared in such big crystal, it can also be prepared in very, very tiny fashion. We call it quantum dots. Basically, it's only a few nanometers in size, but the property can be very unique from the bulk one. It's very different. And for this reason, and the quantum dots also got the Nobel Prize last year. And these three gentlemen for this finding about the quantum dots for use in like the TV screen and also the LEDs. And the perovskite can also be prepared in the quantum dot fashion. And they also hold some hope for the solar cell application because they can prepare on the flexible substrate and can also be produced without any heating. It's very different from the silicon-based solar cell. So low cost and low and actually energy input. So, but the quantum dots-based solar cell has some difficulty. And in the past 10 years or so, the power conversion efficiency actually has been stuck in about 13%. That's mainly because of this, to prepare these dots, which normally need, like we call the surface ligand, basically, so like this fluffy stuff on this cube, and which on one way will help to prepare the quantum dots, but on the other side, and because of the insulating nature of this fluffy stuff, it will also block the way for the electron to pass through and affecting the solar cell's efficiency. So, and our team have been, design the interface, interaction between this fluffy surface ligand and the quantum dots. Actually, try to actually increase the conductivity between, like the communication between the dots, but also keep the dots to be in good shape and good crystallinity. And like we can prepare a range of quantum dots with different size, different composition, and also different property. And we apply this into the quantum dots-based solar cell and achieved a efficiency, the certified efficiency of 16%, over 16%, and which also help us actually to put our UQ's name on this, the so-called best research cell efficiency chart. And if you don't know about this chart, it's something like the Olympic Games in the solar cell category, and it's collected, the record in the past 50 years. And on this chart, you may see a number of dots, actually contributed by Professor Martin Gray's team from UNSW, and we are also lucky to have one dot actually from UQ, and we may need to work hard to have some more dots to be on this chart, so in the future. So now we're talking about the good side of the perovskite, and what about the bad side? So perovskite actually have two big challenges. The first one is the stability, and because of the unique nature of this material, and basically they are not very stable. They are sensitive to everything, to moisture, to oxygen, to heat, and so we really need to make this stable and for the perovskite material to be used in solar cell and in other areas. And we applied the old ceramic processing theory. In here, we use the ball milling to mix our perovskite nanoparticle with some other species. And we also use the phase diagram and to control the phase change. And like the glass sintering process, basically we quench the material from high temperature to room temperature, and to offer this material like a monolith glass, but the perovskite nanoparticle embedded into the matrix, and which can offer this composite with very high stability, much higher than the perovskite itself, but it has also very good functionality, like the light emitting property in this case. So, and we also can, to address another issue about the toxicity, because the current perovskite material all contain lead. So if you want to apply the lead-based solar cell on the rooftop or your unwearable device, you may have the concern from the public about how the toxicity. So then we have been focusing on how to change the composition from lead and to the less toxic tin-based one. And in the past some years, actually this area has also become very busy. But a problem for the tin-based material is that it has a very fast crystal growth process. It's very difficult to control. So then these are the things actually I told our students. If it's something about the material preparation, crystal growth, crystal control, that's our expertise may contribute to solve this problem. So then we apply the similar process. In this case, we still do the cooking, but we try to add some seasoning to the system, like we call it dopant. We add dopant to the system and try actually to stabilize, to slow down the crystallization process in this case, and we can prepare quite a uniform thin film of the perovskite, which are able to help to increase the solar cell conversion efficiency. And in the past, some years, the certified efficiency in this category has been stuck around 15%. And recently, in the lab, we already achieved more than 17%. The service certified efficiency about 16.6%. But we are actually very confident this efficiency can be further, improved based on our, knowledge in the ceramic processing and the crystal growth. So. And another area I'm working on is still also try to apply, our ceramic processing theory and to improve the property of the battery materials. So like the battery materials, and so many battery materials actually they have good performance, but they not last long. And our strategy is also still to use the cooking process, give them like a sugar coating, and to give the material looks better and also tastes good. So then this material can last for much longer cycling life. That's basically give the material, the battery, a longer life. And then currently we are working with a number of local industry partners And Australia is very lucky to have so many critical minerals, but actually we still have a lot of work to do actually to increase to upgrade our value chain. And in this regard, actually we have been working with the industry partner actually to upgrade our the battery material design, and with the better performance. I was also very lucky to receive the ARC Industry Laureate Fellowship a few months ago, and to work with the local industry partners and to further improve the battery performance. And with this, I would like to thank many people and my team members, our long-term collaborators, and also my family, and my wife Helen is here. And in particular, I wish to appreciate a few people here. My nominator, Professor Deborah Burhardt, and my supervisor and mentors like Professor Max Lu, Ruth Amo, Jim also helped me a lot, Jagdish, and Professor Huijin Zhou, and many others. With this, thank you very much.
Thank you, Lianzhou. And I wish you well in the Solar Cell Olympics in the future.
Thank you.
Can we open it up to questions now from the audience? Here. Francis, yet another question.
Thank you. It's good to hear that you can replace the lead with the tin, and you've got the efficiency up to almost 17% now. But what about the stability? How stable is the material?
So in this case, we also look at the stability now. And there is a tin-based one. So traditionally, the stability is not as good as the tin-based one. But recently, we also add some like redox couple and to stabilize this process. Basically, it's have like a so-called self-sealing process. And it's, at this stage, it can be stable up to 2,000 hours, and it's still going on. I think we still, we should continue to work on to improve the stability of this material.
Fascinating talk. Thank you very much. Tin is about 100 times as expensive as lead, isn't it? Will that be a problem?
I'm not sure whether it will be 100 times, but certainly it's more expensive than lead. But in the application, this one, the film prepared by the prepared with the perovskite is very thin. So it's only a few hundred nanometer thick. So which means if you cover square meter side, it will be using a very small amount of materials, but it still can have a relatively good efficiency.
How long will tin-based solar panels last compared to like lead-based solar panels?
How long are you thinking the solar for the
how long will a solar panel with like the tin-based technology last compared to one with the lead-based technology, like a solar cell?
So we are still in the developing stage. I think this is very relevant to Francisca's question. And now we continue to increase the stability. As I said, it's about 2,000 hours. I understand for the lead-based one, it's going to up to tens of thousand hours already. And we will work hard.
Thank you. I think we should move on.
Okay,
thank you again, Lianzhou. Hand over to Ian.
So, thank you, Jim. So our next speaker is a corresponding member from Sweden, Professor Erik Warrant, from Lund University, I think. So Erik is a world leader in the fields of neuroethology, comparative vision, and visual ecology, as well as navigation in extremely dim light. He has elucidated the optical and neural principles that improve visual performance in nocturnal and deep-sea animals, and discovered the sensory mechanisms that enable nocturnal animals to navigate while homing or migrating. Please welcome Professor Erik Warrant.
Okay, well, thank you very, very much to the Academy for this immense honour to be among this amazing group of people. And I'm very, very grateful to you for this. And I'm very grateful to my nominator, Professor Srinivasan from the University of Queensland. And I accept this honour on behalf of all the wonderful students and postdocs and collaborators that I've had over several decades now doing this work. And so I dedicate this to them, actually, because as we've all said so far, we would not be standing here if it wasn't for the fact that we had so many wonderful people to work with. And it's been one of the greatest joys of my life to be able to do that. I also want to thank my fantastic and wonderful and supportive family who are watching live online from Sweden. So this is a great thrill for me as well. I had the fortunate upbringing to live in a rainforest when I grew up. And when I was there and I played in the rainforest all the time as a little boy, I became fascinated with insects. And that fascination has only grown. And I've spent my life working with them. And the thing that really has amazed me and still amazes me and keeps me in awe of this group of animals is the fact that they're extremely small. They have a brain that is typically less than 1/10 of the volume of a grain of rice. But they can see, they can smell, they can feel, they can hear, they can fly, and they can walk. And they have a complex lifestyle that rivals that of many vertebrates. And yet many of them are less than 1 millimetre long. And this for me is a true miracle of evolution. And I want to talk about one of those, for me, miracles of evolution, and that is their ability to see in extremely dim light, which they do, I hope, to show you, they do extremely well. You may not realise, but starlight is about 100 million times dimmer than sunlight, and we're day-adapted animals, so we're used to the brighter end of this range, but there are many, many animals that are used to the very dimmer end of this range. And the problem for vision is that this makes vision extremely unreliable, and this is obviously because the light levels drop and the signal therefore goes down. The relative noise levels are greater, and thus you experience a much lower signal-to-noise ratio. But despite having extremely tiny compound eyes, it turns out that insects nonetheless have stunning night vision. And I hope with just a couple of examples from all the many different examples of insects that we've worked on in the past to convince you of this and to try and explain how they do it. The first example is this absolutely beautiful European hawk moth that looks for flowers at night and looks for them, it turns out, on the basis of their colours. By training or teaching moths to associate colours with food, we were able to determine that they could see colour at light levels where our colour vision was completely gone. And in fact, this was the first animal to be shown to have nocturnal colour vision, and a few other animals have now been found since. This animal that I've been working on, you've heard a little bit about already. I currently work on a lot, the Australian bogong moth, which is a remarkable long-distance navigator. It has a spring migration that begins from all over southeastern Australia. They fly about 1,000 kilometres in different directions to a single destination, which is a small group or a small number of alpine caves dotted across the ridges of the Australian Alps. It's a place they've never been to before. And we've discovered that they're able to use their small brain and their very small eyes to see the stars and to use the stars as a true compass to find their way. And in fact, there are only 3 groups of animals that are known to be able to do this. That's us, ourselves, with the aids of different kinds of instruments, some species of night migratory songbirds, and now bogong moths, which is the first invertebrate animal known to have this ability. And I'll just remind you, this is an animal that has a brain 1/10 of the volume of a grain of rice and extremely small eyes. This last third example is a nocturnal bee, and believe it, there are actually nocturnal bees in more tropical areas of the world. This bee, Megaloptogenalis, comes from Central and Northern South America, and it navigates at night through a rainforest like this from a nest stick that's very inconspicuous in the undergrowth. It travels hundreds of metres through this kind of environment in the pitch dark of night to look for flowers and finds its way home again. By manipulating visual landmarks around the nest, we were able to show that they are able to do this phenomenal task completely visually. And here is a landing in real time of a bee in very, very dim light. This is actually filmed in infrared light. And here it is again, if I can get it to work, to the next slide. Here it is again, slowed down 10 times. By recording from individual photoreceptors in the compound eye at the same light levels, we were able to determine that while it was performing this precision landing visually in the dark, each of its photoreceptors was absorbing 5 photons every second, which is a remarkably low visual signal. And our question has been now to try and find out how on earth do we bridge this gap between this incredibly small visual signal, low visual signal, to this incredible behaviour that you see on the right. And our hypothesis has been for a long time that they're using mechanisms of neural summation of light in space and time somewhere in the brain to be able to enhance the visual image at night and make it much more reliable. And this is the brain of a bogong moth. It's a very sophisticated organ made up of many different regions. The yellowy orangey areas are areas devoted to vision, visual processing. They have many areas which are similar to our own visual cortex. And just to explain what we mean by spatial and temporal summation, in time, in temporal space, this is like having a camera where you increase the exposure time in dim light to allow more light to reach the image plane. That makes the image brighter, but of course the downside of that is everything that moves rapidly is much more difficult to see. In other words, temporal resolution is sacrificed. In space, there might be neurons that actually pool together the very small visual pixels that give you high spatial resolution and make larger, brighter pixels. The downside of that, of course, is that the image gets coarser. In other words, spatial resolution declines. But it might be better to see a brighter world that's coarser and slower than to see nothing at all, which in fact would have been the only alternative. And with this in mind, I sat down and developed a theoretical model to try and measure visual performance as light levels fell and invoke in that model spatial and temporal summation to see if it improved vision. And the result of that model led us then to test it using films that we actually recorded with video cameras in extremely dim light to find out whether those mechanisms we determined in insects could actually improve dim light video. So here you see such a video. You can see a few little lights there. This is the train set world where we have a camera mounted on the train driving through an environment. This is the raw camera output from this film. And if you apply these principles of spatial and temporal summation to this image or to this video, you get the following. So not only do you see a much better, brighter world, it's a little bit sort of blurry and slightly sluggish, but it's very clear that you see things there that you didn't see in the previous film. And moreover, you're actually able to retain colour. And this gave us a very strong clue that colour vision in insects and many other nocturnal animals, presumably, is probably subserved by these mechanisms of spatial summation of spatial and temporal summation of photons neurally. And so we've now determined that this is likely to be the explanation for this gap between what's happening in the eyes and what's happening in the behaviour. And indeed, we have now found actually the circuits in the brain which are responsible for spatial summation. We've detected temporal summation in higher visual processing in the brain as well, but we haven't yet located the circuits which do the temporal summation. We're still looking for them. And so for changes. Yes, and these, as you might have seen in the film yesterday, these principles that we've uncovered from insects have now been, or are now currently being applied by the car company Toyota to create new types of cameras that automatically adapt to different light levels and change the both the temporal and spatial resolving power of the camera as light levels fall in order to optimise the camera's output. And they're intending to put these cameras into cars to aid drivers in detecting objects on the road, people and animals, before the driver themselves actually sees them. So our work over some decades now has now led us to understand that visual summation very likely allows many nocturnal animals to see extremely well in dim light, even little animals like insects with tiny brains and tiny eyes. And with that, I'd just like to thank you for your attention, to thank all of our funding bodies, and of course, once again, to thank all the fantastic students and postdocs and international collaborators that I have worked with and continue to work with, and hopefully will continue to work with in the coming years. Without all of you, as I said, I wouldn't be standing here. Thank you so much.
Thank you, Eric.
You're welcome.
We have a question right down here, straight away.
So it occurs to me another challenge you might have with summation is that the field of view is not static, especially if the animal is moving. And so it seems like that might be another limitation, that the field of view gets smaller because you can only sum over the things that are held in the field of view over whatever your integration time is. Have you explored that at all?
Yes, actually the modelling takes that into account. So one of the necessary side requirements is that if you start to sum longer and longer in time, you have to move more slowly in order to be able to see things. So that's why you tend to find that nocturnal animals move more slowly than day-active animals do, probably for that reason. But it really depends on your lifestyle. So if you're anyway a reasonably fast-moving animal, you can invest more into spatial summation and less into temporal summation. So the exact balance between the two can be moved around according to your actual velocity.
Hi, thank you so much for a very fascinating talk. So so you mentioned two examples where insects navigate through a rainforest and also navigate using the stars. So I was just curious, so what kind of experiments are performed to conclude whether the insect is using like some landmark on Earth or some landmark like stars?
Well, I can tell you about the experiment with the stars because I was going to mention that and just realised I forgot to briefly mention that. So we had them tethered, and migratory moths that we'd caught while during migration, we had them tethered on a little stalk, and then we connected them to a device where we could track their virtual trajectory over a period of time relative to north. And then we projected a natural night sky, in fact, the same night sky that was outside the lab at the time of the experiment. And then we had big sets of Helmholtz coils around the setup where we could get rid of the Earth's magnetic field, so that had no effect at all. And then we literally just simply watched where they went under the starry night sky. And they flew in their inherited migratory direction, both in spring when they were travelling towards the mountains and during autumn when they're travelling away from the mountains. They were flying in the right direction. If we rotated the night sky by 180 degrees, they turned and flew in the opposite direction. And then if we took the individual stars of the night sky and randomly scrambled them across the screen above them, they were totally disoriented. So it's experiments like that we've been using.
We could take one more question. There's actually one at the back, sorry.
Thank you very much. That was an absolutely fantastic talk.
Thank you.
When you sum signals in certain types of noise, you will also be summing the noise. Is there a part of the brain that's doing something about deconvoluting that noise in some way?
The lucky thing in visual systems is that visual signals are correlated from one sort of photoreceptor to the neighbour, but noise is not. So that when you do this summing, which is a form of averaging actually, what happens is that you enhance the signal at the same time that you average out the noise. And so it's a fantastic way of improving the signal-to-noise ratio. We've done all those experiments, but they were too complex to describe in this talk. Yeah. Okay, thank you.
Thank you, Professor Eric Warren.
Our next speaker is Professor Willie Swanepoel. Willie is a leader in experimental software systems. His work on distributed shared memory has made fundamental contributions to a variety of subjects, including multicast communication, fault tolerance, internet servers, graph processing, visualization, and storage systems. Please welcome Professor Willy Zanderpoel.
Thank you for the introduction, and thanks to the Academy for electing me as a fellow. Particularly gratified to be a member of the Academy of Science because I really never had imagined in my life to become a scientist. I call myself an accidental scientist. I grew up in a small village in Belgium. My brother and I were first generation high school graduates, let alone university students. I was studying electrical engineering because I thought I could get a job that way. But one thing happened in the lab where I did my undergraduate thesis is they bought this machine that those of you of my age may remember. It's a PDP-11. It was the first microcomputer. And I thought, well, this is kind of interesting stuff. So I asked my undergraduate advisor, I want to learn more about this, what should I do? And he said, well, US is really ahead in this game, so you should go to the US. So I did. So I got a grant from the Belgian American Educational Foundation, and off I went to Stanford for a year to do a master's degree. That year turned into 23 years because I found a lot of interesting things there. So the two sort of things that really struck me when I went to Stanford, first of all, is the number of amazingly smart people that were there. And there are many of them. I just singled out two here, my two PhD advisors, Forrest Baskett and David Sheraton. Both of them billionaires by now. I'm still working on that. The other thing that I sort of found remarkable is that they had time to listen to you, me who knew nothing, basically. And then the final thing was there was some totally cool technology. Technology that by today's standards you'll find, ridiculous, underpowered, but by the standards of those days, they had the Sun workstations, the first workstations, and having a computer to yourself that I had never heard of. And then they also had Ethernet that was developed at Xerox PARC. It was 10 megabits then. Now, again, that sounds ridiculous, but in those days, 1200 baud modems were the norm, so this was really sort of a sea change for me. So we were starting to use those, and I noticed these things had a problem. And the problem was the disks. The disks were not insulated in any way. They were meant to be in machine rooms, not in people's hands, like it is in this voice. And so besides being big and clunky and slow, they crashed a lot. And so this was a real problem with the development of these kinds of systems. And so we had this idea, and this is a picture from my thesis actually, that I dug back up for this purpose, of building diskless workstations. So the disk would be in the machine room with the server, and then the workstations would be on the network. And again, this may sound sort of obvious in the days of clouds, but in those days that was quite a revolutionary concept. So this is my first paper. So computer scientists often publish in conferences, not in journals. So I thought this was a good life. They pay you for what you like to do, so I became an academic. I went to Rice, and there I sort of worked on similar things, to build sort of, you had these powerful machines now, they were connected to the network, why not try to get them to work together on sort of hard computational problems. So many people had that idea. The thing that I guess I'm known for is the concept of distributed shared memory, where you sort of try to create an illusion that all these machines have a single memory, which makes programming them much, much easier than if they have separate memories. So that was sort of that's actually the paper I'm best known for, that appeared in '96. So then along came the internet, and if you were around, you will remember this number 503, which was an error that the server would return or that you would get back from your browser saying the service is unavailable. Well, actually, the service was not available. It was just keeling over because it had too many things to do. These machines, both the hardware and the software, were designed to, take 10 requests per second, and now there were thousands of requests, and so these things were not prepared to handle that. So there are many ways of dealing with that. I worked on a concept called the reverse proxy, which is the thing here that you see sort of here, which is sort of a front end to the server that takes a lot of work away from the server and also distributed the work to many different machines. So we wrote a few nice papers about that, but I was sort of getting tired of writing papers. So this was my first company. It was called iMimic Networking. Our timing was perfect. 1999 was just before the internet bubble burst. So our timing was great, but we actually survived. And in 2003, we were bought out and eventually became part of Cisco. So now I had some money finally, so I thought it was time for a midlife crisis. So I actually became a bureaucrat or an administrator. If you want to be a little more polite, I actually went back to Europe, to EPFL, to be what they call dean there, but what you would call head of school here. That's Patrick Hrvoje, the president at the time of EPFL, who talked me into it. And well, I'm sort of a bit flippant perhaps about this, call it a folly or a midlife crisis, but actually a very gratifying experience. And we were really able to turn EPFL from what was a regional engineering college to what it is now, which is a research powerhouse. So that lasted for 8 years, and then I went back to Stanford, and history repeats itself. I again met some incredibly smart people, Mohit Aaron, who was a student at Rice, and Deshpande. They had this idea of hyper-converged infrastructure. And so that's a little hard to explain for non-technical, non-computer people, but in essence, before that, storage was on one set of machines and computing was on another set of machines. Our idea was to put both of it on one single machine. And so you may think, why would you want to do that? Well, it means that you only have to maintain one machine, which makes it a lot cheaper and more possible to do that. So this was sort of, to me, an amazing story that the company was founded in 2009. I joined as an advisor in 2011. We had a $1 billion valuation by 2013. We IPO'd very quickly in 2015. And then you can see the story after that. With the vagaries of Wall Street, we actually we did pretty well as a company. So if you're in Silicon Valley, you're supposed to say that you've all predicted this and you knew this was going to happen. I had no idea. I was totally surprised that everything went so well. So time for a second folly or a second midlife crisis. After that, I became Dean of Engineering at the University of Sydney. I had actually spent the sabbatical semester in Australia, and sort of fell in love with Australia in the process and with Sydney. So I took this job as Dean of Engineering. However, I always tried very hard to keep involved in research on a smaller scale, obviously. And I'm particularly proud of this work with my student, Juana Balmau, and with the people from Nutanix, actually. So she worked on something called key value stores, which is sort of a storage mechanism that has really overtaken from relational databases in many internet applications. And so without going into the details here, she received several awards for her dissertation and for some of her papers. So with that, and with the time running down to a few seconds, we'll conclude by thanking the many people, my students, all the ones I could find a picture of, my many students, postdocs, collaborators. I'd also like to thank Professor Dajing Tao, who was my nominator, and thank you for your attention. Thank you very much.
Well, Willie, a very interesting career, and I guess it was important that you did have a midlife crisis.
Yes.
We'll now open up for questions to Willie.
Just a quick question. How would you describe the cloud?
Well, the cloud is, it's maybe a little self-serving way of describing it, but if you think of this network of diskless workstations that I mentioned, the cloud is essentially, the storage is remote. Typically, you don't store things locally anymore. You store it somewhere else. So to me, it's sort of compute and storage being remote and shared infrastructure. That's how I would define it.
Emma?
Hi, Emma.
Hi, Willie. Great to hear your story. I'm just interested in this computer science and all of the stories that you've told, whether or not you feel like you've learnt most on mathematics or physics or systems thinking, or is it a real combination of those that has helped you, make all these great discoveries?
So computer science relies on a very broad array of knowledge, sort of electrical engineering at the more physical end, mathematics at the more theoretical end, systems thinking at sort of the more practical end. So I'm very applied, and so in my case, I would say it's mostly system thinking.
One up the top.
This is a bit of a silly question, but did you ever manage to set a computer on fire by running something that was just a bit too demanding for it?
No, I must admit I've succeeded in quite a few things that I wouldn't want to mention, but never to put a computer on fire.
Okay, just because I've seen a red laptop catch fire at one point.
No, not by me, no.
We'll take one more, quick one.
Hi, I'm curious to know what you wish you'd known going into your bureaucratic roles.
That's a difficult question. I think it's the type of job that you really don't know what it is before you really get involved in. What I wish I had known. Yeah, I don't really know. Sorry.
I think we should move on.
Okay.
Thank you again.
Thank you.
Well, our lucky last fellow presentation is from Professor Mark Krumholtz. Mark is a world leader in the study of star formation and the interstellar medium. He has contributed fundamentally to our understanding of physical mechanisms that control the rates at which galaxies form stars, the mass distribution of those stars, and the way stars cluster in space and time. Please welcome Professor Mark Krumholtz.
Thank you, and I'd like to thank my nominator, Matthew Cullis, my family who are here, and you've heard some questions from my son. And I would like to thank, of course, all of my postdocs, PhD students, undergraduates, the many people who I've worked with over the years. This is a collective effort, as I hope to show later. All right, so I thought I would start by talking about not so much the results as the tools, because I've always thought of myself as someone who lives on the border between applying the tools to reach scientific conclusions and building the tools. And the tool we use is simulation. And the reason we use this so much in astrophysics is that, well, I sadly cannot put the galaxy in my office. It won't fit. We can't do controlled experiments. And so we have to rely on doing experiments in silico instead of in vitro. We do experiments on computers to understand how these complex systems work. The other obvious example here, as I've mentioned, is global climate, where they do a lot of simulations too, where we probably shouldn't do experiments. We are, but we probably shouldn't. And the other advantage we have compared to people who deal with complicated things like living organisms is that our systems are comparatively simple. We know the laws of physics that govern them pretty well. And those laws of physics are, in comparison to a living thing, the laws that govern a living thing, very, very simple. And so you have a well-posed mathematical problem. I know the equations that describe my system, and I just have to find a way of solving them. The problem is that solving those equations is not an easy thing. All right, so here's why. I'm showing you just 3 simulations my group and I have done over the years. On the left, you have an entire galaxy. On the right, you have the formation of a single star. In between, you have what's called a giant molecular cloud. And the scales go from 10 to the 20 meters to 10 to the 14 meters. Now, that's 6 orders of magnitude in dynamic range. So for those who don't normally think about this, all right, 6 orders of magnitude of dynamic ranges, I would like to simulate the entire Earth and resolve you, right, individual people. That's 6 orders of magnitude in dynamic range. And I want to emphasize, even in this most zoomed in simulation where we're simulating the formation of a single star, we're not resolving the actual star. If we wanted to go down to the resolution of resolving the actual star, that would be I would like to simulate the entire Earth and capture your individual cells. That's not so easy. All right, so the fundamental problem we face in astrophysical simulation is the curse of dynamic range. All right, and one way of expressing this is the basic thing we're doing is solving the equations of, say, magnetohydrodynamics. And the maximum time step we can take when we're advancing the simulation from one time to the next is limited by the size of our cells. And the net effect of that is that if I want to get twice as much resolution, well, the cost goes up by 2 to the 4th power because I need 2 times as many cells in every dimension, and then I need to take twice as many time steps. Now, you can do a bit better on the number of cells using adaptive techniques, but there's currently no practical way to work around the time step issue. All right, and so that means we're never going to capture the dynamic range we want, and we have to rely on what are called subgrid models. We basically have analytic estimates and prescriptions for things like the behavior of a star inside our simulation. But we want to do that as little as possible. We want to capture as much by doing the laws of physics right and relying on these models as little as possible. So how can we do this? Well, what my group and I have been doing a lot lately is taking advantage of GPUs. Now, for those who are not familiar with these are a type of computing device that has become very, very common in the last decade or so. And they weren't invented for science. They were invented so that my 13-year-old can kill hordes of virtual zombies as quickly and with as much, graphical gore as possible. But we can take this and use it for other purposes. And the advantage of these things is that they're very, very dumb, but very fast at doing something dumb. They can process very, very simple operations in parallel on large amounts of data very, very quickly. And the speed gains you can get relative to a CPU are large. All right, so just to put this in perspective, the fastest, most optimized CPU-based astrophysical simulation codes can take one of these computational cells and advance it 1 step forward in time in about a microsecond. On a GPU, I can cut that advance time down to about 10 nanoseconds. That's a big gain. That's a factor of 100. All right, so that's great. The challenge of GPUs is that they're really, really fast at computing and really, really slow at moving data. And we can't avoid moving data between the GPUs because the things we want to simulate are so big, we can't hold them in memory on a single GPU. We typically want to use hundreds at a time just because of the memory requirements. We can't put it all on a single GPU. We have to distribute different parts of the volume over hundreds. And it turns out that you also can't avoid data movement entirely because some of the physics we want to simulate, for example, gravity, is effectively non-local, meaning every part of our simulation talks to every other part. Now, it's not really non-local. The laws of physics are local, but this information propagates at the speed of light, which is really fast compared to everything else, so it's effectively non-local. All right, and so the challenge is that many of the algorithms that we've relied on traditionally in astrophysics that are optimized for CPUs and that work well on CPUs just don't work on GPUs. They're incredibly slow and inefficient. And we have to just design new algorithms to deal with the new computing hardware. And this is, unfortunately, in the simulation world, something that we go through regularly. As computer hardware changes, the optimal algorithm for simulating a given physical system changes. We're solving the same equations, but there are many ways to skin a cat. There are many ways to solve a given set of equations. And you have to know the hardware in order to choose the best software. So we've been developing this thing called the Quokka code. Quokka is the quadrilateral umbra-producing orthogonal coordinate kangaroo-conserving code for astrophysics. You will learn a few things from this. One is that astronomers are fans of terrible, terrible acronyms. This is not the worst. This is nowhere near the worst, I just want to emphasize. The second thing I want to emphasize is you may kangaroo conserving. Well, I guarantee running this simulation code does not change the number of kangaroos in the world. It therefore conserves kangaroos. It's kangaroo conserving. So Quokka is this next generation GPU accelerated simulation tool we've been building. It has adaptive meshes to minimize this fourth power problem. By adaptive meshes, I mean we don't have the entire simulation volume at the same resolution. We put the resolution only where we actually need it. It includes magnetohydrodynamics, self-gravity, radiative transfer, lots and lots of fancy math goes into the design of these algorithms. I'm not going to try and go through it. I'm just going to show some numbers here, which is that we achieve, as I said, 10 or 20 nanoseconds per cell advance for hydrodynamics, and for non-local physics like radiation, it costs maybe 50 to 100 nanoseconds per cell. That's much better than you can do with a CPU code. And the cost of the non-local physics to the local physics, the radiation to the hydrodynamics, is only a factor of 5 more, which is much better than you normally achieve in a CPU code. And crucially, the parallel efficiency is very high. And what I mean by that is, how long does it take you to do a simulation using, say, 100 GPUs versus 1 GPU? Now, of course, 100 is going to be faster. Ideally, you'd like it to be 100 times faster. In real life, it's never actually 100 times faster because there's always some overhead associated with moving the data between the different GPUs. We've reduced that overhead to only 10%, which is remarkably good for what we're doing. And so we can use basically all of one of the supercomputers like Gaudi and Photonics efficiently. They won't let us use all of it. We'd like to, though. All right, so this is what you should take away from this. This is our rocket Quokka. All right, so I'll end on sort of a sample application, which is the problem of galactic winds. So in galactic winds, we have one of these multi-scale problems where supernova heated gas at 10 to the 7 Kelvin is dragging up these suspended droplets of cold gas at temperatures of, say, 10 Kelvin, which are much smaller, and that's hard to simulate because of the dynamic range. And here's what we could do with Quokka. So I'm showing you a slice through a piece of a galaxy. I'm only showing you the top half just so it fits in the domain. And I'm showing you just 2 views. One is showing the density of mass, the other is showing the density of metals. And just so you can appreciate the dynamic range we can achieve, here's a zoom in. Oops, if I can get that to advance. So that's the sort of dynamic range we can achieve. What I'm showing you there is just to zoom in. That's only a small part of the simulation box. The entire simulation box has this tiled 8 of them over the domain. So that's the sort of thing we can achieve with this tool taking advantage of the latest technology. All right, and I have some final thoughts, which is a challenge we face in astronomy is that to develop tools like this, we rely on people who are as much computer scientists or software engineers as astronomers. And we have a challenge in that we don't have a real career path for them. People who design research software, who are tool builders, it's hard for them to get jobs because they're not writing tons of papers. They're great at writing software, but they're not producing tons of papers. And if our field is going to rely increasingly on this sort of specialist software skill, which is what we're being driven to by advances in computing hardware, we need to find a career path for these people if we are going to keep taking advantage of their skills. So I'm going to end there. Thank you.
Thank you, Willie, for a very stimulating talk. Ivan.
Thanks, Mark. Fantastic talk. I'm wondering, in these simulations, using subgrid models, is it possible to have grid independence? In other words, how do you know when you have the right grid?
That's a really good that's a really good question. I mean, one of the hardest problems we face is that when you're relying on a subgrid model, you can't do a proper convergence study, right? So the answer is you try and limit your subgrid models to things where you're really confident you understand the physics and that they're scale independent. So an example of that is like stellar evolution. That's not a solved problem, but it's a pretty solved problem. And so if your subgrid model is just, I'm not going to capture individual stars and simulate what's going on within them, you sort of feel okay about that. But yeah, one of our real challenges is that you have to sort of do bespoke experiments to figure out if you've got enough resolution and if you're getting an answer that's independent of the resolution. It's a real problem.
And yet, up here.
Thank you so much for the very nice talk. So I'm just curious, so have you, in terms of the scientific inferences drawn from these simulations, could you tell us some examples of, some aspects in which the inferences drawn from the high resolution simulation differ very significantly from those at low resolution simulations?
Sure. So in the example I showed of galactic winds, so one of the big challenges in studying galactic winds, the big questions is what's called the mass loading factor. That is, for every gram of mass that's converted to stars, how many grams of mass get blown out of the galaxy in the galactic wind? And that's a hard problem to study observationally because you have all of these different phases of gas. You have the hot gas at 10 to the 7 Kelvin. You have the warm gas at 10 to the 4 Kelvin. You have the cool gas at a few thousand Kelvin. You have the cold gas at 10 Kelvin. Each of these emits in a different part of the electromagnetic spectrum. And they're very hard to put together observationally. So one of the questions you'd like to ask is, all right, I want to know the mass loading factor. Which phase is carrying the mass? In low resolution simulations, you don't capture those little droplets of cool gas, and you tend to completely miss them because you can't resolve them. And so you wind up with the conclusion that the mass is mostly carried in the warmer or hotter phases because you can't resolve the colder phases. When you go to higher resolution, that answer changes. And you find that, in fact, most of the mass is carried in the cooler phases. And that seems to agree better with what we're seeing in observations. But it's an ongoing problem. But that's an example of something where you need the resolution to get the right answer, even in a qualitative sense.
Greg, quickly.
As someone involved in the data center and artificial intelligence background, I categorically disagree with your final comment that it's hard to get these your students jobs. I think they're in huge demand and we need more and more of them. It's not an exciting job like astrophysics, but we just need them. And Australia in particular is very short of people in this area. And the people I work with, we're finding that all our people with the sort of skills you're developing at a very high intellectual level are having salaries doubled and tripled by other companies and are being shipped offshore. I just wanted to throw that into the mix. I think with the students you're training are the people we need for this economy.
Yeah, so I should be clear. It's not that they can't get jobs. They can get jobs getting paid way more than I do. it's that they can't get jobs in science. It's that they are very well trained and they would be great to have around developing scientific software, at least for me, and the problem is there isn't a career path for them to do that. And so yes, a lot of them, I mean, my former students work at Google and Amazon and Microsoft Research, and yeah, they can get tons of jobs and again, get paid way more than I do. But we need to keep at least some of those skills in the sciences, and right now, we don't have a good mechanism to do that.
I think we're going to have to wrap it up or we'll miss the gala dinner. I'd like us to thank all of our speakers in this session. And pass over to Anna Maria to conclude this.
Thank you. Thank you for all your presentations and such a stimulating day. Special thanks to Professor Krumholtz Jr. I've loved your questions and we look forward to seeing you on this stage soon enough. It's fantastic. Thank you for being here. It's really lovely when family and friends are able to join on these occasions. Thank you to our online audience. There have been many people watching, and to all of you for your participation, and to Jim, Margaret, Alan, Francis and Ian for facilitating the sessions today. For those of you joining us at the gala dinner, that's being held, as you know, at the National Arboretum. We'll be hearing from the Governor-General, from the Science Minister, Ed Husic, and the Leader of the Opposition, unfortunately, has had to pull out at the last minute. So the Shadow Minister for Science, Paul Fletcher, will be delivering his speech on his behalf, and we'll be able to listen to the awardees or give the awards out of our prestigious career honorific awards to awardees. There are coaches departing from Peppers, Siebel and Novotel hotels at 6:45 p.m. and they are returning at the conclusion of the gala dinner. You do not need a booking for those coaches. You simply need to be out the front of one of those hotels at 6:35 p.m. to take advantage of those transfers. Pre-dinner drinks are being served from 7 p.m. and the formal proceedings will begin at 7:30 p.m. and we will have to start at 7:30 p.m. on the dot. There is some grab and run afternoon tea outside, so don't leave through the side doors. Leave through the main door and you will be able to grab some goodies to have on the way out. If you are not coming to dinner, we will see you here tomorrow for day 4 of Science at the Shine Dome, bright and early tomorrow morning. Thank you everyone in the theatre and online. That brings today to a close and I look forward to seeing many of you tonight.